I think we're about time to start. So welcome everyone to Haskell Implementers Workshop 2021. My name is Ningning Xie and I'm the program chair of HIW this year. I'm going to start off with a little of basic information you need to know. So first of all, you can find the whole program of this year's HIW online, and I believe many of you might have already seen it. We will have 4 very exciting talk sessions with 1 keynote after the first talk session. Presenters, please get ready 5 minutes before your talk. When it comes to your talk, please speak up in the chat or raise your hand so that we will be able to promote you as a speaker. You will not be able to speak until we promote you as a speaker. The whole program will be streamed on YouTube, and for people who have registered for HIW, it is also available on AirMeet, the virtual platform that hosts the SFP and all co-located events this year. So if you have registered, please consider switching to AirMeet, which you will be able to get a more interactive experience from. We will have Q&A at the end of each talk. Attendees on AirMeet, please ask questions on the Q&A tab or raise your hand, and our session chairs will help moderate with questions. Finally, I'm co-hosting this workshop with EDSCO, so if you have any questions regarding talks, Q&A, or your roles as speakers, please feel free to reach out. For more general questions, please visit the help desk in the virtual lounge on AirMeet or reach out to the SFP technical team. You should also be able to find their names in the attendees' instructions sent by the conference before. So now, without further ado, let's head off to our first talk session.
And I'm going to speak to you today.
Our first talk is from Alan Zimmerman, who will present us exact print annotations in GHC.
About exact print annotations in GHC. If you recall, I spoke last year as well about the plan to move the exact print annotations and the processing into GHC, and today I'm reporting on those results. The goal is to give a 10,000-foot overview to firstly orient GHC developers and API users who wonder what on earth this is, and to give some pointers for previous users of GHC exact print as to what will have to change. But first, an overview of what exact printing is and why it's important for tooling. As its name suggests, exact printing aims to reproduce exactly the original source of a file parsed by GHC. It does this by storing the exact original forms and locations of all parts of the original. Apart from the obvious things like keywords, comments, and so on, things like literals also need special treatment. So the compiler captures the number 1 for all 3 of those forms, but obviously the source is different for each. And even things like language pragmas can be spelt in a case-insensitive way, so we need to capture the original. Exact printing has a further goal, though, to allow the parsed AST to be modified and then exact printed so that all the unchanged parts remain exactly the same. This allows us to write tools to modify code, for example, adding a new import without disturbing the rest of the file. This is complicated by the fact that Haskell is layout sensitive, so special care must be taken when moving a piece of code from one place to another where its indentation may change. For example, in this let expression, if we change the XXX to be XXX longer, the entire piece needs to move off, and it does with the exact printing that we have. Exact printing has been available for tool writers since GHC 7.10, and there's a whole ecosystem of tooling built on it, from formatters to code mods, retry, and so on. What is changing from GHC 9.2 is that the locations of the additional items, trivia as they're called in Swift and Rust, are now captured directly inside the GHC AST. The GHC exact print library is still distributed via Hackage and is still the one to program against if you've used it up to now. But it's been heavily updated and as such gets a major version bump. It's going to be 1.1 and it loses backward compatibility. I didn't go 1.0, it's a bit, people get weird ideas on that. Changes to GHC exact print. There are three main effects from the perspective of tool writers. First of all, the indirect type of the API annotations is gone. They're now called exact print annotations as well. They used to be tied together via the source span and constructor name. They're now captured directly in the AST. We also no longer have a two-phased approach inside GHC exact print. We used to take the raw output from the GHC parser, run it through a delta phase, which made all the offsets relative, and then allow you to manipulate that and then print it. And also no longer need to add default annotations for freshly parsed or constructed pieces of AST, because for some time now the GHC Pretty Printer has a guarantee that anything you pretty print will parse back to exactly the same AST, modulo locations, but the actual structural AST is the same. One of the other things that's changed in GHC 9.2 is an internal restructuring of the modules making up GHC itself. For our purposes, that means the old GHC.hs hierarchy has been split into language.haskell.syntax, which is completely general and intended to be separate at some point and can be used for template Haskell or any other usages that just need the syntax tree, and GHC.hs, which provides the specific usages inside GHC. It populates the extension points, defines the parsed, renamed, type-checked variants, and so on. When I use the word AST, I'm talking about the parsed source in the stalk, which is defined in GHC.hs and includes the GHC-specific interpretation of the trees that grow extension points, which are used for the exact print annotations. So to be precise, the parsed source is a located HS module, and inside HS module it's specialized to GHC parsed phase, the parse phase. Another thing you'll notice about the new AST is that it's littered with extract types. Extract is defined as a type family where P and A determine R, and R in turn determines A. Within the GHC.hs side of things, extract is defined on GHC parse for all the parses that are GHC specific to be gen located, and another type family anno of A, where the type family just maps the A to a particular annotation based on it. So for example, we have for this LHS expression is extract P of that. In GHC, we say that the anno for the HS expression in the GHC parse is a thing called a source span an A, which I'm not going to go into detail now, but it's a source span with annotations in it. The machinery for going from an extract declaration to the actual annotation to be used is very awkward to use in practice, especially since it's split into the two parts, language Haskell syntax and GHC.hs. means the extract definitions occur in one branch of the source tree and their resolutions in another, and not always in an easily searchable way, because the type family resolves to the expanded synonym, not what you type. To see the expansion of the example before, LHS expression converts extract GHCPS, because we care about the GHCPS variant, which is gen located anno, which then, because of the other type family, maps to source span and A, and we have an alias that this gen located source span and A is also known as located A. So we've got a shortcut. And there's even more detail. If you look into the source span and A, it's a source N with a list item, which is defined as one of those, but we're not going to go into that detail. Look it up in the source if you care. So as a GHC developer, not really interested in exact print annotations, you have probably been confused at the changes and a little bit lost. But all is not lost. A is your friend. The most common annotation type is the one shown for the LHS expression earlier, which is used for items appearing sequentially. That AND list tracks the basic bookkeeping of an entry. The annotation tracks the basic bookkeeping of an entry, location, and comments, as well as any trailing trivia based on it being in a list, such as commas, semicolons, and so on. And we gave it that type synonym ending in A, which is located A, as you can see there, just a recap of before. This means that, in general, we've taken the naming convention that the normal versions simply get an A at the end. So located becomes located A. Getlock has getlock A. Nolock has nolock A, and so on. Which means that, in general, if you're getting stuck and it doesn't quite make sense, then put an A at the end of the normal one and you may get out of the hole fairly quickly. Okay, GHC ExactPrint itself has got, it's had some major changes. In the prior GHC ExactPrint, the output of that delta phase gave us this annotation type. This is linked to the AST item documents by the source span and constructor name, and this is the data part of it. And in this case, you have an entry delta, which is this thing called the delta pos. That's just a line and column offset between this thing and the thing that came before it. It's got comments that come before this thing and comments that appear within the span that this thing annotates. The actual payload is this ANS DP, which was a mapping of keyword IDs and delta positions within the AST, and the sort key we're not going to worry about. The new ExactPrint annotations capture the same basics, where you have your entry point, which is that one, your annotations, which is that one, and your comments, which are those two. But the anchor is a little bit more flexible. Essentially, it always has a real source span in it, which is used, we call it an anchor because that's used to calculate the deltas to all the sub-elements within this particular part. But when it's first generated by GHC, it will always be an unchanged anchor. If we want to modify the AST for our own purposes, we can call it a moved anchor and add a delta pos. We still need the anchor because that only adjusts how this fits into the sort of upper level stuff. The parts inside this AST element are still captured with reference to the anchor. Another highly visible change is that the delta pos type, which was used to capture all those deltas, was a little bit bad before, so it's become more useful. It now expressly says it's on the same line and has only got a column, or it's on a different line and it's got a line and a column. Strictly speaking, we should somehow encode that the line is always greater than 0, but I'll leave that for people coming beyond. And these are mostly, when we come across them, it's wrapped in an EPA location, which is either the real span as coming out of the parser, or we can give it a delta, which allows us to change the location of items and work in a purely relative zone without having to try and make source spans, construct source spans that make sense relative to each other. And this duality of having the span and the delta is how we actually get rid of the delta phase, because if you don't change anything, then the original spans are still valid, and we just print. In the printing phase, we convert them into deltas and then print, or you can put in the delta directly. And that means you can, if you change an entire subtree, if you move a subtree in the AST, you only need to adjust the top part with the delta, and the rest will just carry on lining up because it's all the relative spacing that we care about. This is what the new annotations feel like in the new AST in a good case. Here we have a let expression, we have the trees that grow extension point, which is xlet. Its instance for the parsed phase is defined as this EPN, which we had before, those three different things, specialized on ANS let. And ANS let is defined as a location of the let keyword and the in keyword. So it explicitly captures what is in the trivia we care about. And here's a quick look at how changing ASTs with the GHC exactprint transform module changes between the previous version of GHC exactprint and the new one. This is using the prior version of GHC exactprint. It's adding a local declaration called new decl to the first declaration in the file. So hsdecls gives you a list of all the declarations in order. You need to balance the comments. The comments are all heaped up before D2. So if anything actually belongs to D1, then we need to split them up between the two, so that when we add new child expressions, they get the comments lined up in the right place. So this modify val_d is a way of diving into a function bind, pulling out the match dependent on the location of the match expression we care about. It gives you the actual match and the child declarations in it, and whatever you return is the new declarations, plus this other part just comes back if we need it. And then we replace the declarations with them before, with the new ones. The new variant is very much similar, except we can't use the variable D1, we've got to call it DE1. D1 is now a short form for a delta pos of same line 1 space. You'll notice that the balance comments now explicitly returns values because it's in tree, so we don't, it's still in a monad because we need to be able to give out fresh source spans, but the changes themselves happen in a pure fashion. The declaration, we have to wrap a declaration here. In fact, this new decl in the previous one was already wrapped. That's just because declarations have always got it's a val_d that wraps a fun bind, and that's all that does, and lines up the annotation. And we just replace them as before. So the coding, you switch into a slightly more pure style of coding, but otherwise the general structure of it stays much the same. So, wrap up. The basics is the API annotations have now been renamed exactprint annotations. They've moved into the GHC source tree as first-class citizens. This has benefits. We have tests of actual usage in the tree, and all the pieces related to this machine row in one repository. And that the major benefit of that is, first of all, it allows developers working on GHC to have some confidence that the updates of the API annotations are actually reasonable and make sense, because you can see them directly and you can see how they're being used and hopefully update whatever tests need updating based on it. So it should make developers' jobs easier. And it also allows us to do incremental improvement and removal of the rough edges. This has been a huge task, and it had to come in as a whole. You know, people rely on this functionality in the current versions of GHC. The entire functionality had to be made available in the new version. It means there are some parts that are not wonderful, but because it's now in and it works, it allows incremental updates to happen. And in fact, we've already got some coming. There's some discussion around not using the trees that grow extension points, but putting the trivia directly in the tree so that it's even more clear what's going on. And this refactoring is starting to happen. But as I say, because the whole is there, we can now start making changes. And here are some resources. The wiki page relating to this whole effort, which is sort of up to date. Sorry, I'm not very good at that stuff. The new GHC 9.2 version of GHC exactprint, it is tested against current, that branch in the GHC tree. I believe a new release may be out by the time of this talk. It's imminent. And Shane Fletcher wrote a blog post on his experience of updating the GHC, his parser, GHC lib parser, to use this. And he's got some resources there as well. And that's it. Thanks very much.
Great, Alan. Thank you for your great talk. Now I'm going to bring you to the stage so you will be able to answer questions. So we got a couple of questions on the QA tab.
Right. Hello, everyone.
And the first question is for Andres. Yeah.
Great. GHG itself does not use ExactPrint for anything at the moment, primarily because in the previous version, it was unusable without the GHG ExactPrint library. We now have a copy of that library inside the test utils, and I put it there because it's not clear where it should live. The separate GHG ExactPrint library is the thing to program against. A decision can be made by the developers as to where precisely the sort of master version of it lives. But now that it is in tree, in principle, it can start getting used for more things.
Cool. And then I will mark this question as answered. And we will move to our next question. So the next question is from Yuji Yamamoto. And the question is this talk about the ANN pragma?
No, it's not. Sorry, that's confusing. I should perhaps have clarified it right in the beginning. These are the ExactPrint annotations and are unrelated to that pragma.
Cool. And if there are many more questions, please ask in the QA tab or raise your hand, so we will be able to bring you to the stage. So when I listen to this talk, one thing I have been wondering is like, so how challenging is the implementation of this exact annotation? So what's the biggest challenging, if I may rephrase it?
The original biggest challenge was just coming up with a mechanism that actually worked, which was in place for GHG 7.10. Matt Pickering worked on GSOC 1 year and cleaned up the implementation quite dramatically. And for this case, it's just a huge amount of detail of just working through everything, making sure that it actually fits in everywhere and that every single case gets covered. The normal process before doing a release is to make a local copy of the entirety of package and run it on all of that. I just finished the most recent one. It's 165,000 source files that we process and ensure that every single one of them can be reproduced.
Cool, that's very impressive. If we don't have any more questions, then we will move to our next talk. So thank you very much, Alan, for this great talk.
Sure. I hope you enjoyed it.
Yeah. So our next talk is from Haskell, and he will tell us how to avoid quadratic GHC core code size.
My name is Edgar de Vries. I'm a Haskell consultant with WellTyped. Today I want to talk a little bit about sources of quadratic core code size in GHC. And this is work that I did with my colleague Andres Leu on behalf of JustPay. Consider this module where we have a record with a bunch of fields. In addition to the record, we have some instances, show, eq, SOP generics to JSON, and we're using the record.preprocessor plugin to generate lenses for this record. Turns out, the size of the core generated for this module is quadratic in the number of record fields. And we will see in this presentation why that happens. By contrast, if we're using the large records library, the size of the record of the module will now be linear in the number of record fields. But we still get all the instances, including generics, albeit a different kind of generics, and the lenses. Does it matter? It does. If we have a record of 100 fields, the size of the AST in basic GHC goes up to nearly 500,000 nodes. That's terms, types, and coercions. Whereas for large records, the library, it stays down here at nearly 5,000. So that's nearly 2 orders of magnitude smaller. After the simplification, it's slightly less dramatic, but it's still 350,000 compared to maybe 30,000. So still an order of magnitude smaller when using the library. In terms of real resources, OS reported memory usage goes up to nearly 500 megabytes with core GHC, with basic GHC, whereas with large records, the library, it stays down here flat at nearly 100 megabytes, and this is normalized, by the way, to an empty module. And similarly, compilation time goes up to nearly 3 seconds with basic GHC and stays under 1 second with large records, so 3 times faster. Again, this is normalized to compilation of an empty module. There are 2 main sources for this quadratic code size. One is that we have no way of accessing or updating a record without mentioning every field, and we will see 2 examples of this. And then the more tricky one is that we have no way of introducing and controlling sharing at a type level. And we will see a few more examples of this because this is the more difficult one. So first of all, records. The moment that you define a record in GHC, you get quadratic code size right off the bat. Why? Well, GHC generates field accessors. Each of those field accessors has a pattern match on the record and extracts exactly one of the fields of the record. Since every field accessor needs to match and mention all the variables in the record, each field accessor is itself linear in the size of the record. Since we have one of these for every field in the record, that gives us quadratic code size immediately. Similarly, for the lenses generated by the record.preprocessor plugin, those lenses look like this. Like we have the accessor generated by GHC and we have a setter, which is just a field override. This looks fine, but after desugaring, it looks like this, right? We have 2 of these pattern matches now, and then for the setter, we also have a third of these blobs where we are constructing the original record, except that we're overriding 1 field in the record. Right? So clearly this is linear in the size of the record, and we're going to have one of these lenses for every field in the record, so again, quadratic code size. The second example in this category is type class dictionaries. So if we consider this class here, which is meant to capture the concept that some constraint C applies to every field in the record. In core, this looks just like the definition of a record, right? We're going to get a type class dictionary, which is going to have 100 fields, 1 for every superclass constraint, and accordingly, GHC generates 100 accessors, right? Each of those accessors does a pattern match. Those pattern matches are linear in the size of the record. We get 1 for every superclass constraint. So a class like this is quadratic in the number of superclass constraints. And if we have 1 for every field in the record, that means it's quadratic in the size of the record. Okay, let's move on now to the more subtle problem, which is types. Consider this function zip, which is going to zip 2 records together with given some function that we are going to apply pairwise to every field. Now clearly we're going to have to apply this function once for every field in the record, right? So clearly we're going to have 100 of these applications. That's expected. However, if we look at this in core, each of the applications of the app operator, the applicative app operator, has a type argument. That type argument tells us the types of the arguments that we get to apply. That argument is itself linear in the size of the record, right? First we have all the fields, then 1 less, then 1 less. And so this means that although we have 100 lines, each of those 100 lines is itself linear in the size of the record, and so this function all by itself is quadratic in size. As another example, consider this type of heterogeneous products, right? So this is coming from the SOP library. It's indexed by some functor and a bunch of types. So we can construct an NP, a heterogeneous product, from our record simply by just consing all the fields together, right? Easy enough. But although we have 100 applications of this cons operator, those cons operators have a type argument. That type argument tells us the type level list of the fields yet to come. And so in core, this looks like this, right? Where we have 100 applications, each application tells us the tail of the list. The tail of the list is linear in the size of the record, just like before, so this is quadratic in the size of the record again. Now, the previous two examples were examples where we were writing the code. The next two examples are examples where GHE is writing the code. Consider this definition of singletons for lists, along with a class that says that we must be able to produce a singleton for a given type level list, right? Which has a standard two instances, one for nil and one for cons. This is fine by itself, but the moment that GHE needs to generate evidence for slist I for a concrete type level list, it's going to look something like this, right? If we need to produce a slist I instance for a list of 100 elements, we're going to have 100 of these scons applications. That scons application has a type parameter, right? The tail of the list. That tail of the list is itself linear again in the size of the record, and so quadratic code. As a final example, consider this from this type definition this definition of a type family which computes a constraint. This is coming from how the large records library deals with generics. It doesn't really matter what it does too much for the purposes of this talk, but the only thing that matters is that we are looking at every pairwise element of these lists and computing some kind of constraint applied to these elements. Right? So we have a constraint here and then whatever else. Now this is fine, but when GHE needs to produce evidence for a concrete type level list, it needs to produce evidence that looks like this. We're going to have 100 cons applications, right? This cons operator here. Each of those has a type argument. Again, it's the type of the evidence yet to come. That evidence is, the evidence for all other arguments, then for one fewer, and so again, that type argument is itself linear in the size of the record, the size of these type level lists here. And so quadratic code. So how does the large records library manage to avoid all this? Well, when you define a record like this, what gets spliced in is actually something like this, right? The record just becomes a vector of any. So GSC does not see at all that this is a record. We're basically giving up on type safety internally in the library. The user still works with the type safe interface, of course, but internally we have no type safety at all. So since this is a record, since it's a vector, we can just get an element from the vector or set an updated element from the vector easily. And that means that we can then define accessors which just use the vector get. And we can define lenses that just use the vector get and vector set. Of course, we still have 100 accessors, we still have 100 lenses, like linear, but each of those accessors or each of those lenses is itself constant space, right? In fact, they're tiny. So this is not quadratic. We do not currently provide a pattern synonym for the record because the moment that you define a record pattern synonym, GHE produces field accessors for every field in your pattern synonym, and we're back to square one. GHE 9.2 has no field selectors, so that might hopefully make it possible to define a pattern synonym, but I haven't yet experimented with that. The other thing I want to show you is how we deal with the dictionaries. Remember, so not only do we have our own representation for records, we're also going to have our own representation for dictionaries for those records. Because I showed you before that defining a class that has n superclass constraints results in something that is quadratic in n. So how do we avoid this? Well, we're also going to have our own representation for the dictionary. And that representation looks like this here. It's the rep, R here is some sort of record, with dict C. What is rep? Think of rep as a vector that contains an element for every field in the record wrapped in some sort of functor f. Right? And in this case, the functor that we're choosing is dict C, meaning that rep of dict C is a vector that has a dictionary for every field in the record. In other words, it's a typed as dictionary, but we're using a vector rather than a record. We then have a single instance that produces one of these dictionaries, right? A single instance for this class. That instance has 100 superclass constraints, but that's okay. This will become a function that has 100 arguments, so linear, but there's no compounding factor, right? So it takes 100 arguments and then basically just sticks them all together in this vector here, and that's it, right? So it doesn't need to do very much more than that. And it's linear in size, not quadratic. Now, this thing is called rep because it's the generic representation of something, of a record, in large records generics. But notice here that this A is phantom, right? Meaning that we don't have any type level lists almost anywhere, because it's very difficult to work with type level lists in a way that doesn't result in quadratic code size. The final thing I want to show you is this function normalize here. Now, normalization, again, is part of how large records does generics. That's a topic of a different talk. For the topic of this talk, only two things matter. We have some kind of constraint here, but the function is unsafe coerce, meaning the constraint is important for safety, but we're not actually using any evidence. So what is this constraint here? Well, it's actually just a wrapper around this interpret2 function that I showed you before, right? And I showed you this function because I said it was no good, right? If we have evidence for a particular concrete list, then that evidence will consist of 100 applications of this cons operator here, this comma operator, each of which has a type argument linear inside to the record. So this is no good. So how do we fix it? Well, we actually define a slightly stronger version of this. Rather than saying that these things must be coercible, we're going to say that they must be equal, right? This coercible here. We're going to make that stronger and say equality. What does it enable us to do? We can now define this like follows. We're always going to compute the trivial constraint. When we have two elements to compare, we check if they're equal, which using this potentially stuck type family, right, partial type family. If they're equal, we just continue with the rest of the list, eventually coming down to the trivial constraint. If they're not equal, this doesn't reduce at all, right? So that means that we get no evidence, which is what we want, and therefore the evidence that we generate is not quadratic. It's in fact constant, right? It's the trivial evidence. So to conclude, avoiding quadratic code size is difficult. It's often that I was working on this and I thought, surely this is going to be fine, and then I ran my benchmarks and oops, quadratic code. So it's not easy at all. Large records does it, but at the cost of internal type safety. We have also no support for unboxed fields. We could do it, but it would make a whole lot more things more complicated. Now, of course, it's a huge hack, right? It would be much nicer to do it in GHG itself, but I think that would not be easy at all. Especially the type level stuff is probably worth a PhD or two. That's all I wanted to talk about. If there are questions, I will be more than happy to answer them. Thank you very much.
It's great talk. Okay, we have one question, and I will bring on the stage, and that is from Joachim, and he says, wow, doesn't that issue heavily affect GHC itself with its huge dyflex record? Shouldn't that incentivize GHC to fix that problem in core, or is it not so bad for them for some reason?
Are you bringing him onto the stage, or will I just answer?
Okay, I will also bring Joachim to the stage.
All right, I guess you read my questions already, so we should get all the other people on stage who already proposed answers on the chat. So I guess Andres and who had good answers, Andreas. So maybe we can get them here and they can tell us about it.
We can do that. So let me first answer, while Ning Ning brings other people on stage, let me just first say my take on it. I think, yeah, the problem is, so we're looking at compilation time here, right? And it's the compilation time of the record. So even in GHG, the compilation of DIN flags might be expensive and it might generate a lot of code. You pay for it once and you don't pay for it when you use the record. So I think the problem for GHG itself is probably limited. That is not always true. Like when I talked about the type level stuff, that tends to affect client code much more. So if you have, but that's not a problem with DIN flags, right? That's a very simple ADT. There's no type level stuff happening there at all. There's no generics. So it's not a huge deal. But yeah, like in terms of the full GHC compilation pipeline, I have no idea how expensive it is. It's probably not that significant, I would imagine, but I could be wrong.
But maybe we should convince the GHC developers that they have a problem so that they can fix it in GHC rather than having poor ETSCO write a library that does something that should just work out of the box. So
I totally agree. Yeah, I mean, this library is one enormous hack. I have never written so many unsafe calls in my life before writing this library. It's been an interesting combination actually of some high level, like fairly advanced type level stuff with some extremely low level hacks. But yeah, I would very much rather not have to do it, and this should be solved in GHC itself. Yeah, for sure.
Yeah, I think a short-term solution was needed here, and the other aspect is that I think if we just had said, like, let's turn this into a research project immediately and just fix GHC, we either would have done it incorrectly, or we would still have had to go through a phase where we even just discover all the different sources of quadratic behavior, because intuitively we had a certain idea of what causes quadratic behavior, and some of these ideas were correct and others were incorrect, or at least there were many more sources of quadratic behavior than we originally thought there would be. So just addressing one of them is not enough. So now we have a rather complete picture because we have at least a hacky solution that that works.
and is there a chance of getting that fixed at core? Like, are there ideas floating around, or is it basically we have no idea how to do this cleanly?
I mean, partly. I mean, the record stuff. I mean, there's some partial stuff in GHC. I think there's primitives for accessing records in constant space, but not updating, as far as I'm aware. As far as the type level stuff, I mean, that also comes back to Richard's question. So maybe we should bring Richard's question onto the stage. But yeah, that's apart from the paper that Richard mentions. I'm not aware of any other. I mean, work on sharing, like in general, if we could control sharing at the type level, that would be great. And we could do much better. But I'm not aware of any. Andres, are you aware of any research in that area?
No, I'm aware of the paper that Richard mentions.
Sure, but that basically just says let's remove types.
And I'm aware of certain like ad hoc ideas as to introduce explicit type level sharing in core. But I mean, to me, I have not deeply looked into any of this, but to me, it's always been unclear how this precisely interacts with all the other core-to-core transformations that GHC has. And you have to be extremely careful that like this explicit sharing is maintained throughout all the core-to-core transformations, but also that it does not block somehow any further optimizations that otherwise would happen. And this combination seems at least difficult to me intuitively, but as I said, I haven't spent very much time looking at this yet.
Hi, everyone. I think I'm on the wrong camera here. Hold on. There we are. So, yeah.
Could you read your question, Richard, for the live stream people? They can't see the actual question.
Okay. My question is, how does your approach compare with scrap your type applications? That is, do you think that scrap your type applications would fully eliminate these sources of quadratic behavior, or would it be inferior, but better because it's actually part of core? So it sort of does a worse job, but more conveniently.
I think it would do. My intuition is, but you could maybe tell me better than I know, Ken. But my intuition is that it would go a very long way, and maybe indeed solve all problems. Because I mean, you ask like, how does it compare? And basically, the way that we solve the type problem is by not having types, right? I mean, large records it does away with all type level lists. And we had to jump through a lot of hoops, especially to make the generics work. We had to invent new concepts, new ways to do it, to make that work at all. And I'm glad that we found such a way, but yeah, it's not at all easy. So if we could, like a lot of the stuff that we would like, a lot of the ways in which we would like to express our problem, we were unable to use, right? Because they would result in quadratic code. So yeah, I think scrap your type applications, at least by my understanding, could go a very long way to solving most of these, because a lot of these duplicated like tails of lists everywhere would just not be there. But I don't know if, like, I'm not an expert on this paper. I don't know if they would like end up having to be recovered, and maybe that would have its own costs. I'm not entirely sure. Maybe you have an insight in that.
I don't. I mean, I'm a paper. I have not read it or thought deeply about it. All I know is that it's complicated, and there's some skepticism about whether it would overcomplicate the compiler. But also, I realize as I'm thinking, wouldn't fix the record problem.
No. Those are two
I mean,
completely orthogonal. Yeah. These are two completely orthogonal problems. I suspect the record problem, if we were willing to modify core, is easy to solve. Now I know there's an enormous reluctance to modify core. So, but if we were like, if people would be okay with having, you know, the right primitives in core, then that's I don't think it's a technically difficult problem to solve. I think the type level stuff is much more interesting in that sense.
So if you're looking at the chat, Christian has an interesting suggestion that if we had top level bindings for types, that might bring some, or even not top level, because actually GHC already supports local let bound types. So in your sort of quadratically sized type level list where you just keep repeating the tail over and over and over again, if we define sort of each con cell in the tail as a separate let defined type, then you could probably do that without using quadratic space.
Yeah. Yeah. So just for the live streamers, Christian suggests like independently typed Haskell, we can have top level bindings for things of type. And indeed, yeah, I think that might go a long way.
For control at the user level, at least, like at the GHC level, we could still have like it could just use types in them instead of expanding the list and just do some common sub expression elimination locally. But,
Yeah, you might be right. I mean, it's certainly, for the easier examples, I can certainly see it solving the problem. I don't know whether or not there will be more complicated examples where it might be more difficult with bindings or things like this. I mean, like Stephanie says, like we might need like type level let, and that we might be able to control. But yeah, with top level annotation, we might already be able to go quite a long way. Yeah, I agree.
Just to be clear, they're not top level bindings, although just an ordinary type synonym could do that. They're sort of local let bindings that exist today, but we could perhaps just enhance that a little bit.
I mean, the key thing there is that you should be able to like preserve them, right? I mean, that there isn't some compiler pass that just then inlines them and then we're back to square one.
I don't think so, but I don't think that there's any guarantees that we preserve them. I mean, might be a nice way to sidestep the problem, though.
I think there's also in the backend some quadratic issues if you have a really large number of records. Like if once you start going with more than 200 fields or something like that, and there are some passes that are currently known to be quadratic. Like I think record updates for once. So if you inline that, then you duplicate that and just end up generating very much code that can take quite some time to compile, even if you solve the type issue. So there's other corners and other problems I think that you would run into eventually if you fix this problem with very large records.
All right, I think we are running out of time. So thanks again, Edisco, for this great talk, and thanks everyone for this interesting discussion.
Thank you, guys.
So our next speaker would be Douglas Wilson, presenting improvements to GHC's parallel garbage collector.
Hello.
Hi.
There we go. Hi, everyone. I don't have a video, so let me just share my screen. All right, is that working? Yep, nice. Okay, hi, everyone. I'm Douglas Wilson. I'm a Haskell consultant with Well-Typed, and this is some work that I did earlier this year to make the garbage collector work better. There's no Haskell in this talk, unfortunately, but there's some. I try not to get into the C too much. So I did this summer 2021. It's in GHC 9.2. Most of the work's in Linux on AMD 64 architecture. So we're going to be talking about things that they're different on different platforms. So I'm a little bit less confident about how much better this is in. Yeah, it was the Southern Summer. Yeah, it was the Southern Summer. So what we're doing is changing the way the cross-thread synchronization works. And it in particular reduces the CPU times for Haskell programs. I'm going to show some measurements of the improvements, then talk about just what changed and some other experiments. So this is a chart of building the Cabal library with GHC. It's a really simple test to run when you're working on GHC because the dependencies are guaranteed to work. Now, the most interesting, well, I think instructions here. So this is the instructions as measured from Perth. You can see it's 7.5 times 10 to the 11 with the baseline. And then with my changes, which I call them no spin GC, it's pretty flat. So we've got cores on the x-axis. And then these are different measurements that have come out of the compiler. All of these measurements they're over like 6 samples. And they're all done on my laptop, which is a Zen 3 AMD, and with 8 cores, 16 gigabytes, hyper-threading on. And then I work everything in a 12-core CPU set. So where you see 16 here, this is approximately running with 16 capabilities on a 12-core machine. So you can see that instructions massively increases in the old version, and it stays pretty flat in the new version. And total CPU seconds shows approximately the same kind of shape. Total wall seconds is the stopwatch time. So it's much the same as the cores increase. The new version wins a little bit, but it's not dramatic. You might think, well, if it's not faster. But the thing is that CPU seconds is really measuring the energy cost. It's kind of almost the carbon footprint even. So this is really about making Haskell programs more efficient. And even if they're not faster by measuring it, they're using less resources, so we can do other things at the same time. I've also got here the max pause. So this is a little bit of a dubious statistic, looking at the maximum pause for a given run and then averaging it over 5 times. But you can see that it does marginally get better. It's about half what the old version is for these larger core counts. Yeah. So what's the change? It's essentially taking calls to shed yield out of the hot path. Shed yield, very briefly, is a Linux system call. It's implemented in kernel/shed/fair.c. And this is an excerpt from the man page telling us that the way that we were using it is not really how it's supposed to be used, and it's going to cause problems. Shed yield, the idea is that you you don't want to do anything right now, so you just tell the operating system to run something else for a little while. But in practice on multi-core machines, either you have something in the run queue, in which case when you call shared yield, you're forfeiting your time slice, and so you're effectively lowering your priority. Or if there's nothing else in that run queue on that core, then it's just a busy spin. And that's why we see those high CPU times, is because we've just got a lot of busy spinning going on. GHC itself invokes other processes like assemblers and linkers. So for that reason, the behavior we see in GHC is a little bit different to what we see in a more of a micro benchmark, where we're doing our best to keep the whole machine silent. So when the whole machine is silent, this is kind of the best case for shared yield. And it's why it's quite a difficult thing to measure. Why do we use shared yield? Well, there's various synchronization points in the garbage collector. So when we start garbage collecting, everything has to, maybe I can actually go here. So when we start a garbage collection, there's a synchronization point to make sure everyone's there. And then there's another synchronization point once the leader has finished doing its initialization. Then there's another synchronization point when everyone's finished. Then the GC leader does some cleanup, and there's another synchronization point, and everything can continue running in the mutator, doing things that matter. And at all of these synchronization points, prior to my change, we're doing a shared yield busy wait. So we say, are we ready to go yet? No, otherwise, okay, we'll yield. And so the change is we don't do that anymore, and we use mutexes and condition variables. Yeah, I got done that. So we need to be careful. Like, it's really tricky, the C code and the RTS. And so we want to make sure that we're not causing any problems, get all kinds of seg faults. So there's some fairly straightforward invariants that we can identify, and then they're maintained before the change, they're maintained after the change. We can tell because we put some assert statements and things, so it's going to blow up if anything we think should be the case isn't the case. And then we minimize broadcasting on condition variables. So we'd prefer to wake up one thread than to wake up all the threads that are waiting on a thing. That causes what's called thundering herd problems, where you have many threads starting up at the same time. There's 3 places. So there's the GC entry and the GC exit, and then there's also the work stealing loop. So that's where the GC threads are looking for more work to do. Yeah, so this is describing here, I went through this before, it's describing the invariants for the startup and the shutdown of the GC. And so these are the same, they haven't changed. It's just a different mechanism of doing this blocking. When it comes to work stealing, so what we do is we track the number of threads that are currently working in a global variable. And threads that aren't working are in this wait state, waiting for new work to arrive. And then when the number of threads running reaches 0, that's our stop condition. That's how we know to proceed to the exit of the GC. The tricky thing here is that there are many, many blocks made available for workers to work on during a GC, and we don't really want to we'd like to minimize the number of syscalls we make. So what we do is we just signal this condition variable so that a single thread wakes up, and we only do it when the number of running threads is less than all of them. So that's going to mean that most of the time all the threads are running and we're not going to signal. And when we do signal, we just signal one thread to wake up. And if there's more work and more threads waiting, then there's going to be another block soon, which is going to signal and wake up another thread to get going. So this is showing how much thread yield is being called on the baseline and in the no-spin GC version. So in the top row here, this is the number of times that must spin yield. So this is measured. This is one of the synchronization points. This is another synchronization point. You can see it's in the order of 10 to the 9. Notice the log scale here. So like 1 billion calls over the building of Cabal, and then a little bit less for this synchronization point, but again, loads. There's no orange line here because we don't do this anymore. I guess we could be measuring how many times we're waiting on the condition variable, but we're not. So that's why there's no orange line. Any work, here we are measuring how many times we wait on the condition variable. So you can see it's the order of 10,000, whereas before we were yielding 10 billion. These other 4 are spin locks that remain in the RTS. So this one, yeah, some various points. You can see this one's at 10,000. This one's at 1,000, but it's a lot less than these. So it's not clear how urgent removing these is. It probably would not be noticeable, but one might like to do it anyway. And yeah, next thing is, this is an experiment that I did running stress ng in the background while we're running these programs. Stress ng, it's a program just for stressing your CPU. So this is the invocation here. And this is telling it to run one instance on every core to just compute the Ackermann function and try to keep the CPU load of 40%. And then these dotted lines are what's happening in the when you've got this with background noise going. On this axis here, we have the few different programs. So this is build Cabal, which is the one that we've been looking at. And then Coins, Minimax, and Ray are all programs from the parallel suite of NoFib. And the really interesting thing is right here. So the CPU seconds for build Cabal is it's a different mode to these other ones. Whereas before, there's very, very little change when moving to the no-spin GC. But the background introduces this large change. Whereas we've already got a change here even without the background for building Cabal with GHC, and that's because of the assembler and the linkers that are running. So this is because GHC never, with assemblers and linkers anyway, it never runs on a quiet box. And then I've also got the total wall seconds here. You can see that gets pretty bad with something in the background. And then this is the average pause in generation 0. So this is the latency limit of your program. And you can see that even with a busy box, we're still maintaining good latencies here. And I mean, in this program, even it was degrading here, wasn't it? Next thing, what's next? There are some schedules calls remaining. It'd be nice to get rid of them completely. Benchmarking on other platforms. So quite important. I appreciate some help with this one, if anyone's got a box lying around. And there's an opportunity here to make Cabal and Stack install large sets of dependencies faster by allowing the individual packages to compile with multiple capabilities and some kind of cooperative sharing between there. Potentially something like a GNU job server. I have a draft patch that does that, but it doesn't look that great yet. And then here's some links. So the code for the presentation and all the experiments is available here at GitHub.org GHC bench slides. All of the graphs you've seen have been generated. Baseline it was the tip of 9.2 when I did it with all of my changes reverted, and then I unrevert. This no any work is with just the work stealing in place. That's not present on any of the graphs, just to make things simpler. And then this no spin GC is with the entry and exit of GC done as well, and also a single bug fix. Yeah, so thanks. That's what I've done. Anyone have any questions for that?
Yeah, thanks for the great talk, Douglas. And I'm now going to bring one question to the stage. And I'm also going to invite Andres to the stage. So the question is for Andres, and he asks, is compiling Cabal the only workload that you have looked at? I saw a comment by Simon Marlowe being worried about the impact of these changes on some no-fib benchmarks.
No, it's not the only workload I've looked at. It is the main one. The no-fib changes, I posted some data where I had mixed up my core counts. So I had some numbers that look pretty bad. The no-fib mostly doesn't change very much. It's not so easy to see on this graph, but these are 3 of the parallel programs. But the building Cabal is the only large workload I've tested it with.
So we currently can't see what your screen anymore because the question is on the screen.
Oh.
Because you referenced the graph that was not visible anymore.
Oh, can you see it now?
Yes.
How about now?
Yeah. So I'm not. I haven't really seen any regressions in NoFib from this.
For compile time or for runtime?
Only for runtime. I haven't looked at compile time.
Okay. I just saw the comment on the ticket, and the ticket is still open. So maybe, like as a GHC dev, right, we always like to see if there was a confusion and you have new data on NoFib where nothing much changes, just be explicit about that.
Yeah, I've been kind of focusing on getting the talk ready, but the I'll post some more data on there. Yeah.
Yeah, and those are some really great changes. So can't be overstated, I think. Good to see that they hold up. If you say no, I don't think we would expect NoFib to change very much. So because this is all about GC performance, and there's very few GC heavy benchmarks.
Yeah,
and I'm not sure if there are parallel GC heavy benchmarks to NoFib really.
The parallel suite is, I think, supposed to run in parallel, but even that it uses a lot of Sparks, and I'm not. Yeah, I don't quite understand how this. There's some complication there because they're treated differently in the garbage collector, I think.
Yeah, and I think they're also not very GC heavy.
No, they're not.
If you improve the GC performance by 10%, which is huge for some workloads, and those have a productivity of 80%, right? Then you get like 2%. So still good, but yeah, that's all about my question so far.
Yeah, thank you, Andrews. If people have more questions, please ask it in the QA tab or raise your hand. So one question I have is, so the whole area of garbage collection has been like intensively started for like decades.
Mm-hmm.
And then why do you see there are still optimization opportunities for like a specific implementation like GHC?
I'm sorry, can you repeat the question? I don't know. I didn't hear the last sentence.
The question is, so the whole area on garbage collection has been like intensively started for decades. And why there are still optimization opportunities in a real world implementation like GHC?
Well, I don't think people look at it very much. So the things that I changed, they were put in place about 15 years ago, I think. I think that's right. And things were a bit different then. Multi-core was less of a thing, and operating systems were a bit less sophisticated. And the glibc implementation of the mutex and condition variable primitives was also less sophisticated. And we have the futex system called it. I mean, it has been around forever. I don't know exactly how long it's been around. So this is really not a leap forward in how to implement garbage collectors, or from a theoretical or algorithmic point of view. It's just an implementation improvement, really. And I think there are things remaining to be done as well that I think that not a lot of effort gets put into improving them.
So I think we need like more manpower in looking at the garbage collection, and maybe there are still like further optimization opportunities.
I think that there are further optimization opportunities that manpower could help. I mean, I don't know if it's the best place to put that manpower, but yeah, like for example, I think that we can do a lot better prefetching when we're scavenging and evacuating.
And address in the chat. Yeah. Would you like to repeat the comment, or I can read it for you?
I can do it. I will paraphrase it. So I think in general, like GHC attracts very contributors that are focused on the type system and the high-level features. And so that means there are not a lot of people, few people that contribute to the runtime system and to the code generation. And there has been a lot of research in LLVM, in the Go runtime and things like that, where I think you can basically pick a paper and look at GHC and say, I can do that there as well. And I've done, like Lucas did some things there, right? Like I've did similar things in the code generation side. Ben Gimari, I don't think he's here, but he did a garbage collector. And like I think there's lots of things that are similar nature that could be done. And if someone is interested, like for research or like personal interest, it's definitely worth having a look there. And
yeah.
Cool. I guess that's all for all the questions. So thank you again, Douglas, for this great talk.
Thank you.
Yeah, so now we are done with our first session. So thanks everyone for joining this session. In around 40 minutes, we will have our keynote given by Martin Agren, and we are going to take a break now. So for people who are on AirMeet and would like to stay for more discussion, please feel free to hang out in the lounge. When the session resumes, you will receive a notification from AirMeet. So thanks everyone, and I will see you in the next session. Okay, I think we can get started. So welcome everyone to the keynote of HIW. It is my pleasure to introduce our invited speaker, Martin Agren. Martin leads a team of quantitative analysts and developers at Standard Chartered Bank since 2008. Previously, Martin worked in related roles at Lehman Brothers, Goldman Sachs, and Credit Suisse. He graduated from London Business School with an MBA in 1995. Martin divided his free time between his children, embedded programming, modular synthesis, and photography and reading history. Today, Martin is going to tell us about Haskell reinterpreted, large-scale real-world experience with the Mu compiler in financial markets. And a final remark, we are going to have questions at the end of this talk. For people on AirMeet, please put questions in the QA tab during the talk, and we are going to go over them at the end. Or you may raise your hand at the end, and we will bring you to the stage so you can ask the questions. With that, please take it away, Martin.
Okay, hello, and thank you for inviting me to speak at this forum. My name is Martin Agren, as you said, and I work at Standard Chartered Bank in Singapore. I should mention that I'm speaking here in my own personal capacity and not on behalf of my employer. So in this talk, I'll speak very little about the commercial environment that we work in, and I will focus specifically on the language topic. I'm going to give you a brief overview before going into some detail on why we built our own compiler. Then we'll contrast this with the real Haskell. We'll talk a bit about the compiler implementation and our libraries. Then we cover some code statistics to see the time evolution, distribution of module sizes, and language extensions. And then we finish off with some current research and potential future development for convergence. And then, as Ning Ning said, Q&A will follow at the end. So just briefly on the business context. So our work here goes under the rubric of quantitative analytics. This is a function that large banks maintain in order to have a competitive presence in securities markets. We're based in the front office, so that we have frequent and direct interaction with trading and structuring functions. We are heavy on financial mathematics, meaning stochastic calculus and measure theory. We are convention laden. We have millions of details of market conventions to keep track of. We do a lot of high performance compute, lots of linear algebra, and lots of Monte Carlo simulation. It's an environment, which is fairly fast-paced, fast-changing priorities, and demand for quick turnarounds. So our team, basically the modeling team, is organized with the product and the model development mirroring the corresponding business lines. And then we have resources for core, applications development, continuous integration, project management, and model risk shared across the business lines. So I'm going to start here with a kind of review of the timeline, basically how I came into Haskell. So a long time ago, like 25 years ago, I started working in the financial markets industry. At that time, the use of spreadsheets was commonplace and development required good integration. This meant that we were writing libraries that could be called as add-in functions from, for example, Lotus 123 or Excel. Institutions could go about this in a manner and style of either I don't care, anything goes, or slightly more principled, like don't mutate anything upstream. So I was lucky enough ending up working for one of the latters. So we had notions of purity and referential transparency, but we didn't use that terminology. We weren't even familiar with the concept. But that's how we program. After that, I guess around 2004, I moved to an institution with almost no spreadsheets, and all the higher level code was written in in-house dynamically checked language. And by 2006, I'd been around in a few different financial institutions, and I wanted to pull together some of the lessons that I had learned. It may not be everybody's lesson, but this was kind of my take on it. And those lessons in summary would be that having a high-level scripting language with an interactive top level is a good thing. Static typing is necessary for development at scale. Purity is required to play well with spreadsheets. And then I was wondering if it would be possible to get some control over effects, even though I didn't really know what that would mean. Now, the answer, of course, is obvious to everybody here in this audience, and that is Haskell. So that's basically how this whole thing started. So from around 2007, I started leading teams that had Haskell, not perhaps centrally in what they were doing, but at least it was an important element. So from 2007 to 2009, we mostly got away with using Haskell as a specification language and for implementing tools. At one of the banks, we were expressly not allowed to have Haskell binaries in production, but we could use it in the development environment. But from 2008, basically since I joined StanChart, we gradually got more adventurous and started using Haskell for a few production packages, as well as widespread use in the development environment. Then by 2009, we had a high demand to deliver scripting capabilities for end users. And our response was to develop a dialect of Haskell that would mesh well with the rest of our ecosystem. And therefore, we made Mu. And basically, since then, there's been no looking back. So why would we build our own compiler? Well, as I mentioned on the previous slide, Haskell was kind of well supported and motivated in the team. That choice wasn't contested, but we had our own ecosystem, and we had an ecosystem and a runtime that already supported code mobility. So what I mean by code mobility? Well, the idea is that you can construct an arbitrary term here, evaluate it in place, or send it over there for evaluation now or later. Over there, that might be a different machine, different architecture, different OS, even different word sizes. And we had built all that functionality during the preceding years, and it formed the basis for everything we were doing or intending to do with respect to distributed compute. So after consulting with people closer to GHC, we concluded that we didn't have the resources to build a custom GHC backend to target our runtime. So we struck a compromise and decided to implement a minimum viable subset of Haskell 98, and then try to reuse our existing backend as is. So from the start, this was a very speculative development. It was intentionally, high high probability that it would fail, that we would abandon it, but we gave it a try. And it was done with very few resources. But it turns out, of course, that Lennart can write a nearly complete Haskell compiler in about 2 weeks. So there we go. So, okay, so what is Mu? Well, it's a whole program compiler for Haskell. It compiles to bytecode with a small runtime interpreter, hence the title of this talk. It has lazy semantics, but a strict runtime, and it has no FFI. So all functions from C++ are called natively. All Mu functions have a C++ type of object I function. C++ can apply any object I function natively, and hence we get seamless calling across the language boundary. So now we're going to go into some of the differences between regular Haskell and Mu. So you can't really write idiomatic Haskell if you have strictness all the way to the top. In the lazy language, of course, programmers are accustomed to writing things like from maybe, error, something, expression. But of course, in the strict language, this will fail every time because the arguments are evaluated before the call to from maybe. So the error is always thrown. But Mu implements some tricks to ensure that such code can be treated as if it was lazy. For instance, the definition of from maybe is annotated with a by name pragma, which means that it's always inlined, and that is, it's treated like a syntax macro. Additionally, the implementation takes care to delay the first argument explicitly. And this means, of course, that when it's inlined, you don't get the same problem with argument evaluation. The desirable consequence is that most of the time, we don't need to think about evaluation order when writing this code. The Mu compiler also uses the liberties of lazy semantics to do some aggressive code motion for performance optimization. For example, we're lifting let clauses inwards to near their usage sites. We're inlining a let clause if it only has a single use. And we can identify common sub-expressions and lifting them into let binding to be evaluated once and then shared. In terms of the semantics, the worst thing that can happen, for example, errors, is that they happen in a different order at runtime or not at all compared to strict implementation. And on top of that, having a strict runtime gives us really good stack traces. So the example here shows the typical head of empty list error that is common in Haskell programs and less common in Mu. And they're notoriously difficult to locate when it happens in Haskell because of lazy evaluation at runtime. The Mu exception shows the full stack trace from the definition on line 17 back through call sites in F, lines 13 and 14, and to the usage of F from main in line 8. But there are some consequences of not having real laziness. So as lazy programmers, we're used to creating compiler-like pipelines as the architecture for solving many problems. For instance, ingesting data from a concrete file format might involve lexing, an initial parse, and then a transformation. So we have the functions lex from string to list of token, parse takes a list of token and gives us either an error or the foreign AST, and then we transform the foreign AST to the local AST. So this is natural. Uses laziness to unroll the lex's resulting token stream on demand as the parser consumes it. But in a language with a strict runtime, the entire original string must be consumed and converted to a list of tokens before the parser gets to see anything. On a large data set, this can lead to some unfortunately large memory usage. So in a very few places, we rewrote our lex and parser combinators to have an explicit lazy channel between them, like you see in the continuation form here. The lexer, instead of producing a list of tokens, produces a single token at a time, paired with a continuation that encodes the suspended reminder of the lexing process. where the parser combinators within the parse function would previously have peeled items from the front of the token stream, just as list operations, now they can peel only one item from the lex return or invoke the continuation on the residual input stream to get another lex return value. So it turned out that making these very few changes to the lex and parser combinators, it was sufficient for us to allow us to port a lot of Haskell code based on them, with no changes in the actual parsers that use the combinators, and then retain the lazy memory behavior. We also have explicit ML-style laziness, which we use. For example, we had a pretty printing library that we got simply by copy-pasting the Haskell library into Mu, and it seemed to just work for years. Then we noticed bad performance, and we evolved some kind of folklore advice to only use it for small things. Then we came across one use case with a small XML file, a small but deep XML file. And it turned out the original Haskell code crucially depends on laziness for performance in this case. And in Mu, under strict runtime, this became accidentally exponential. But the fix was easy and consisted of just adding explicit laziness to a couple of fields in the docs data type. Another difference between Haskell and Mu is that strings as a list of characters, it's kind of a misfeature of Haskell. It's great for teaching recursion over simple data types, but little else. In Mu, we don't have a cart at all. We don't have it as a data type, only string. And the string type is therefore abstract. You can only use it via the provided API. For example, isUpper applies to whole string, not an individual car like in Haskell. And you can see here kind of the various cases laid out for car. And internally, strings are implemented as C++ std strings with UTF-8 semantics. This implementation works quite nicely because the representation is compact, like byte string, but indexing operations can be expressed in terms of the abstract UTF-8 character position rather than the byte position. And in general, the complexity of string operations is no worse than they were with lists of car, and in many cases, rather better. Okay, so recursion in Mu is a language extension, and you have to switch it on with the pragma. This is kind of a happy accident with the Mu runtime implementation. Before Mu, there was a library written largely in C++, and all Mu code needs to interact with it. Mu functions are essentially evaluated by a bytecode interpreter, which takes up a single stack slot on the C++ stack. And C++ can call Mu by invoking the interpreter, and Mu can call C++ directly. But this means that any call from Mu to Mu is treated just like another call to C++ function, meaning a frame is added to the stack. We don't have any tail call optimization, so all recursion ends up on the C++ stack, and this is relatively small. So recursion tends to work fine for small examples, but it will blow out the stack as soon as you try something reasonably large. Our solution then is to provide all the usual recursion combinators natively as primitives written in C++. So map, fold, unfold, scan, until, loop, etc., all written in C++. And because these are higher order, you just pass a Mu function to C++ combinator, and only 2 stack frames are used. There's actually a happy benefit of placing this barrier, that is a compilation error, to the casual use of recursion. One, it nudges developers into thinking carefully about the nature of the recursion to choose the right pattern. And it also means that other developers who later need to maintain the code find it more readable. And there's no need to decode Byzantine recursive implementations only to find out their standard pattern after all. Okay, so Mu, having its own standalone compiler, doesn't get any of the GHC goodies for free. So over time, we have implemented several extensions, most notably functional dependencies, type families, and data kinds. these aren't exact matches of what GHC offers. For example, for type families, mu only has closed type families. For data kinds, we don't promote data types. Instead, data kinds are open and separate from normal kinds. And some extensions, like CPP and template Haskell, were never implemented. These would interact really weirdly with code mobility, because suddenly you would have to know what runs on what machine. So we're not doing those. And since mu is targeting our pre-existing runtime, it also limits somewhat what we can do. So for example, our runtime only supports rank 1 polymorphism. This rules out higher rank types and existentials. The latter in turn rules out GADTs. And we have no type classes in our runtime. Definitions are specialized starting at main, which is another reason why we need the full program compiler. So if we look at kind of the extensions that we have, basically our favorite extensions apart from those that we can't have, on the Haskell side, we have 1,794 Haskell modules. And the top extension is that in this category is derived data typable. And that's only here because we're still on GHC 7.8. When we upgrade, that's obviously going to go. And then we have record wildcards, which I can take a minor credit for, as Lennart introduced this in response to my complaints trying to use Haskell in a real-world setting back in 2006. And that list of Haskell extensions kind of tapers off fairly evenly, and there's nothing kind of that stands out, I think. On the mu side, you can see this massive popularity of record wildcards used in 7,975 modules. Multi-param type classes rank second, and this is really because we use it in defining attributes for our financial products, and we have many of them. So that's why it comes up that high on the list. Recursion is also relatively high on the list, but at 975, you can see that's only used in 4% of our mu modules. We have 26,000 of them. So clearly, you can write a lot of Haskell without recursion, explicit recursion. So mu is a whole program optimizing compiler. So the entire source of all libraries are used on each compilation. So what are the upsides from this? Well, we have some optimization opportunities. There's no need for runtime dictionaries for class instances, and all function calls are monomorphized at the usage site. But to be fair, it's not just optimization. We have to do this monomorphization because we don't have rank 2 types. We also get module synchronization. You can never accidentally link against an old version of a dependency simply because we don't have linkage. On the downsides, well, compile time can be rather long. A typical main module can have more than 2,000 transitive dependencies. Some of the mitigations we have there is, with some restrictions on exported types, it's possible to load modules dynamically at runtime. And you can also run a compilation server that keeps an in-memory cache of modules already parsed and type-checked to share across multiple compiler invocations. Another feature that we have above Haskell, I would say, is that every runtime value can be serialized. So that includes functions. So you can save any partially applied computation and restart it on another machine, even across Windows, Linux, and network boundaries. This enables process-based parallelism across architectures. So ParMap or parallel map is one of our most used facilities. We perform hundreds of thousands of core hours of parallel cloud compute every day of the week. And how do we implement this? Well, so primitive values are just themselves. C++ data constructors have unique IDs plus their internal fields. And we have a versioning scheme to ensure that any old version of a value can be read with a deserializer for a new version defaulting any new fields. C++ runtime functions have stable and unique IDs. And mu functions are a data value of object I function containing the bytecode. And then finally, mu algebraic data types become either enumerations or records in this environment. So this thing that I called code mobility, I consider really the most valuable aspect of the new environment. You can author fresh code from your desktop anywhere in the world and immediately run it distributed on off-premise cloud infrastructure, harnessing tens of thousands of compute cores without any deployment. Another feature that we have that you don't see in Haskell is this notion of safe I/O. So we have safe I/O and I/O. Why two? Well, this was initially motivated by the need to get external market data into spreadsheets. Forcibly recalculating, for example, a spreadsheet cell that performs a safe I/O term could bring in fresh market data from the outside world. The main idea here is to keep things where effects are unobservable from the perspective of the caller in safe I/O. So data might be different each time, but the outside world didn't change except for getting slightly warmer. So I/O is split into effectful and non-effectful parts, essentially input and output. So safe I/O, you could think of that as input and I/O as output or writing or mutating things. We have monad lifting from safe I/O to I/O, of course. We have monad dropping, so we can perform a safe I/O and get a value. And it's only safe I/O that can be both lifted and dropped. This has also allowed us to ban the use of unsafe perform I/O completely from the code base. So anytime a module wants to use unsafe I/O perform I/O, it has to actually register that with a compiler enforced authorization. Another one is how we deal with data collections. So mu lists are actually arrays at runtime. This works reasonably well for small to moderate data sets, but lists are not our preferred collection type. A standard go-to type for collections are relations. Relations are abstract first-class objects implemented in C++, and they have pure operations on relations. You can think of relations as a tabular data structure with named columns, named and typed columns, and rows of data in the body. We don't have any material ordering of either columns or rows, and columns are only addressable by name. We have an efficient implementation of the relational operators with well-defined algebraic properties, and this makes it easy to reason about relational expressions and helps refactoring. We regularly work with relations containing millions of rows and hundreds of columns. We also have a typed version of the algebra to which we are gradually migrating. This one has a somewhat higher initial development effort, but offers savings in maintenance and reuse. So the last part here in terms of our libraries, for GUI projects, we developed a property model-based toolkit called Widget. The main feature here is that UI elements are essentially mutable properties with the user interface, and you can construct a GUI simply by building a property graph, some of them with UI, some of them without. And coupled with abstract layout, it becomes possible to write applications that are independent on how they're ultimately presented to the end user. We currently have two backends to this, one using F#.net and WPF to present what's essentially a thick Windows application to the user on a desktop. And the other one is a cross-platform service that can render applications as HTML in a web browser. So on this slide, you see screenshots of a small application using the two backends. On the left, the desktop application with a WPF front end. And on the right, we have the web browser version. And they're essentially identical, apart from the superficial difference in the built-in widgets. And to show how compact this is, if we look at the code, so this page is the complete code for that application. And You can see how small that is compared to what it might have been if we had used any of the competing toolkits that have bindings to Haskell, for example, GTK or WX. And with this, we get the cross-platform browser presence for free, working both on Windows and Linux. So now let's talk about the code base overall, showing some code statistics. So the project started back in 2008 with C++ and Haskell from the get-go. And you can see that C++ and Haskell has grown in roughly constant proportions to each other throughout time. When we started this project, I projected that we would need about 1 million lines of code for a complete system, 1 million lines of C++. We haven't quite yet hit 2 million, so I think my estimate wasn't completely off the mark, and I didn't know I was going to be here for 13 years either. And in this count, I have not included the about 2 million lines of auto-generated API glue that comes out in C++, Java, and C# that is just part of our build process. That's code that is not touched by humans and code that's just thrown away after each build. Mu development started, of course, as soon as the compiler became available in early 2010. And you can see the Mu code taking off. The Mu code outnumbered Haskell code within 1 year. So the crossover there is at the end of 2010. And after 4 years of Mu development, we had Mu surpassing C++ in end of 2013. And basically since then, the Mu code base has been growing at about 500,000 lines a year. And I think when we look at this graph, we should also remember that we observe basically a factor 5 to 10 in the line count ratio between C++ and Mu. So you could either multiply the Mu line count here by 5 to get the kind of corresponding functionality that is actually living in Mu compared to C++. So I would count that as, the Mu code is worth 25 million lines of C++. Okay, the next slide here, we are showing some statistics on Git commits and contributors. So I can see on the right side, the number of active committers continues to grow and has now surpassed 100. So we have over 100 people actively developing on the repo, which also, of course, implies that our team has been growing and continues to grow. You might wonder why there's a dip in the number of commits per month over time, kind of following 2014. Probably a couple of factors there. One is that we changed from fast forward only PRs in the integration system to be able to rebase commits already pushed. So devs are now more likely to rewrite their commits when a test fails, rather than adding new commits on top. And then also as the project is maturing, individual commits have become beefier. If you go back and look at the code trajectory on the previous page, you can see that the line count rate hasn't really been abating, at least not materially over the same time period. And then the next slide, I'm showing the distribution of module sizes. So we have over 26,000 Mu modules. The largest module is 74,000 lines of code, but that one is generated. Note also here that the chart is truncated on the right at 1,800 lines. So the largest modules are really far out on the right here. The largest handwritten module is just under 6,000 lines. And then we have lots of small modules with the mean length being around 200 lines and the mode even smaller at 25 lines. Again, note that the y-axis here is in log scale. And we have modules as small as 4 lines of code. They tend to be just re-exports of existing modules, kind of just pushing them under new names. Okay, so with all that Mu code, what are we doing to secure its future? okay, well, we for a long time we've been considering the possibility of some convergence with GHC, at least for the front end. So this year we started a kind of a researchy project to establish both a feasibility and kind of a course roadmap for what this would look like. So the aim now is to use GHC to compile Mu to core, and then to translate core into the current Mu compiler's internal representation, and then use the rest of the current pipeline and runtime. So we have to have some inversion of control in the source driver. So in GHC, you have module resolutions, module name resolution into file names, which are then loaded from disk. In Mu, an import is either the typed interface of a C++ add-in or code from disk or service. So this we can get around simply by using a lower level GHC functions instead of the top level driver. But some GHC assumptions need to be changed. For example, string is not defined as a list of characters. So this will require patching GHC itself. And then there's some feature parity things, like we'll probably want to patch recursion pragma into GHC to retain, the discouragement, continue to discourage people from using explicit recursion. And for other things like data kinds, it would probably make sense to just migrate the Mu code base to what GHC provides. And then finally, as I said, the team is growing. From time to time, we have job postings. And if you're interested in applying, this slide shows you how to do it. You can go to this link and do the search as described. If you just search for Haskell, you will find jobs in other teams because we're not the only Haskellers in the bank. But if you follow the search criteria, you should find my group. And I would thank you for your interest on that. And over to Q&A.
Awesome. Thanks for the great talk, Martin. Let's give Martin a round of applause.
Thank you.
So we already have a number of questions lined up, and let me go through some of them. The first question is from Andrews. Andrews, do you want to be on the stage? Okay, could you repeat this question for our YouTube audience?
Yes. So you were talking about the recursion pragma, and you were mentioning that the that Mu supports these common combinators directly as C++ functions, but these are all combinators for lists or either or maybe or other data types. So what about user-defined data types? Version of a user-defined data types.
Yeah, we don't support that.
You don't write your own data types?
We do write our own data types. We don't write recursive data types.
I see. Okay.
Yeah.
Okay.
Yeah, we have plenty of our own data types. Of course, we're swimming in them, but we avoid doing recursive data types. When we do things that require that, we tend to do that in native Haskell and then provide that as a library that we integrate through the FFI that I say we don't have. We can write Haskell modules that become accessible in Mu. Right?
Mm-hmm.
So a good example of that would be we have the contract combinators kind of following in the same style as Simon's financial combinators paper. And actually what we've done is we implemented all of that in Haskell, and then we kind of reflect that over into the corresponding C++ constructors for all of those combinators, and then use that from Mu.
Okay, thank you.
Cool, thank you for that question, Andrews. So we have a raised hand from Philip. Philip, would you be?
Hold on. Right, what do I need to do? You can hear me. Great.
Yeah, you're very well. Hi, Philip.
Yeah, so thanks for the nice talk. This is sort of a high-level question. So I go around telling people, functional languages are widely used in finance, and that's because people need to write stuff quickly, but they need to know that it's reliable.
Yes.
So is that a fair thing for me to say, or should I be saying something else about why people are using functional languages in finance?
It's absolutely fair. So one of the things, I guess, we're not in the, how to say, safety critical place where people can get hurt or lose their lives, right? But we're in a safety critical place where you can easily drop large amounts of money very, very quickly when something goes wrong. And being in kind of an environment where most of what we write is purely functional, and it's sort of immune to refactoring, reordering, and so on, and you can actually understand what's going on. That's a great comfort for everybody who writes code, and we don't need to lose much sleep over things like that. So I'd say yes, that aspect of having something that is tractable and have kind of nice math semantics is really, really key for us. Another aspect of it is that we provide our environment in the end user space as well, what we call end user computing. And that means that we have people who are non-programmers who write often business critical functions, at least that they use for analysis or desk level decisions themselves. And we strongly believe that having them use a pure language leaves much less room for expensive mistakes than if they were in an imperative environment.
Right, that all aligns with the sort of stuff I say. I always feel a bit hand wavy when I say this sort of thing, because I can say like 7 different banks use Haskell, and there are other ones that use other functional languages. But I don't really feel like I have much heft. So I guess one thing I could say is you guys have 5 million lines written in Mu. That's important.
Yes.
Are there any other statistics like that I should be waving around at people so I'm less hand wavy?
So I haven't really followed, recently what's going on at our competitors, but I know at least 2 other major institutions where Haskell or other functional language play a key role. And then obviously there are some funds that do it as well. But I think we're probably one of the larger.
Right. Well, thanks for a great talk. That was very interesting.
Oh, thank you so much. I think you're on mute, Ning Ning.
Sorry. Yeah, sorry. So yeah, thank you for the question, Philip. And I have already politely removed you from the stage. So our next question would be from Andrew Gundry. And Adam, would you be on like to be on the stage? And do you mind repeating the question for our YouTube audience?
Yes, I think my question's probably been answered already, which was that I was wondering whether you had support for polymorphic recursion, given that you're implementing classes with monomorphization rather than dictionary parsing. But I think you mentioned that you don't really use recursive data types at all.
Exactly.
Presumably, polymorphic recursion is also not really available. Does that impact on the kind of code you write and the kind of code you can reuse?
As I said, in practice, there's only one library I can think of, which we ended up writing, in Haskell, and then having, enough combinators exported that we could kind of manipulate those data structures from C++ and then from Mu, and that was basically the contract data type for financial contracts. That's the only example I can think of. And I guess the answer there is that yes, given enough motivation, we could work around it by simply doing that in Haskell instead. I haven't come across that type of discussion in any other context. I would say in what we do, the need doesn't come up that often.
Thank you.
Thanks.
Great, thank you for your question, Adam. Our next question is from Andrew, and then he asks, what language was the initial Mu compiler written in, and is it currently self-hosted?
Okay, so yeah, I can answer that. That's easy. So the initial, and it's still the same, Mu compiler, of course, it's been evolving over the years. But yeah, it's all written in Haskell, and it's not self-hosted.
Well, that answers that. Thanks.
Great, thank you, Andrews. And Anisco, would you mind being on the stage? And the question from Anisco is, you can repeat it?
Sure. So you mentioned save IO and perform save for save IO going to save IO 8 going to A. Did I understand you correctly that you said that reading data from the world is an example of save IO?
Yes, reading data from the world. Okay, but it's not reading more data from the external world. It's reading data, and then, so put it this way. In most, take an example, for example, reading a file. So that's in Safe IO. That reads the file and gives you the content. And if you do that again, you get the same content. It's not that you get more data the second time. Right?
So for example, like reading market data would not be an example. Is that right?
No. So reading market data, given that when you run perform, let's say in a spreadsheet, you do it as an explicit action. So it's the end user can control when that happens, right? It happens only if the user forcibly refreshes that cell, and that's because they want to have a fresh version of the data. So imagine that you have a call that is going to give you the current spot value of $yen FX, right? And it's coming back at 100.4, and you can keep hitting that cell over and over and probably get 100.4 again, unless it has moved. Well, it's going to move all the time. Next time it's going to come back at 100.5, right? But it's a user action to decide. The user expects it to move because it's live data, right? But it will only move when the user forces the perform.
I see. So because it feels like reading in a file and it doesn't change, like treating that as being morally pure makes total sense to me. But reading a market value and treating it as morally pure seems unsound to me.
I guess
that makes it not a pure language anymore, right? I have pure things that look like pure values but aren't pure values.
Okay, but reading the file and reading it again is also not a pure value if someone wrote the file in between, right?
Right. I mean, that's like a Nix, for example, right? You would like have a hash in there saying like reading with this particular context. Like there's ways around that, right? You expect it to be the same.
Okay, so here we don't expect it to be the same, right? If we expected it to be the same, we have another facility which we call the kind of the reference data service, and that's more in line with what you're asking. So things that we don't expect to move are threaded through a value that you can kind of read from purely. It's like it's kind of a long lazy read, and that's used for things like static data describing market instruments, calendars, holidays, and such, right? And that's not expected to change, and therefore, wherever you reference that in your program, it's just getting a pure value. It's like getting a constant value. Of course, from today to tomorrow, if there are corrections in that data, it will be different, but we don't consider it to be impure just because of that, right? When it comes to safe IO, when we read from the outside world, we have to be prepared for the possibility that it will change, right? But it's a benign change. It's not like we are launching missiles or deleting files or sending out payments. We can safely redo a safe IO as many times as we want without kind of consequence to the external world.
But for example, like 2 times perform X, is that the same as perform X plus perform X?
No.
but then we don't have you said we have a pure language, mathematical properties, but even like the most basic properties don't hold then, right?
Well, I mean, so safe IO perform. Okay, so safe IO perform is
hello.
Sorry, safe IO perform is in a monad in the safe IO monad in mu. So you would have to use, you have to do it in a do block, and you have to actually lift it to IO if you're going to use it. The only place where we allow safe IO perform kind of in the way that you describe it is in Excel itself. So when you write mu code, you can't just run safe IO perform as a function, right? You have to do it in a do block.
I see. There are some like external to the type system, some external checks that limit where you can use this.
Yes. Yeah, it's actually not even exported into the. No. It's exported into the mu namespace, but it's of course it's in the safe IO monad there. So you have to do it. You have to lift it to IO and then run it.
But the signature was perform IO of type save IO A to A, right? So I could call that anywhere in principle, as far as the types are concerned.
Okay, that might be a typo here. Let me see.
Monad dropping.
Yeah, I think this is only in Excel where you can do this.
I see.
I would have to go back and actually check the documentation.
I see. Okay. Thank you.
Or it simply is that safe IO perform isn't even accessible from mu.
I see. Okay, thanks.
I think we got a follow-up question from Matthias.
Okay, this is a question about serialization, I guess. Not necessarily safe IO, but could be also. I would say the answer to this is no, because the values that you serialize in our platform are not kind of the primitive unboxed values. I mean, everything will be in some form of container with type annotations at the top. So my answer here would be no.
Does that answer your question, Matthias? We cannot hear you, so I guess the answer would be yes. So thank you for the question. Our next question is from Andrews. And Andrews, can you be on the stage?
Yes. So my question was about serialization, and in the slides you had primitive values adjust themselves when serialized, but you also mentioned that this works across different platforms and bit widths, and I assume maybe even NDNS. So I just maybe that's a different notion of primitive than what I think of, but I think of it in the GHC way where we have inserted hash. Oh.
Okay. Yeah, I can answer that. So we, when we say that the primitive values are just themselves, so this is true with respect to one choice of a C++ or C level representation in memory. And basically when we wrote the wire protocol for the serializers, we just picked whatever was the closest to what was native to the compiler we were using at the time, and said, well, this is the wire format for this, and we picked, for example, all the word lengths for integers and so on, and the NDNS based on the platform we were, and said this is now forever the wire format. And then of course the serializers on other platforms then make the necessary adjustments to stick to that protocol.
Does that not cause issues when you have things like overflow, and so the computation might give a different result on different width platforms?
So yes, there were some restrictions with respect to the range of integers, but I think what we did was we defined ints originally to simply be 32-bit ints. 32-bit, yeah, 32-bit ints, and that means that when we go to 64-bit platforms, we have this extra space. We have runtime checks both ways for overflow.
Okay. So I guess in a sense you defined your primitive int to always fit into the native int of all the machines you run on.
Yeah, exactly.
Yeah. Thanks.
Thanks.
Great, thanks for your question, Andrews. I see you has several questions. Could you be on the stage?
Hello, Gigi.
Hello, nice to meet you. Is technical optimization supported by the recursion programmer?
Yeah, no. Actually, if we had that, then we would probably not even have the recursion pragma, apart from kind of programming style reasons. So yeah, we don't have tail calls in the runtime, so we can't really do it.
Okay, thank you.
Thanks.
Next. Okay. Okay, next question is mine. Does the HTML backend render only on the server side, no JavaScript?
Oh, I don't know the complete details of that. There will be other people here on the yeah, there are some other people here that would know, but I actually don't have the answer. I think there might be some JavaScript in there, and I know we've been working on it, and we have work underway to improve the HTML backend to give a better user experience. And of course, in that place, I would think JavaScript or TypeScript or something like that will serve a key role, but that work is just starting.
Okay, thank you.
Thank you.
Thank you very much.
Okay, thank you for your question, Yuji.
Yeah.
I will mark this as answered.
Yes, thank you.
So, I'm turning. Okay, so just to answer Yuji's question, so the way it works is that the logic runs on the server side, and then there's this very small JavaScript shim in the browser, which just takes small fragments over the wire that update the UI in response to events. So there is JavaScript, but it's only used to change the state of the DOM, basically.
Cool. Thank you for the further clarification.
Thanks, Gergo.
Sure.
It seems we are running out of questions, and we have also reached the time limit. Yeah, so thank you again, Martin, for this great talk. I really enjoyed it, and I really appreciate you taking the time sharing the new experience with us. Yeah, you can see a lot of applause from the audience.
Well, thank you so much, and I should thank my team who helped us put all of this together, both the code base and obviously the material for these slides. Thank you.
Yeah, cool. Thank you, and thank you everyone for joining us this session. So for now, we are going to take a break, and our next session will resume in 30 minutes. So thank you, and thank you again, Martin.
Thank you. Bye-bye.
All right. Welcome back to the Haskell Implementers Workshop. My name is Andres Lö. I'm the session chair for this session. In this session, we're going to have 3 regular talks, and then at the end, there will be the GHC update by Simon Peyton Jones. And as a bit of advance warning, that will probably run over into the break. So we're probably going to use most of the break time for that as well, because we expect this to be interactive with lots of questions. The first speaker is Richard Eisenberg, and he's going to talk about generalization is hard, but somebody's got to do it. Richard.
Thanks for that introduction. And thanks for having me here at Haskell Implementers Workshop. This is a talk about generalization in GHC. So what do I mean by that? This is really about how do we infer the type of a definition that doesn't have a type signature, right? If I say id x equals x, well, that of course can operate on int or on bool. And so how do we determine that we can do that? And so this talk is all about that because it turned out to be much more subtle than we might think. So the code for the talk is available here. This file that we're looking at, you can download it if you want to sort of follow along. You don't have to, though. We'll be sort of bouncing back and forth within the file during the talk. Let's see. So here is how generalization is done. We have, this is all, by the way, extracted from mostly this decide quantification function within GHC. We're not going to be looking at GHC source code today, though. But in case you want to look, you can go there. And what we're going to do is really talk about these 7 steps, or really steps 3 through 7. So this both is the recipe for how we do inference / generalization, and also the outline for the talk. The idea here is that when we first see a function, something like id x equals x, we're going to generate constraints. And that gives us the first few steps, or rather that gives us the sort of the framework of what the relationship is among the different types. So for example, if I have something like it, or wouldn't be it, fxy equals x comma y, then GHC will say that, oh, x has type A0, y has type B0. Here, I'm using A0 and B0 to mean unification variables. This is a type variable, but it's a type variable for an as yet determined type. And then we'll pretty quickly see that A0 must equal B0, right? Because in the right-hand side, we have x and y both used in the same list. And so that will produce this equality constraint that A0 must equal B0. The next step of inference is to simplify the constraints. So in this case, when we see A0 equals B0, well, that's a very easy constraint to solve. We'll just choose A0 equals B0. And then now we just have one type for both of them. It will turn out that there's no further work that we can do here. There's no other constraints on these types. And so we'll just say that this function takes 2 variables of type B and will return a list containing element of type B. So that's generate constraints and simplify constraints. Constraints also include class constraints. We might have ordered constraints and eat constraints, things like that in here. We're actually not going to focus too much on these steps. I wanted to give a little background on what's going on here. Most of what we're going to talk about is what happens afterward. So let me get rid of this stuff here and really focus on this stuff down here. So once we've generated and simplified these constraints, then how do we actually go from that to determining the type? Hindley-Milner would have you believe that we just look for all type variables that aren't in an outer scope. And then we generalize over those. And that's kind of true, but of course, GHC makes things trickier. So we're going to go through a bunch of examples that illustrate all of these other steps here. So let's jump down into the code. So this is real code that's running in GHCI here. I have a very recent build of head. So I guess you could call this either 9.2 or maybe even 9.4. And we're going to start with a fairly simple definition here. X equals 5. We can see, well, what's the type of x? It's integer. And already something interesting is going on here. That's because what we're going to see on the right-hand side is 5. It doesn't have type int. It has type A0, and we also get a constraint num A0. So we can quickly determine if 5 has type A0, then x also has type A0. But now, do I want to generalize over A0 or do I not want to generalize over A0? there's not further constraint. So I could say that X has type num A, arrow A. And indeed, that works. But that's not what happens. And that's because of something called the monomorphism restriction. The monomorphism restriction says that when we have a definition that does not look like a function, and X doesn't look like a function because there's nothing here, there's no argument to the left of the equal sign. When we have one of those, we will not infer any constraints. That's the monomorphism restriction. There's some other subtleties to it around mutual recursion and whatnot, but that's the simpler form. If we look at our recipe here, so the first step, the step 3, this first step of generalization, is to determine ungeneralizable variables. GHC calls these the mono-TVs. So 3b has variables mentioned in a constraint when the monomorphism restriction applies. So down in our example here, A0 is mentioned in this num constraint, and so A0 becomes an ungeneralizable variable. We won't generalize it, and then the reason that we get the type X of type integer down here is because GHC does defaulting and says, well, I know that there should be some type A0, I don't know what, but it's definitely going to be a number. And so what's a good number out there? Well, there's sort of a list of different number types that GHC will try in order. And the first one is integer. That works. And then X is assigned to type integer here. Okay, let's move on to the next example. So the next example is Warble. This also compiles. But actually, the interesting thing is not the type of Warble that I want to look at, but the type of verb. So in order to understand what's going on here, we're going to have to convince GHC to tell us what the type of verb is. And to do that, we can dedump TC, which that will output the result of the type checker. And so in here, we get stuff about verbal, but we still don't see the type of this local definition verb. So I need even more here. I need fprint type checker elaboration. Now, when I load, whoops, what's gone on? Something strange has happened. Okay, let's try that again. There we go. Now we get the type checker elaboration, which sort of buried in a lot of other gunk will actually tell us the type of verb. Okay, so now having sort of set up that we can see it, let's analyze what's going on here. So if we just look at this verb y definition, well, we'll see, well, this mentions X. So X is going to have type A0 for some unknown type A0. Y is going to have some type B0. We quickly learn, because we're adding them together, and plus takes two things of the same type. So we quickly learn that A0 has to equal B0. And we need this to be, we have a num constraint A0. But the question is can we generalize all of this? Could we say then that verb will have type, say, num b to b to b, right? It takes one argument, it returns one result, it has to be a number. Is that an okay type for verb? No, it's not. And that's because verb here on the right-hand side mentions X, which is a fixed type from out here. And so because of this, this type variable B0 or A0, sort of however A0 and B0 get resolved together, that is an ungeneralizable type variable. This is the very much more classic sort of Hindley-Milner, we can't generalize a variable that's already in scope. And so that's why down here, verb gets this type, P arrow P, not a for all type like verbal gets. So verb just gets this local type, that, or this type rather, that just mentions this already in scope P. Okay, so that's the verbal example. And again, going back to our outline, that's demonstrating how we won't generalize variables from an outer scope. The last part here for ungeneralizable variables is variables related by equality constraints to the above. So to do this, we're going to need a slightly more involved example. Let me comment this out, actually. So here, I have a type family TF and a function inject, which just takes something of type A and changes it to have type TFA. We'll end up needing type families to sort of make GHC a little not so clever, so that we can witness some of the strange things that happen. Now, my function here, f, I actually give it a type signature. I don't care about f, I care about g. And if I try to compile this, we're going to get a type error. about A0 is ambiguous. So let's try to understand what's going on here. So X is brought into scope. X has type A, as we can see from the type signature for F. Then, when we look at the definition of Y, well, we don't know what type Y is going to have. So I'm just going to call it A0. I would normally call it B0 just to keep it different from A, but A0 is what the error message uses. So we're going to guess that Y has type A0. Then, from the right-hand side, we see that inject X and inject Y are used in the same list. So if these are used in the same list, then that must mean that FA equals FA0. Now we have to determine, will we generalize? Can we generalize A0? And according to our rules, back up here, no, we can't. That's because A is a variable from an outer scope, and A0 is related to A by an equality constraint. Whoops, this equality constraint right here. And so GHC won't generalize. Instead, it will infer a type something like this, A0 to list of FVA. But then it can't figure out ever what A0 should be. Because there's no call sites of G. There's nothing for us to sort of use to figure out this next step. And so we get this error that A0 is ambiguous. This would not be solved just by enabling allow ambiguous types, right? It's not that we have an ambiguous type signature for a function. It's that really A0 is ambiguous. We just don't know what it should be. What's interesting here is that there is a perfectly good type for G, this one. And if I try to compile, this gets accepted. And so what I've done here is I have indeed generalized A0. I've called it B here. And then I just say that TF of B equals TF of A, where this A is brought into scope up here using scope type variables. So this is a little bit suspect, this variables related by equality constraints, because it actually stops us from inferring the better type for G. Okay, let's move on to the next example. And that's this IDI here. So let's look at the rule. The rule is number 4. After we figure out what the ungeneralizable variables are, then maybe there's still some variables, some of these unification variables we haven't quite sorted out, and we're going to default them. So in the case of IDI, this is a very simple definition. And if we compile this, we can ask, what is the type of IDI? Let's turn on print explicit for alls. And we can see that this is for all P, P arrow P. But what's the kind of P? Well, what GHC won't tell you, because it's just sort of omitted because they're so common, is that P actually has kind type here. But there are other good kinds for P. So I could write instead and that still works. So here now I've said that P is not a lifted type, but actually an unlifted type. So this would be a strict IDI that works only over types of an unlifted kind, or that are represented by an unlifted pointer, I guess. And yet she didn't infer this type. It specifically chose to use lifted types. That's because those are the most common. But this is this example of defaulting. And what's interesting here is that the defaulting mechanism is actually totally different than the defaulting mechanism that we saw earlier for integer, which happens all the way at the very end of type checking. This one, where we default, in this case, a representation variable, that happens during generalization. The next example is this cat id. So this is using categories id. So we can ask, what is c.id? So it's a method in the category class that works over any A of kind K. Or works over an A of any kind K, I really should have said. So what's the type of cat id? Not in scope. I guess I have to recompile. What's going on here? I wasn't expecting this. We need to disable the monomorphism restriction for this one. And now we compile all as well. and we ask what is the kind of cat-id, well, it's what we would expect. It's quantified over k and over the category of kind k and over a of kind k. That's all well and good. If we turn off polykinds, which is on by default in newer GHCs, and I compile everything as well, but now the type of cat-id, it defaults all of these kinds to just plain old type. And this is all part of this defaulting step. Okay, after we've determined the monovariables and then defaulted, we now have to choose the actual quantified variables. So we have a few more examples to demonstrate that. That's down here. And let me re-enable the monomorphism restriction, although I don't think it comes into play right away. So if we look down here, well, what's going to be, what's going on here? So we have show 5. 5 has type A0 for num A0, but printed has type string. Oh, and we're also going to have show A0, aren't we? And so now we have to figure out, are we going to generalize this A0? We don't really know what it is. No, we're not, and that's because A0 isn't mentioned anywhere in the type string. And so because of that, we don't know really what to do with A0, and so we're going to use our defaulting scheme. And that's, we can see that here in this output that show is actually specialized to integer. So here the default matters, right? If I default to double, I'm going to get a different string. Length has a similar issue, except here there's really no class constraints. And so the defaulting works differently. It defaults to sort of an internal type any. That's because GHC determines that no matter what we choose as the element type of this list, we're going to get the same result. Let's see, going back to our little outline here. So that's this 5a. We're only going to quantify over variables that are mentioned in the body after the fat arrow sign of the inferred type, as well as variables related to those in a constraint. So that's our next example with frob and zerp here. So with frob and zerp, here I have frozu(x), which calls frobzerp x5. So frobzerp is this function here, and frobzerp will give rise to a constraint frobzerp of a, b. So here we're going to have x of type a0, 5 has type b0. We're going to get a num b0 constraint, but then we're also going to get a frobzerp a0, b0. The type of frozu we're going to see is, what is it going to be? A0 to unit. So normally we could generalize over A0, but not over B0, because B0 isn't mentioned in this type of frozu. But because it's related to A0 in this frobzerp constraint, we will generalize over B0. And indeed, we can see that if we look at the type of frozu. Oh, not in scope. Maybe I have to recompile again. Here we get frozu, frobzerp a, b, num b, these constraints, even though b isn't mentioned over here. So this is an ambiguous type, but it's still the type that GHC will infer. By contrast, we can look at fro blank zoo, which separates out the frob and the zerp. And so now we're going to get a separate frob a and zerp b constraint. And then now we get errors because it's not going to generalize over that b. Instead, it complains about ambiguous types. It calls it A0 here, but really the problem is that we can't satisfy zerp of A0. The last step here is, whoops, let's just comment out this whole region. I'm going to leave some time for questions. So the last example that we're going to look at is let's see, it's choose the quantified, or sorry, is remove redundant superclasses. This choose the quantified constraints is really about, we want to also figure out what goes to the left of the fat arrow. And it's only going to be the constraints that mention the quantified variables. That one's actually fairly simple. This last step is about removing redundant superclasses. So here, check ruffle, right? On the right-hand side, this gives rise to both an eq A0, if we have x as type A0. This will give rise to eq A0 and orid A0. And we could imagine quantifying over both, but that would be a little silly. It's much better to get this type here that just mentions array by removing the redundant EK superclass. So there's actually a lot more than we've seen in generalization. Partial type signatures makes this much more difficult. There could be mutual recursion, implicit parameters, functional dependency, something called naughty quantification. You can search the GHC source code for more about that, as well as all the usual implementation details. But I'm hoping this overview gives you some ideas of what will happen in GHC when you have a definition without a type signature. Thanks very much.
Okay, thank you, Richard, for the great overview. I'm checking questions. So there is a question by Adam Gundry. I'm just going to read it because we don't have very much time. What's the motivation for Rule 3C? You showed an example where it was unhelpful, but when is it helpful?
So I actually think that Rule 3C is unhelpful. So there's a patch that I'm working on that gets rid of derived constraints in GHC that actually changes Rule 3C to be variables that are sort of implicated by a functional dependency from those that are fixed, right? If we have fixed variables on the outside that control variables that haven't otherwise been fixed through a functional dependency, we're going to fix those, but not this just related by inequality constraint for exactly the problem shown in this talk.
Okay. Then there is a question by Matthias. When we are not running in interactive mode, we get a lot more ambiguous type variable errors for some of these, right? I guess it's a leading question.
I don't think that there should be a difference between interactive mode and not interactive mode. I guess the only real difference I can think of is that interactive mode uses something called extended default rules, which makes it more aggressive in defaulting. But I don't think any of the examples, at least in this talk, trigger those rules. So maybe we can talk offline about the example you're thinking of.
Yeah. Okay. Then we have a question by Joachim. How principled is this algorithm? Is it based on what works best in practice while still being feasible, or is there a more fundamental guiding principle here, principal types or something like that?
That's a good question. You know, this has sort of grown over time. I don't know that there's a sort of a concrete analysis of it. That's a great question, and I don't really have a good answer. I'd be happy to discuss that. Certainly, we need to not generalize over variables from an outer scope. That's all about principal types. And then the rest is just sort of funny features in GHC, right? Monomorphism restriction, defaulting has to do with these extra fancy features. Avoiding ambiguous types. I don't know. I don't have a great answer.
Yeah, so there are some comments by Simon, which I'll just read as well. It's worth stressing that there is something a bit arbitrary about the generalization rules. A safe and principled thing to do is to abstract over all unsolved constraints, but you get huge types that way. And yeah, I think
yes.
Let's and then there's one final related question by Roger Bosman. Can you elaborate on the decision to default instead of generalize? Do you prefer simpler, slightly less general types over potentially confusing the user?
Well, there's sort of two different places we saw defaulting. One was around the monomorphism restriction, which has to do with sort of, do we want unexpected, runtime consequences of having a constrained type? The other defaulting has to do with restrictions in compiling levity polymorphism, right? We can't generalize over representations, so that's no good. The kind variables, the fact that we default them, I think that's a bug because I would like to remove no polykines at this point. Defaulting multiplicity variables is about simpler types, so there's actually sort of different priorities here, but there is generally a desire to infer simpler types because these complicated types are confusing. And so how do we balance out generality with simplicity? I don't know.
Okay, thank you again, Richard. we have to
Thanks.
stop here, unfortunately, because we're short on time. The next talk is by Sam Derbyshire, and the title is A New Interface for GHC Typechecker Plugins and Type Family Rewriting.
All right. So let's get started. So I've been working with Richard over the summer on GHC, and one of the things I've been doing is working on these type checking plugins, and in particular rewriting type families. So I'm going to go over that. So first I'll talk about kind of what are the things we want to do in these type checking plugins. I'm going to review what we have currently, talk about what I'm adding, so these rewriting of type family applications. And then I'm going to give a quick example so we can see some actual code, but it'll be quite short, but I'll link to the full code. And finally, I'll talk about this new library I've written. This should make life a lot easier for authors of type checking plugins. So first off, what would we be using a type checking plugin for? So I assume a lot of people already know you can use it to solve instances and rewrite type families in a kind of not depending on GHC's own logic. So here we're going to focus mostly on the type family aspect. And I have some basic examples to show. So first off is a bit of arithmetic. So if we have a type family like this, where we're just basically inductively defining addition, we quickly run into some problems reducing this type family application, because the way this works is we're looking at the first argument. So the type family will be able to reduce only when we know what the first argument is. So that can cause some issues quite quickly. So for instance, here's something that the GHC can't solve. So n plus suc n equals suc of n plus n. And the problem here is the first argument to this addition type family, the first argument is a type variable. So we don't know, well, is it 0 or is it the successor of something? And so because we don't know, GHC just doesn't reduce this type family application. It stays like this, it stays stuck. And as a result, it's not able to reason about it. So that's one thing we'd be able to do with a plugin. So for instance, Christian has the typelets not normalized plugin, which introduces logic to handle this. A second example would be row types. So a row type is kind of the type level logic that we would have to handle some like extensible records. So we'd have something like field 1 is of type int, field 2 is of type bool. But the important thing is with these records, we want to deal with unordered records, so that the order in which these fields are specified shouldn't matter. So if we imagine trying to set this up with a type family, we need an equation like this. So we have a row R, some abstract set of fields and types that is not determined yet, and we want to be adding 2 extra fields to it. So we add the type W with name L and the type V with name K. And one thing we might need to prove is that we've got an inequality like this. So we'd be reordering this type family application. But the problem with that is in GHC, we can't have a type family equation where the left-hand side is also a type family application. And so here's the error message we'd get from trying that. Illegal type synonym family application in instance. And well, there are several reasons for this, but one of the reasons is non-confluence. So here's a very simple example. We've got a type family F, and we suppose we're allowed to have it refer to this type family F in an argument. So we have these 3 equations like this. And now we can see if we take a type like f of bool, well, we could reduce this in 2 ways. We could start by reducing the outer type family application. So we use the first equation there, f of f bool. So we got a equals bool, and that gives us bool. So that's if we reduce the outermost type family application first. if instead we decide to reduce the inner type family application, so we start by rewriting fbool, well, fbool reduces to float. So, and we've still got the outer f, so we get f of float. And then the equation that would match here would be the third one. And then we get maybe float. So this is just a simple example to show that if GHC just allowed type family applications on the left-hand side, in a naive way at least, like this, then the order in which we write type family applications would end up mattering, and we could end up with different results. So that's one of the reasons why GHC doesn't allow that. But in plugins, we will be able to do that. So it's kind of becomes the responsibility of the plugin author to write code that reduces type family applications in a way that, I mean, that prevents this non-confluence problem. I mean, if a plugin author wants non-confluence, they can have it, but I think generally speaking, it's something we'd want to avoid. So let's review now a bit these type checking plugins. So first, how do they fit in with GHC? So we can imagine we've got GHC's type checker on the left here. So we've done the previous stages, like we've passed, we've renamed, etc., and then we start type checking. And then when we're about to start type checking, we initialize the plugins. So that calls this, for each of these TC plugins, they'll have a function called init, which I'll review in a second, that kind of starts up the plugin, and it can do things like start up some external tool like an SMT solver or something like that. And that will generate some kind of plugin environment S, which the plugin author can choose. And that gets passed to the other stages of a plugin, which are the solve stage and the stop stage. But it doesn't call them, it just passes this data they're going to need. And then it's when we're in this type checking loop that we actually call these plugins. And for solver plugins, there's two ways they can get called. They can get called to simplify some given constraints, or they can get called to solve some wanted constraints. So this will keep happening in a loop until GHC decides it's done, it's solved everything, or it's finding things that are definitely insoluble. And then it'll finish and call the stop function. So that's kind of what we had already. And now let's see what we're adding. So this is this TC plugin data type, which had these three things we saw previously: init, solve, and stop. And we're adding a new field, which is rewrite. So rewrite, it takes in this plugin state. We'll see a bit more what plugin state is if you're not familiar, like how it's used in practice. And then it returns a map. So this just means a map from tycon, which is like going to be the name of the type family we want to rewrite, to a rewriting function. And what's a rewriting function? So we want to write a type family application. So we have the type family name here. We're going to have its arguments, however many arguments, just to make sure the type family application is exactly saturated. And we also specified the given constraints at the point of rewriting the type family. So that's knowledge we already know at the moment we were writing, which, as you'll see in an example, we need to know sometimes. And we return this TC plugin rewrite result, which is basically just a maybe type. So either we don't do anything, or we rewrite. And if we rewrite, we have to specify what type we rewrite to, but also specify a coercion. In the plugins, it doesn't really matter. We can use some type of universal coercion, like believe me, which is kind of what we already did for constraint solving plugins when we were solving inequalities. And the other thing we're allowed to do also is emit some new constraints when we rewrite. So that's kind of quite different from how GHC usually worked, because when GHC rewrote type families, usually it never created any new constraints. But in a type checking plugin, we're allowed to do that. So in terms of the previous diagram, we're just adding one new stage. And as I explained previously, we get past these given constraints from the type checker, and we get past the arguments for the type family application, and we have to specify a reduction, which is this pair of a type we reduce to and a coercion that witnesses this reduction. Okay, so now I'm going to go over one of my own examples. And this was inspired by a little challenge that Stephanie Wyrick posed about a year ago, which is to implement a strongly typed version of systemf. So this would be some kind of AST. We'd have some terms, but it would be a gadet. So we keep additional information at the type level. So in this case, it would be a context and a type. So for example, we could have a function application. So that takes a term in context phi, which is a function type, a to b, and then a term in the same context phi of type a, and applies that function. So we'd get a term in the context phi of type b. The other thing we have, so in systemf, compared to lambda calculus, is we have these type lambdas and type applications. So for instance, we could have a for all type, and instead of applying it to a term, we apply it to a type. So this would be a singleton for a type, and then we apply it, and we have to substitute in the type in the term. So for instance, it might be the identity type, like for all x, x to x, and we apply it to int, and we get int to int. And so the key thing here is this substitution type family we've got. So let me just quickly show what that looks like. So we have some apply sub type family, which would take a substitution. That's in the example I've got, it's some declarative type. So it could be the identity substitution. It could be a composition of substitutions. It could be, well, as in the example below, we extend the identity substitution with just a type. And so we've got this type family. And we'll see what we want to prove about this that we can't prove normally. I'll quickly, for later, we'll see that it's important when we're writing type checking plugins to take into account the visible but also the invisible arguments. So the full kind signature of this would be, so it takes a substitution and a type and returns another type, but it takes in some additional invisible arguments, so contexts and the kind. You don't need to worry too much about what this is, but it's important to know that it takes in 3 additional arguments. So when we're writing this type family in a plugin, we have to take into account these additional arguments. That's the same as it's been in the past in type checking plugins. So what difficulty do we have with the setup, and why would we need a type checking plugin? It's what we've seen before, problem of rewriting an argument which is a type family application. So we want to rule like this. So we're applying a substitution T to A, and then we apply the substitution to S to the result of that substitution. And we'd like to rewrite this to applying the composite substitution S composed with T to A. And there's several reasons for that. One of the reasons is then we can completely reason in terms of this language of substitutions we've got, and we'll have many kind of propositions on substitution that we can rewrite. We can rewrite the composite of the identity with something. Well, we can just remove the identity and things like that. Or we could, if you've got 3 compositions, then we want to reassociate so that, if it's A composed with B composed with C, the parentheses on one side or the other, then we want to be able to reassociate. So we're going to need a type checking plugin to handle this type family in a type family argument. And the other thing is we might also need to use given constraints. So we might have something like apply sub S to F, and the given saying that F is equal to apply sub TA. So it might not be immediately obvious. We might need to use a given constraint. And this happens, on GHC 9.0, for instance, it happens quite a lot because we have flattening of type families. So we'd often see things like this. So we need to be able to handle that situation also. So that's kind of why we had the given constraints passed on to these type family rewriting. So let's see what this looks like if we try to implement a type checking plugin to rewrite this type family. so we have to specify a rewrite function. That's what we saw before. So this plugin defs is the little S we had in the diagram. And for people who are familiar with type checking plugins, we looked up a lot of information like what is the name of things. So here in particular, we'll have looked up the apply subtype family. We have looked up its tycon, so we can refer to it in the plugin. And so we have to specify a map for each type family name, a rewriting function. So here we'll have the apply sub type family, and we'll have the rewriting function associated to it. And we can specify this as a list and use the list to UFM function in GHC to get a unique FM. And so then this rewrite function, well, so it takes in these definitions because I passed them here, takes in the given constraints, it takes in the arguments to this apply subtype family, and it's going to be a fully saturated application, and it's going to have to return a rewrite result. And so in this case, we have 5 arguments. If you recall, I had the full standard unkind signature for the write sub for the apply sub type family, which had these 3 extra invisible arguments. So we have to take those into account. So I won't write out the full definition of this function because it handles a lot of different cases, but that's going to be available in the repository. But for example, if we were in a situation where we've got these arguments and we've got another given like this, so this argument here to the substitution is another application of apply sub, so that's going to be the nested type family example, then we'd rewrite something like this. We'd say, well, so this is apply sub of T to, apply sub to this. So then we compose them. So here we'd create a tycon application of this composed data constructor, promoted data constructor. When we pass all these arguments, so we'd have the first substitution here, and then the inner substitution here that we've obtained from a given constraint. That we're not emitting any new constraints. We don't need to do that here. And then we can, so this is just the type we want to rewrite to, and then we can specify it as a reduction. So in this case, this is specifying a nominal reduction, and it's specifying this kind of string here. You can specify whatever data you want. This is the usual thing you can do in type checking plugins of specifying a universal coercion. So that's a little overview of how we would rewrite a type family with this new interface. To finish up, I'd like to talk about the new library I've written that kind of simplifies all the things around writing type checking plugins. So one of the problems with writing type checking plugins is we have access to way too much stuff. We have access to pretty much the whole of the GHC compiler. And that means we have to know exactly which function to use and where to import it from. And this leads to import lists to look like this. So just absolutely loads of things, and things have changed across GHC versions, which means it's quite hard to maintain. Loads of CPP instructions. It's just a nightmare. So instead, my idea was, well, let's have a library handle all of this. So we can write a library that exports something that tries to be as stable as possible, and in particular will handle these internal GHC changes and just export what an author of a type checking plugin would need. So we replace this by just import a single module. And this is quite helpful to get started for beginners, because now we don't need to go looking to see where is everything defined. So for instance, we could just import a single module and then say we want to turn a coercion into an evidence term for an equality constraint. Well, we say we don't remember which function that is, so we just put an underscore and use typed holes, and we get a suggestion: use ev coercion. Or another example, where we want to apply a type family or promoted data constructor some arguments. How do we do that? Not sure. Put a type hole, make type up. So, I mean, obviously in practice, it's not going to be as simple as this, but it helps so that we don't have to, because otherwise, if we didn't know which module to import it from, we'd never be able to get these suggestions. So it's quite helpful. And the other thing is, I think the package documentation can be quite helpful. So I've written loads of like small snippets to get people started, to orient people, because there's a lot of things one needs to handle when writing a type checking plugin. So for instance, looking up all the names when we start a type checking plugin, that's not obvious, and it's not necessarily very well explained. So the package documentation is kind of a way to get people started and to tell people how to, or what things they might need to do, like enable call int or enable dump tc trace and how to look through tc trace and things like that. And there's a few helper things that I've also added to the library. So for instance, emitting custom type errors, that's always been kind of annoying, because you need to look up all the constructors for this error message data kind, and then construct a type for this error message and everything. So the library kind of handles that.
I think we have to come.
Okay, one last slide.
And
yeah.
If you want to have any questions, you have to.
Yeah.
And now.
Yeah. So we've got an API for custom type errors, which simplifies things a lot. So this is all available now. So the library is available in Hackage. Everyone can use it. The type family rewriting functionality. So that's been added natively to GHC 9.4, but it's also already usable on GHC 9.0, 9.2 if you use the package. It's going to be slightly less efficient because it has to use the existing API, but it still works. And then the GitHub repository contains the full example for this system F, and the slides are available online. And finally, I've got a blog post in the works on the Twig blog, which will do a more in-depth overview of constraint solving and type checking plugins. So for all the necessary background, if you're really beginning writing a type checking plugin, and that's it. So
okay, thank you, Sam. This looks great. Thank you. I'll ask two questions, even though we're a bit over time. So first is by Adam Gundry. Do you have an example to motivate type family reductions emitting new wanted constraints? It seems fishy to me, as we don't have a clear specification of when a type family gets reduced.
Yes, well, I don't have so many motivations. One of the ones is that's the mechanism I'm using currently to emit new type errors. So if you want to emit a type error as you write a type family, you can do that by emitting a type error constraint. Or, if we change to Adam's unsatisfiable constraints, we could emit an unsatisfiable constraint. But the idea was also to experiment. So it wasn't difficult to add this functionality. So I thought, well, let's add it and see if people find uses for it.
Okay. And one question by Joachim Breitner. What core gets emitted for these reductions? Essentially unsafe cores, right? Can plugins opt into producing evidence for the rewrites when possible?
So this is the same as normal type checking plugins. So you just have to, you can pass any coercion you want, really. But the thing that pretty much all plugins always do is just say, use a universal coercion with plugin provenance, which, as Joachim says, is basically unsafe coerce.
But so the answer to being able to opt in is essentially yes, nevertheless. I mean, plugins could.
Yes, but there's not really a good, in my opinion, a good framework for, there's not a custom programmable language of coercion. There's not an extensible language of coercions that you could use. You have to use the existing coercions that exist in GSC. And, you can't use the type family rewriting coercions because, well, specifically, those are too specific. They don't handle rewriting type families with type family arguments and things like that.
Okay. All right. We have to stop here. Thank you very much again, Sam.
Thanks.
Then the next speaker or the next talk is by Matthias Paul Gisurarsson and Agustin Mista. I think the speaker is Matthias, and the title is The Dynamic Haskell Plugin for GHC.
My name is Maddie, and my partner in Crimes Against the Typechecker is Agustin Mista. And we're both PhD students at the Chalmers University of Technology in Gothenburg, Sweden. Today, I'm going to talk to you about the Dynamic Haskell plugin for GHC. The dynamic here refers to dynamic types. You might know dynamic types already from top hits such as Python, JavaScript, and Erlang. And what dynamic types essentially allow you to do is to delegate type judgments to the runtime, which means that you don't actually have to decide what you're going to do until you have a value of that type. Now, this can be very nice for instance for do fast prototyping. It can be very nice to do heterogeneous lists, and it can be very nice especially in cases like Erlang where you're not sure what the data you're going to be getting is looking like. So if you're running a node or a server and you get a message, you might think you know what the type of that message is, but you want to be able to safely work with it until you actually have to make a decision. And dynamic types can really help you in that respect. So you can use dynamic types in Haskell already by using the data.dynamic module. It's a very simple module. It has this dynamic type, which is an index type rep, and the value, which together form a dynamic value, which contain some type rep, which is kind of a representation of the type and the value itself. It has a toDin function, which takes in a value and it returns a dynamic, but with the caveat that you have to be able to give it a representable type value. So it goes into this type rep. And then you have the from dynamic function, which is kind of a safe interface. And it's very cleverly done. It essentially says that if you give it a dynamic and you want the type that it actually contains, then you say just that value. But if you want a value, if you give it a dynamic value and it has a different type than from the one you expect, you return nothing. So how do we use this? Well, here's a message passing example, right? So what we have to do to use dynamic is we have to apply toDin to every element in the list, right? And then when you handle the message, you have to use this just dance, right? You have to say, oh, if you give me something and it's a boolean, then we handle it as a boolean. If you give me something as an int, we handle it as an int. If you give me a unit, we handle it as a unit. Otherwise, we're going to throw an error. And you notice that we are giving this a string. So it's going to crash if we give it a string, right? We don't know what happens if we get a string. It's a very common case in dynamic languages, right? That if you give something that is expecting a certain set of types, something that's not in that set, then you just crash. So if we run this code, we get the expected output, right? We get yes, we get 42, we get the no, we get the unit. But yeah, when we hit the string, we just get an error. And this works, right? But we're Haskell, right? We're at this point in the Lambda cube where we have a very strong type system, the strongest possible type system, while we can still deterministically infer the types of all the things, right? That's kind of the point where you want to be at in the Lambda cube. Of course, this has some caveats now, right? I mean, there are things that we can't actually type deterministically because we've added stuff to the type system, right? So we sometimes have to provide annotations, and that is expected. You can see with like the 42 here, right? We have to tell it if it's an int or integer, otherwise it's just going to be a mess, right? But the idea here is, we know that we have a value boolean, right? And we know that we're expecting a dynamic. So why don't just do the obvious thing? Why don't we just turn that boolean into a dynamic? When we look at all the syntax that's just extra here, we can just remove all these toDins, right? Just coerce it into a dynamic. Just make it into a dynamic, right? Remove all this from dynamic maybe dance. Just say if it's an X boolean, then I want to do this. If it's an int, I want to do this, right? Now we've defined this sugar interface to kind of how we want it to look, right? So, you give it a list of things, right? And it's expecting a list of dynamics, but it's not a list of dynamics. It's something else. Then we simply add a call to toDin everywhere, right? That's just what we should do. It's kind of one obvious thing to do, right? So we have this already in the plugin, right? Now, this is function here is just a pattern synonym, actually. It just removes the just dance, right? It just says if it is a boolean, do this. If it's an int, do this. If it's a unit, do this. And now we're not doing anything extra, right? We're just communicating our intention to the compiler without all that extra overhead, right? So this works with just a pattern synonym and view patterns, right? But for this, we need some sugar, right? We need this to mean something else. right? We need this to mean 2 true and 2 42. But that's okay. We can do that. But this is not, this is not kind of the end point, right? We want to be able to not just match on the type, right? We want to be able to match on the constructors themselves. And that's what you can do in Erlang, right? You get a message, and what in Erlang, you usually match on both the type and the pattern of the message that you get. So by being able to do this in Haskell, we're very close to what Erlang does, and they do it very nicely, and they're a hugely successful language. So I think this will be very nice. But another caveat is that in Haskell, we have a lot of type classes, right? A lot of the stuff we do is using type classes. So being able to make things dynamic doesn't really help if everything you're going to apply it to a type class and then it doesn't work anymore, right? So here's one such example, right? We have a type class and it has instances for bool, int, and unit, right? But there's no dynamic. There's no instance for message dynamic. So if you call this message function on a list of dynamics, it will just complain that there's no instance for message dynamic. So we would like to be able to do something there as well. Kind of being able to work with type classes as well. Okay, so what's the trick here? Well, the trick is actually using typechecker plugins and this message, right? That booleans is not dynamic, right? Or that there's no instance of message dynamic. So the trick is writing a GHC plugin. So we were already working on a GHC plugin for weak runtime irrelevant typing for security. So there's a nice library in Haskell called the Mac library. It's written by Alejandro Russo, and what it allows you to do is essentially label boxes with security values. So you can label the box as either private or public, and using this, you can kind of ensure that you only use private values in private contexts. So you're not leaking private values, and you can actually be sure that you're not accidentally using a private value. You can, of course, use private values if you need to, but then you kind of need to state that in the type system. But we wanted to be able to run potentially insecure code, right? Or code with all these security types and, just to be able to test it without having to bother with all the security. So we wanted to be able to go from a secure type to an insecure type. And what's really nice about the Mac library is that it's all new types and it's all phantom type variables. So we can just use safe coerces. So you can safely coerce from whatever type to a secure version of that type, and you can safely coerce back to whatever type you want, right? If it's the same type as the one wrapped by the labeled box. So we want to be able to weaken the security constraints, right? But this, of course, creates an error, right, in the type system, right? We have two ways of typing things. So we've gone the theoretical way of saying we want to type it the way that produces fewer warnings. This is not very clear yet. We're still working on how to kind of theorize this correctly. But, you want to be able to type things only if they didn't work out regularly, right? So that's exactly what we do. We catch this int is equal to dynamic message, which GHC has tried as much as possible to solve, and we can solve that, right? But we know that everything that can be solved has already been solved by GHC. So we only kind of match if it would not compile otherwise. So but then we've put in an order requirement of the type system, which is not theoretically nice. So there's some work to do there. Okay, so how do we do it? Well, it's based on these three functions that we insert into Corp, right? Let's just go over these functions, right? So we have the dincast function. Now this one goes from dynamic to an A, right? And it kind of, whenever you're stuck, you want a value of A and you only have a dynamic, what do? Well, you can go from dynamic to that value. But from dynamic goes to an maybe, right? And we just want the value. So how do we do that? Well, we do the dynamically typed thing, where if you give me something and it's not of the type that I expect, then I just crash with a message saying, you gave me an int, I was expecting a string. This is very classic in languages like Python, right? So, this direction is very simple. You have something and you want a dynamic, and this is just the 2din function from data to dynamic, right? We just wrap it in dynamic. It all works out very nicely. This is the final function. This is kind of a cool function. This one does the dynamic dispatch. So what happens is that we get these, int is equal to dynamic function in the plugin, right? And what we do is that we commit a crime, right? We lie to the type checker. We say, no, ints are dynamics. That's fine. But what we do later is that we do a core pass where we fix all those lies. And we say, oh, I told you int was dynamic. Just by coercing, but that's not actually true. So replace this coercion with a toDin, right? Go to the dynamic function. But to do type classes, that's not enough. You can't just go to the type class. So what we actually have to do is that we have to generate this dispatch table. So what we essentially do is that if you want to generate the message dynamic, you want to call message on dynamic, we generate a table where all of these typers will be the string, or will be the, not the string, will be the bool, it will be the int, it will be the unit. And then this dynamic value here is actually the function at that type. So then you send it to the right class instance. So it kind of works like dynamic dispatch. And this is exactly like dynamic dispatch works in some languages. It's a very nice way to do it, right? And we automatically generate this table in core when you hit this. So it's a big core function, but it works and it's very nice. So these are the three functions that we kind of base it on. And of course, so we have it working and we get it to compile and it doesn't generate lint errors. But of course, some of the errors are very confusing if it generates a lint error, right? So for instance, if you don't specify that the 42 has to be an int, then it just crashes and with a long error saying essentially that, it couldn't figure out the type of int or integer, but that's not the error, right? Because we already solved the problem. We solved the type error, so we don't get the ambiguous type variable error. So there's some work we need to do to interface better with the type system. Let me show you a demo of how it works. So here we have the message module from before. I mean, we're using some type extensions, and we enable the plugin, right? And what we get is that, this is all integrated into GHC. It's all integrated into the excellent work by the Haskell language server team, right? So now it actually marshals, that's what we call a dynamic cast, all of these values into dynamics. And it says, okay, this bool here, I'm going to make it into a dynamic, right? I'm going to marshal this into a dynamic, this bool. I'm going to marshal this unit, and I'm going to marshal this string to a dynamic. Now, this already works, right? So if we compile and run this module, then we get all these warnings, but that's fine. We can still compile it, and we actually run it, and we get the expected error, right? We hit this unrecognized message clause. And if you turn off the plugin, then it simply turns these errors into warnings, right? Could match dynamic with actual typo, which is what you expect. Yeah. So this works. That's great. So here's the other module we were showing you. So here we have the same, right? We marshal all these things, but now it's not enough. The pattern is not enough. So we actually have to generate the dispatch table. So we build the dispatch table. We use all the instances that we have in this module, and it actually uses the instance lookup functionality to find all these instances. And we just generate the dispatch table. And then when we run this, we get the expected value. And what I also wanted to show you here is how nicely it interfaces with the... Oh yeah, sorry. So I already turned off the module. So now I turned it on. So we get the expected message, right? No instance for message dynamic. But then I turn on the module again. And then we get marshalling messages. And then builds the dispatch table. And then it actually works. It just calls a function at the right type. But of course, we call it for a string. We don't have an instance for string. So then we get that classic error here. No instance of message, list of chars when dispatching message, right? Which is a, expected error. You get a runtime error if you try to do the wrong thing. Okay. So it works. And I think it's very nice. But we're still kind of in the process of molding it and seeing where we can take it. It's very early, proof of concept, right? We're not done. There's a lot of theory to be done. There's a lot of work on doing like, what can we do now if we have this? Like, are there things that we would like to be able to write in Haskell now that are much nicer to do in this way? There's a lot of theory, like it's called gradual typing, which is this thing where you have untyped code and you have typed code, and then you're using parts of the untyped code in the typed code and parts of the typed code in the untyped code, and this mishmash there, the interface and the boundaries where you have partially typed code. What happens there, right? And there's a lot of body of theory called gradual typing around that, which we have to explore, and the connection between them. And we got very good comments from the reviewers already, so thank you for that. And we're really here to present this work in progress to get feedback, and hopefully, if it works out and the plugin shows success, and that is a nice thing, maybe we can make an extension someday. I think that would be nice. But we're really doing try first, theorize later. We try, see what happens, see how it works, try and figure out what we want to do. Because our motivation here is just do the obvious thing. What is the obvious thing to do? Like, what would you expect to happen with dynamic types? Which is what Python and these languages do. They just do what you would expect to happen. But yeah. All right. That's all I have to say for you today. Thanks for coming to the talk. And if you have any questions, we'll be here around to answer your questions. And if you're watching this later, then you can reach us on Twitter as well. So I'm Tritlo, and Augustine is Augustine Mista. All right. Thanks a lot, and goodbye.
Yes.
All right.
Thank you very much, Matthias. And I see we have you here.
Yeah.
For questions. I'm just checking, but I'm currently not seeing, and perhaps you have already answered everything in your talk. I would still be wondering a little bit about this motivation. I mean, perhaps asking slightly provocatively, I always think it's very nice that in Haskell we can basically just model dynamics as a subpart of the language. But then when it comes to actual applications, I don't really know. I don't actually have all that many. I mean, is there a particular thing you want to do in Haskell with dynamics that made you?
I mean, so it's mostly, things like I said, like, you want to have you get some value from a user, right? It's a big JSON, right?
Mm-hmm.
And you want to be able to interact with it in without having to deserialize it completely, right? You just want to say, it's going to be a map of strings and some dynamic values, and I just want to use those. And I know that this field will be an int, right? And then I just want to go from dynamic and back, right, without all the syntax overhead. And the trick is that this is all possible already, right, with the dynamic, but at least, we haven't seen a lot of use of the dynamics in the wild, right? And I think it's mainly because of the syntax overhead, right? It's just, you really have to convince the compiler that this is okay by casting to and from, right? And yeah, like I said, there's lots of languages that have dynamic types, and they seem to be very nice, right? So I think it would be cool if we could kind of do something nice with dynamic types instead of this kind of limited subset, right?
Okay. And there is a question by Joachim. Will GHC recompile stuff as needed? E.g., if I add an import that just pulls in another type class instance and not use it directly, but it would be picked up by your tools, will GHC recompilation avoidance do the right thing?
That is a very good question, right? So what we so the plugin works. So it gets this message, right? You're trying to compile a function that uses message, right? And you get this unsolved type class constraint. Could not solve message dynamic. And what we do is that we essentially you can look up in the current scope and find all instances of a message and all the types that they have, and then we use that to generate the table, right? So if it's not in scope, when the plugin is invoked, it won't find that instance. So I don't think that will work. And there's another big caveat right now is that it doesn't work in GHCI, because what we do is that we emit this core with a lie in it, and then we fix that lie, right? But in GHCI, you don't do the core-to-core passes, right? So we don't actually get to the part where we can fix it. So it will just run an unsafe course and won't work. So we also need to figure out, can we make this work interactively as well? So I guess that answers the question, right? If you add an import, interactively, yeah, we can't do anything there because it doesn't work anyway. But we're still trying to figure out how to do it properly.
Okay, thank you. I think we should stop here. Thank you again, Matthias.
Yeah, thanks.
And next, we have the GHC status update. So as I said at the beginning of the session, we're going to let this run into the break, but we are still going to have to stop in time for the next session to start at the scheduled time. And Simon has indicated that he wants questions throughout, so I'll stay around and interrupt occasionally, I guess. And I think Ben is also here. Okay, so welcome Simon and Ben.
Hello there.
and just go ahead.
Hi there. Good. Yes, let's proceed. So please do. Let's see. So
Oh, you're very difficult to understand, Simon.
oh dear, this is bad. Why is that?
It may be the wrong microphone.
Oh, wait. Maybe it's. Could it be that I'm using? How do I?
Can you hear me, Andres?
Yes, I can.
Excellent. Great.
Very nice background.
Is that better for sound?
Much better.
Okay, good. Right. Sorry, I was using the wrong microphone. Good. Okay. Let's see. Was I succeeded in sharing a screen? No, it sort of stopped. Let me do that again.
Yeah.
Good. This is just a little catch up on the current state of GHC. We'll go, Ben and I will go sort of quickly. There's quite a lot to say, of course, but please, I'm going to keep an eye on the question and answer as we go. So just put things in the Q&A and we'll respond to them as we have them. It'll be more fun than waiting till the end. So here we are. What's big in GHC? Well, the biggest thing for me is always the GHC's community, right? GHC is the product of a lot of people now. It's a big piece of software with an enormous contributor base. Here is the commit count over time, which this is actually done by calendar year. So the counts for 2021 are only for January to August. I think Ben will correct me if I'm wrong here. So see, commit counts here are going up. But there's a lot of them. This is like even so far this year, well, by the end of the year, there'll be well over 2,000. That's a lot per day. Number of tickets opened over time. Well, that's pretty high as well. Look at that, 1,700 last year, and I guess nearly 1,300, and we're only in August. GHC contributors over time, I'm particularly proud of this, is people who've contributed in some way, I think by a commit, and will correct me if I'm wrong, to GHC, kind of like up 100 during and this is a August to July year now. So now the numbers are comparable between the 2020 and 2021. And here is the number of committers making more than N commits, where N is 1 for the blue bar and 3 or more for the orange bar and so forth. So there you can see, I think we're pretty stable there. Probably the identities of the committers is changing, but the actual numbers are pretty stable. And I think that, again, this is an August to July year. On the community front, the big event of the year was the launch of the Haskell Foundation. And because GHC is just part of a rather complicated ecosystem, as all of you will know, it's really helpful to have an organization to help glue us together better with our ecosystem of, the stack and Cabal and the Haskell language server and all that. Really helpful. And I do want to say a special thank you to GitHub, who've taken over the funding, frontline support for GHC this year, routing their funding through the foundation. So they're explicitly a sponsor of the foundation. Let's just say a little bit about what's been new in GHC in the last couple of releases. So I thought I'd start with performance, because performance has always been a bugbear and it's usually got worse every single release. But for a change, we have good news. It's got better. Look at this. This is comparing the state of play this time last year, that's the blue bar, with the state of play for 9.0, 9.2, and the current state of play today, which is the orange bar. So you can see that this is to build Cabal with -01, has gone down by about 25%, the elapsed time, which is, I think that's fantastic. And that's on that's with I think with 4 cores on the left-hand bar and with 1 on the right-hand chart. So I'm quite thrilled about that, because it's that's a result of quite a lot of work by quite a lot of people, actually. And here is, and on the memory size space, it's even more impressive. Look, it's just about halved the amount of memory you need to compile with -01. So I'm thrilled about this, because it represents, I think, an investment in the things that people care about when using Haskell in production. That is to say, how long does my system take to build? Just say a little bit about what the sort of new developments in 9.0 and 9.2 have been. Well, so linear types, many of you all know about. We mentioned it last time around. I think it's still sort of somewhat experimental feature, and I think we might yet see changes in it. But Arno and Christoph are still working hard on it. In 9.0. You may remember I again spoke about this last year. We simplified the definition of subsumption in the type system. So essentially, GHC had grown a rather complicated notion of subsumption that actually also had a semantic compromise that meant that the semantics of the program were changed by type checking. That doesn't seem very sensible. So this substantial proposal, which went through the GHC proposal process, fixed that at the cost of breaking some programs. You have to do some eta expansion, but it lays the groundwork for quick look in predicativity, as we'll see in a sec. So that, in a way, is a welcome removal of a feature, or at least simplification of a feature, something that doesn't have to happen in GHC. There was quite some big changes on the library front. There's a new I/O manager for Windows. Now, Ben, is this Tamar?
Yeah, this is Tamar's work.
Tamar, yeah. So this is a big piece of work, and you might want to say a little bit more. In fact, why don't you just speak to both of these, Ben?
Yeah. So this is actually a pretty big step in our Windows support, which has historically been a bit quirky, to say sort of at best. Console handling was very difficult. You had to run on GHCI through a special wrapper script in order for things to behave sort of as you would expect. Unicode was a bit flaky at times, especially path support. Long path support was rarely worked. And with WinIO, all of this should be gone. So it's a sort of native I/O manager using the native Win32 APIs, and as a consequence, should also be much faster. So if you are using GHC or compiled programs in a server environment with sort of a high throughput requirement, then you'll notice a pretty dramatic uptake, I think, in your overall throughput. And then GHC Big Num is sort of on a much different note. A really great piece of work by Sylvain and collaborators who have been working on trying to sort of consolidate GHC's big integer support. And there's sort of two goals there. You want to, make it easier for people to port GHC and its big number implementation to new compilation targets. And so the main target there would be JavaScript or WebASM now. So this is much easier with a consolidated code base, as it now is, and it's also much faster if you do use the sort of naive native Haskell implementation, which is BSD licensed, allowing you to avoid a GMP dependency. So this is very useful for users who in a sort of commercial environment with very strict legal deployment requirements. So I think that's
great. Thanks. And these are I think both projects in Ben are led by more or less a single individual. So it shows that single individual can make a big difference in the GHC ecosystem. So thank you very much to Sylvain and to Tamar for doing these things. I should say we're going to go fairly quickly here. So I'm watching the Q&A. So if you want to know more about any of these things, just ask, because otherwise if we go into great detail about everything, we'll run out of time way before the end. So also in 9.0, some GHC proposals got implemented. So in particular, overloaded quotes, which Matthew Pickering implemented, some better code layout, which I think just gives faster runtimes and better cache behavior. And Sebastian implemented many of the ideas that was in the paper that he led on, called Lower Your Guards, which is an ICFP 2020, is now implemented, dramatically improves performance, both performance of pattern matching, coverage checking, and also makes it work much better with GADTs and all the other type system things. So it makes it a much more, scalpel-like tool. If you get a warning, it should really be something that's wrong, whereas previously you just had to shut your eyes half the time. In 9.2, there are some further changes to the language, particularly on the records front, no field selectors, which means that you don't have to have the automatically generated top-level functions for record selectors, so that declutters the namespace a bit, and particularly this overloaded record dot implementation. I think having dot as a record selector in the language will have a quite profound psychological impact on what our programs look like and how people think about them and understand them. So I think it'll be, although it's not everything everybody might possibly want from a record system, I do think this is a real step forward. There's again a GHC proposal on unlifted data types. You can now declare a data type, an algebraic data type, to be unlifted. That means to say it does not contain bottom. That means to say that everything involving that data type is done call by value. That's a very nice additional piece of expressiveness. Another very nice improvement is that previously, if you look at index, arrays could contain arrays of values, but they were always lifted values. So if you wanted arrays of unlifted arrays, we had to have a whole new data type for that called array hash. And we had to have a new index operation for it called index array. I mean, that's just awful, right? Because they're both implemented the same way as, heap allocated box of pointers to things. So now with this change to the language, where we can have a single array data type which can contain values that are either lifted or unlifted, and a single index operation to get it. So that's really a big help. I think the change to the indexing may or may not have happened yet, but it's set up for that. Quick look, input negativity. So for a lot, I tell you, I've been trying to do this for 15 or more years to make GHC support first-class polymorphism. That is to say, we've always said you can have a list of ints, you can have a list of bools, you can have a list of chars. Why can't you have a list of for all AOA? Well, you couldn't before, and now you can. That's called input negativity, and you can see the sense in which it means first-class polymorphism. A for all type can now be used to instantiate a polymorphic type variable, and that here I just writing down the long list of papers. These are only the papers that I was a co-author on that have sort of been attempts at doing this. There are many others by other people. Finally, I think we got, it's not perfect again, but I think it's a respectable stab at doing, at least a principled take on input negativity combined with type inference. And I'm quite proud of the paper about it. Actually, go read it, ICFP 2020, if I may, don't mind jump in. But I think it will mean for the first time you can reliably write programs that use first-class polymorphism. I'm very interested in hearing from you if you start to use it in anger, but I'd love to find compelling use cases. Okay, nothing in the Q&A so far. It's mysterious. You're sort of all being very quiet. GHC 9.2 also includes the GHC 2021 flag, which is a bag of 45 extensions, which means you no longer need to put quite such a long list of GHC extensions at the beginning of your module. And people might know, okay, so they're writing in the GHC 2021 dialect. There's a whole GHC proposal about the process for doing these things. We expect to have more of those. Quite a lot of improvements on code generation front. Ben, do you just want to describe this?
Yeah, so we have now much better support for ARH64, and in particular on Darwin. And in 9.2, we're going to have a native code generator backend, which will be significantly faster than LLVM for generating ARH64 code, which would really help Apple MU1 users and other ARM users. And it's all just much more robust now. We've sort of nailed a lot of rather tricky memory ordering issues, which should make the threaded runtime much more reliable.
Right, thanks. Then the this isn't the back end, this is the middle of the compiler. Many will know about Alan Zimmerman's GHC exact print infrastructure, which enables us to take a Haskell source text and essentially spit it out again in exactly the form. So we can do transformations and modifications that mean that we know the exact character position, not only of the the variables, but also of the original keywords and the pieces of decoration that occur in Haskell's text. And this is a long process that Alan Zimmerman has been leading. Again, an example of a piece of long-term impact by a single individual. Led by a single individual. John Erickson also encouraged us and then helped execute on isolating GHCs. It's always been an ambition to separate out GHCs data type for representing Haskell programs, which we call HSSyn, into a completely separate library that's independent of GHC. So at the moment, it's not a separate library, but it is now a separate part of the namespace in the GHC's module namespace. It's in language.haskell rather than in ghc.blah. And we're trying to keep we're trying ultimately to turn that into a separate library. And that's all built on the trees that grow infrastructure, which itself is a long development path. I think there's more to do there, but we're on the path there. Ben, do you want to say a bit about profiling?
Sure, yeah. So this has actually been an area where we've done quite a bit of work, sort of a variety of people, actually. So for one, we now have proper support for pinned allocation. So if you've ever seen a pinned entry in your profile for byte arrays, for instance, or byte strings, texts, rather, those should now be handled properly, attributed to their correct cost center. We have now a great set of infrastructure for, in the form of GHC debug, which is an external tool using sort of interfaces provided by GHC for allowing the development of specialized sort of application-specific profiling tools. And so this is work that largely by Matthew Pickering, and I sort of helped a bit. And that should be really great. We've actually found it to be very, very useful in GHC itself to try to figure out where our own func leaks and unnecessary thunk allocations were arising from. And finally, we have this great HI profiling mode. It stands for info table point profiling, which is sort of a lower cost variant of the sort of cost center or heap profiler that we already have, which allows fine-grained heap profiling without the overhead of that traditional infrastructure. By sort of annotating, we profile by info tables or by object type, and and the compiler has grown infrastructure for emitting metadata, allowing you to attribute those info tables to elements in your source program. And that's also a very helpful mode that we found quite useful in GHC.
Do you want to say anything about the garbage collector and Doug's work?
Oh, right, yes, that's right. And I skipped and then not really in the profiling front so much, but more in general runtime. The garbage collector, for a long time, we've suffered from rather poor scaling due to our use of spin locks and sort of pathological behavior of those on large machines. That's been fixed by Doug Wilson. Really great change, which actually has made significant impacts in GHC compilation time, as well as sort of scaling in server applications. So we're hoping that will be sort of enjoyed by the server users, especially.
We have a question by Norman. Can you say a little bit more about how the improvements in compile time were achieved? It was faster compile time for building Cabal half a minute.
Yeah, you know better than me, Ben.
Yeah, there's a lot of, it really is in a project like GHC, lots and lots of small changes, I think, that really add up. For sure, for instance, Doug's change, while it isn't even in the compiler, made an impact, as I sort of alluded to earlier. But we've also just done lots of work to sort of optimize look at profiles and just see, we're allocating a lot here, and we don't actually, none of those thunks are even needed, right? These are things that really should be evaluated when they are allocated. And so this is you just do that, look at the first entry in the profile, the second entry. It really is just like optimizing any other Haskell program.
Sadly,
this was like a deliberate effort. We're going to tune the compiler and improve its performance, not this sort of secondhand. Yeah, cool.
Sadly, there was we'd previously thought, in years past, we thought there'd be lots of low-hanging fruit, but none of the fruit was very low. All of that had gone years ago. There was a second class of work, which was some people occasionally report programs. Indeed, we've got quite a large collection of them that show egregiously bad compilation time behavior. Where clearly something nonlinear is going on, particularly in the optimizer. And I bear the scars of this. I spent a long time trying to figure out why things are going bad here. And there were some significant changes there. So as well as average times improving, I think several extrema have got much better.
Nice.
Wouldn't you say that even some of the developments that you mentioned, like GHC debug and the HI profiling, have at least partially been motivated specifically by improving GHC itself?
Absolutely. Yeah. No, I mean, this is, in a program as large as GHC, it can be rather hard to make sense of profiles. And especially when those profiles are actually changing the behavior of the program that you're trying to measure, as the cost center profiler does. So, HI profiling has been very, very helpful in getting a better sense of what the actual cost structure of the compiler is.
Okay. There's also a question by Christian. Does Christian want to read it himself?
Yeah, sure. So does the improvement to GHC mean that I no longer need to limit the number of threads participating in garbage collection on large machines? Okay.
Yeah, it really depends. I would just say measure. There are cases still where synchronization is always going to be expensive. We do it more efficiently now, but it is still expensive. And if you have 32 kilobytes of allocations that 32 cores are trying to all collect, that's not going to be a very great. It's not going to lead to a very efficient runtime. But if you have a large nursery and you have lots of cores, then it might make sense to actually use all of those cores for GC. Do report back when you find out.
It's probably time to try it again. Is the conclusion? Have another go.
That's right.
On the GHCI front, Loiters made the bytecode interpreter support more of GHC, particularly unboxed tuples. I think was a big thing. So that was that's very helpful. And Roland Sem has worked quite a bit on the GHCI debugger, which I'd like to call out here that anybody listening, anybody who's interested in debugging Haskell programs, the debugger could really do with some love, right? And Roland has been giving it love, but he's sort of a bit on his own. So I think he'd love to have colleagues to help there. And it's a bit, the debugger has never, for a long time, has lacked a champion, somebody who really understands it and makes it better. So please, could you be that champion? That would be great. Let's see. Here's a quick skirmish through. Oh, that's 9.0 and 9.2. Quick skirmish through things that are sort of ongoing at the moment, that are kind of in the pipeline, as it were. And this is even quicker than the things we've been talking about. Sebastian's working on, has been working very, very consistently actually over time on better analysis, strictness analysis, demand analysis, and CPR analysis and boxity analysis now. So lots of stuff that Sebastian's been working on. Andreas has been working on some back-end stuff, particularly noting that in some performance critical code, we sometimes have got trees with strict fields, but we're nevertheless executing redundant instructions to do tag checks. He's working on eliminating those. That turns out would make a measurable, quite significant, like 10 or 15% improvement in execution time in some of these critical loops if we can do that. Some of you will notice that programs that use a lot of type families compile very slowly, and that's because we maintain all of those proofs that the type checker generates right the way through compilation. And I was working on some way to elide those in type family heavy programs. Divam and Matthew are working on improving parallelism in compilation. Well, quite a bunch of other people. I think there's a whole talk that Jeff Young is giving later with Richard about making GHC run faster, I think. Is there anything else to say here? No, I think then Alfredo's been leading a project with Richard on turning GHC's error messages at the moment are really strings. They're not quite strings, they're these stock things, but they're basically unanalyzable except by some kind of, like something that's akin to screen scraping. So what we're doing over time, but actually it's going quite quickly at the moment, is to turn all those error messages into constructors of an algebraic data type or a collection of algebraic data types. That's an ongoing project for which more people can help with, because there's a lot of error messages. So now the pattern is established, other people can help with saying, I'll do the ones for the renamer or for part of the renamer. That would be really helpful. Ben, do you want to say a bit about this, how to reinstall a GHC?
Sure. So a lot of these developer experience tasks really come down to how can we better integrate HLS and IDEs in general into GHC and make them sort of first-class citizens. And Zubin has been working on two facets of this. So the first here, we're trying to move a Haddock name resolution, which currently lives in the Haddock executable in the Haddock library, into GHC proper, and then allow those names to actually be encoded along with the documentation in interface files, such that a user like HLS only needs to link against GHC to actually get full documentation, including like the hyperlinks within that text. And so that will allow really great documentation experience. You'll be able to mouse over an identifier and get its documentation, and click on a link to a related identifier and that sort of thing, what you'd expect from a sort of modern IDE experience. And secondly, one of the sort of tricky bits about GHC's installation or deployment model currently is that really the GHC library, the library that the compiler is built upon, is actually kind of the root of the package database, and you can't really reinstall it in any meaningful sense. You cannot type cabal install GHC and expect it to do something useful. We're trying to change that, and that actually makes it much easier, again, for users like HLS and other API users, which may want to decouple the versions of libraries, like core libraries like containers or text, from those used by GHC. And also it allows us to do things like shrink the bin dist size, since we no longer necessarily need to ship profiled versions of the GHC library or other core libraries, since all these things can be, again, built by the user when they're needed. So that's a really nice, it'll be a nice improvement as well. And finally, Adam has been working on improving out-of-the-box support for statically linked executables. This is, of course, a common requirement in deploying applications today, especially in servers. And GHC is, it's been possible, but it's never been so easy. So we're hoping that, with Adam's work, this will become sort of, ideally as easy as sort of Go, right? You just say, I want this a static executable, and out pops a single file, and you can just run it anywhere you feel necessary.
There's a question about the haddock improvements by ETSCO. Perhaps we can get ETSCO on the stage as well.
Mm-hmm.
Okay. Oh, yeah, but I can just also answer. ETSCO, is there something you want to clarify? Or
just, I mean, it's often annoying, like if a name gets re-exported and re-exported, like you want to import it from the right place, but it's like haddock supports this, right? By saying this is not where you should be importing it from. It'd be nice if GHC would understand that.
I'm actually going to have to get back to you on that one. I don't know at the moment. Yeah.
Sure.
You can carry on, Ben.
Yeah.
Sure. Andreas, I'm conscious that we're sort of probably coming to the end of our original time slot.
No, you may not have heard that in the beginning. I said that we basically can use the entire break, but not more than that.
Yes. Where does that take us to?
That means we still have 25 minutes.
Okay,
great.
Right.
Okay.
So keep going rapidly.
Yeah. So, right, another of these sort of in the pipeline projects is sort of a deprecation and an eventual removal of the make build system. We'll come back to that later in this talk. So we'll sort of leave that for now. But, let us suffice to say that we could really use help in this regard. So if you do have some time or inclination, please look at the make removal milestone in GitLab. And there are plenty of, sort of low-hanging fruit tasks that I think would be easy to pick up. Andreas has been working with Hazura to help enable native statistical profiling support. There's a blog post on the WellType blog about this a few weeks ago. We sort of, it's a rather tricky situation, but we're trying to work through, what is the best way, most usable way to introduce native statistical profiling support. In particular, the LLVM backend, actually, it turns out, is rather hairy, since it requires, LLVM really wants control over the stack, and that's something that we've still trying to work out how to deal with. But if you do have LLVM experience or know a fair bit about LLVM's internals, then do get in touch. We want to know what's possible and what is not here. Alex Dudarenko has been working on improving code generation for non-allocating case alternatives, and this is another of these cases that if you in tight inner loops can really make a big difference. Sort of eliminate one instruction per one branch per loop cycle in many cases. And Simon, you want me to continue?
Yeah, keep going.
Yeah. So John and Sylvain have are continuing with this. At this point, I think three or so year long journey to improve GHC's cross-compilation story. And at this point, we're actually getting very close, I think, to having a runtime retargetable compiler. So, maybe by this time next year, perhaps, we'll be able to sort of be talking about how you can pass a -- target flag to GHC, and it will, sort of produce an ARM executable on x86. We'll have to see. I don't want to put words in Sylvain's mouth, but we're getting quite close. The design is at least quite clear now. As mentioned earlier, Tweag is continuing work on linear types and sort of pushing linearity further down the compilation pipeline, allowing us to be more certain of linearity preservation in core. Sven has been working on two rather exciting sort of user-facing features. So for one, unwinding infrastructure for the Haskell stack that is sort of not dependent upon the architecture or things like Dwarf. So allowing anyone with a Haskell program to be able to unwind the stack and therefore derive a backtrace of the current state of their program. And that fits really nicely with another piece of work that he's been undertaking, which is prototyping the backtraces in exceptions proposal. And that's something that, again, has been sort of a long-standing paper cut in our developer experience that I hope we'll be able to resolve in the near future. And Hakata has continued to do great work in facilitating documentation and has also picked up work in maintaining Haddock, which has sort of been had not a lack of maintenance, but certainly a more it's more active now than it has been in a very long time, which is really great to see. I think the next slide,
Great.
then, Simon.
Yes, I think then we also wondered whether this is a good moment for anybody who's in the audience here who's got stuff that they're working on that they just like to share with other people, just sort of stick your hand up, or maybe you type a question in the Q&A, say I have something, and we can Andres can promote you to tell us about it. But I'm struck by looking at this list, just going through this, I was preparing for this talk, what a large proportion of all the stuff that people are working on is to do with the ecosystem rather than do with the core language itself, or even its optimization pipeline. It's to do with you know, how to do targets or cross compilations, or working on different machines or in different environments, or interacting with different tools like the Haskell language server, or dealing with exceptions or backtraces. Or it's striking, and this of course are all driven by user needs. So I think it's a sign of maturity. But it's a striking difference, I think, between this and maybe the same talk 2 or 3 years ago. Anybody want to offer anything?
I'm not seeing.
No, me neither. Maybe you did a really good job of shaking the bushes, Ben. Ben really sort of constructed this long list. If anybody's got anything they want to raise, then just type something in the Q&A. Probably not. I can only watch one at a time, rather than the chat. While you're doing that, let me just say very quickly about the GHC proposal process. You will know all about this. This is how new user-facing features end up in GHC. It's been it's something that everybody has to follow, you know, myself included. And here's some quick statistics about it. We've had nearly 400 proposals now, compared to in total 330 last time. So another, what does that mean? 63 this year alone. Quite a few of those are under discussion. Similar number actually in the under discussion framework that were a few years ago. Some being reviewed by the committee, 9 at the moment. Overall, 92 have been accepted compared to 75 last year. A couple more have been rejected, and surprisingly, only 2 more have been implemented. That is what the website says, but it seems a little bit low. But maybe, guys, you know, everyone listening to this, get on and implement some of these things. We know what's happening. I can't accept all these things, then have them unimplemented. Here's just a list of what was accepted in the last year, very quickly. Quite one about process, the GHC 2021, indeed 20X framework. Quite a few about syntax, you can see listed here. A few about types, of which probably most are kind of filling out the envelope gently, but the big one is support for the design of dependent types, is a proposal you might be interested to read, because it includes a fairly fleshed out description of a sort of roadmap for the direction in which we might fill out GHC in the coming time. There'll be subsequent proposals to give details of that. A couple of things about primitive operations, including something for delimited continuations that feeds into, I think that may be part of this stack unwinding thing or related to it, and something that Christian proposed, an opaque pragmatism, has a particularly relevant for Clash, but I think be useful for other people as well.
Yeah,
few of the people on the committee.
Clarification on the proposal status on the chat. Perhaps he wants to put that in the live stream as well. Joachim, do you want to come on stage?
Yes, Joachim has minor clarifications. Joachim, are you here? There he is.
Yeah, I guess this was just clarification that I thought would be passed in the background to save time, but total PRs, not all of them are proposals, some of them just updates to files. Some of these updates to files are adding the implementation tag, which requires somebody to do it. So if anybody can do that, and that means the implementation number is probably higher. So if the first line looks better than it should look like, the last line looks a bit less impressive than it should be. But minor details.
Okay, good, thanks.
And Christian put something up as a question, which I think is like a response to Simon's call for other people to speak up who are working on something. So perhaps Christian wants to.
Yes, Christian, do you just want to mention about the opaque pragma? I wasn't planning to, since you're here.
Yes, perhaps you can.
Can you promote him?
I cannot, but Ning Ning can. He's doing that in the background.
Right.
But otherwise, we'll just highlight it. Oh yeah, okay.
Yeah. This is just responding to Simon's call to tell people what I'm working on. So it's the opaque pragma, and it's Yeah, if you really want GHC to leave your function applications alone, then you have to add a opaque annotation to the function that's called.
Yeah,
there are some
useful.
corner cases where GHC still touched it, and opaque will make sure that it really doesn't.
That's useful when you've got sort of something that isn't quite an FFI call, but it's something which you're going to implement separately. Isn't that right?
Yeah,
in particular in Clash.
Yeah, maybe also for rule matching, if you don't want a rewrite rule to not fire because it got replaced by a specialized version of a function.
So I think that's it for sort of the process of language development. Here are the people on the steering committee. So thank you very much to the people who are doing this work, because it's quite taxing sometimes. There's quite a lot of work involved in evaluating these proposals. So thank you very much to all of these people. Ben's going to say something about DevOps, but before you do, I just like to sort of reflect and say you can see that there's a lot going on in GHC land. There really is, and a lot is going on because you, all of the people on this call, in this session, are doing it. So thank you so much. It's very much in a sort of ferment of active development. That's the way I think we all like to see it. But the focus of the ferment, I think, has shifted a bit more towards consolidation and making it useful for production, and a bit less towards let's keep adding new features. New features are being added, but there's a lot of consolidation going on as well. DevOps stuff, Ben.
Yes. All right. So next slide, if you can, Simon.
Yes.
All right. So this year has actually been. I don't think there has been a year in my memory that we've had more GHC releases in 12 months than the last, and that's not necessarily a bad thing. But I will say that we would like to reduce this number again. So really, this all began with GHC 8.10, and really just going back a bit further, 8.10.1, where we looked at the roadmap of Apple's M1 hardware, and we said it really is important that we start to prioritize ARM and ensure that GHC can utilize this new hardware and run on this new hardware, since a lot of our users do use Darwin. And so we sort of started the 8.10 series with the expectation that, we're going to try to start releasing a compiler in get a good release out there, and then we'll backport our ARM, some form of ARM support when M1 is available, and we've sort of stabilized the ARM Darwin support after the 8.10.1 release. And so that actually happened in 8.10.5. There were a few releases prior to that. Windows has been another area where we've been trying to sort of improve things. And so there's been quite a bit of work to stabilize the linker and GHCI experience on Windows. So we had 8.10.3, largely Windows and ARM related things. 9.0.1, which was admittedly, it was so we have this time-based release cycle, and as I'll discuss later, it's been challenging to keep up. So it was an imperfect release, I would say, at best. It had quite a few performance regressions and a few bugs that you cannot catch all bugs, but arguably it could have been better, and I think that it's something that we're going to have to improve in the future. So we've been sort of quietly advising people to stick with 8.10.0 or the 8.10 series until 9.0.2 is out, since many of the issues that we saw in 9.0 were actually ARM issues that we also had to fix in 8.10. So what we've been doing up until very, very recently has been focusing on 8.10, trying to get all of those issues that we've found in ARM and the Darwin support, our new Darwin support, ironed out, and then with the intent of then backporting them, turning our focus to 9.0, backporting them all to 9.0, and then to 9.2. And so that's where we are currently. So we had 8.10.4, just more stability fixes. 8.10.5, we finally introduced Apple support on ARM, and then 8.10.6, and then very, very soon 8.10.7 will hopefully be the actually next slide, Simon, if you can. There we are, the end of the road. We're hoping for 8.10, and this is I think the first time we've hit a 0.7 release, and I hope it's the last in quite a while. But we do have at this point a pretty good story on Darwin, I think, ARM Darwin. With 8.10.7, and moreover, this is sort of one of the sort of reasons why we've had the 8.10.5, 6, and 7 have all been due to various quirks of binary distribution production. And that is because we've actually been working towards moving away from the make-build system on Darwin and Windows for a release now, but now with 8.10 also on Darwin, to Hadrian, which is our new build system, which allows us to do a number of things to improve binary, thank you, our binary distributions. Yeah, that's all right. So we have
by the way, 10 minutes to go.
Okay, yep. So coming soon, 9.2.1 and RC will be out perhaps today, actually, and with 9.0.2 shortly thereafter. So that will introduce, again, ARM Darwin support in the 9.0 series and fix many of the bugs and performance regressions that we've seen in 9.0.1. Next slide. So what to do about 9.4? So as I sort of mentioned, the keeping up with the release schedule has been challenging. Right now we have essentially 4 active branches, 8.10, 9.0, 9.2, and master. And that's a lot of backporting, a lot of work that needs to be done, and a lot of juggling to see, has this bug been fixed in which branches has bug A, B, and C been fixed in, and making sure that they're all fixed consistently. And in part, we got into this situation because of sort of accidents of history. I mean, we have 9.0, we decided keep alive. We was going to be a blocker for 9.0, and we would not release until that was fixed. That took a fair bit longer than we expected. Similarly, 9.2, the ARM Darwin support ended up being much larger in scope than we anticipated. And these two are in principle, these two considerations are in principle sort of one-time events that should not happen again. But, it seems like every time that, there's always something. And so there's this tension between predictable timing and releasing a dependable compiler. And the time-based release schedule that we have currently is very much focused on the former. And I'm there's sort of general concern at this point that it may be too much towards the former, because we haven't even been maintaining predictable timing. We've not even delivered in that first goal. So the plan that we sort of that I'm thinking might be appropriate at this point would be to try adhering for one more cycle, trying very, very hard to stick to the release schedule as proposed, and then if there's yet another thing unexpectedly pops up, then we can reconsider the schedule.
Andreas asks whether we might consider a more Rust-like release model, whatever that is.
Yeah, I think that sounds difficult in our case. Rust has a very fast release cycle. At the moment, I don't necessarily, and they also have quite a different story towards stability of interfaces and of the compiler itself. So it's an interesting idea, something that we could discuss, but I think it would be, there are questions that need to be answered there. So, right, as I sort of made reference to earlier, we're finally moving away from make, and this has been 5 years coming at least. As of 9.2, Hadrian will be used to produce the Windows and Darwin release artifacts, and this is great because it allows us to eliminate the make build system, which has been a maintenance challenge, and especially when you have to maintain then Hadrian on top of it. It's been a lot of work. So with the goal here, 9.4, make is gone. We will see. But there's lots of work to be done. So if you want to help in this, please, do look at the make removal milestone on GitLab in the GHC project. There are lots of issues there. Lots of them don't require a whole lot of knowledge of the compiler, and we'd be happy to help, get people sort of up to speed there. If you are a GHC developer already, as you probably are if you're here, then please, we could use your feedback. If you use make, please try using Hadrian. And if something doesn't work or something doesn't work as you'd expect it to or like it to, just open a ticket, and we can try to address that. But do know that make, the days are numbered, so it's worth worth offering your feedback now. So, in addition, our CI infrastructure continues to grow. We at this point have, I think, nearly 12.5 sort of routine validation jobs, and that's great because it does allow us to catch more bugs. It's also more work, and if we have volunteers to help cover sort of especially configurations that we don't yet cover. and you'll see the blanks in this chart point to those. Then please be in touch. Very, very happy to help people sort of claim ownership over parts of our CI infrastructure. If it's going to be a sort of all-encompassing high coverage piece of infrastructure, then it can't just be us. So Hekata is a great example of this. She added support for stylistic linting and into our pipeline. Moritz Angerman has been doing great work in optimizing the jobs to reduce the pipeline durations, which has been very, very helpful. But there's lots more to be done, so please be in touch. As always, we're greatly indebted to our sponsors. We have Packet, a hosting provider who's been very, very generous in providing compute capacity for us. SimSpace has offered some Darwin machines. Azure now supports us for cloud capacity, and Moritz as well has been very, very generous in providing us with Darwin and Linux capacity. And sort of lastly, Simon at the sort of the beginning of this talk laid out some of the improvements that we've been making in the area of compiler performance. And it's great that we can make these improvements, but we also really want to make sure that we don't lose them to changes. And that's something that you have to actively try to ensure that performance does not regress. And so we've been making a conscious effort here to try to improve our infrastructure in this area, and largely due to Matt Pickering again. We have now a really great dashboard for monitoring compiler performance using the various data sources that we've developed in our CI infrastructure. So head.hackage now provides compile time statistics, and NoFib and a GHC test suite give us both runtime and compile time statistics. And these are all plottable and analyzable via a nice interface, Grafana now. So that's been very, very helpful. And in the next sort of step, the next logical evolution of this infrastructure is going to be then to expand a little bit further the head.hackage infrastructure to then run a very small fraction of our runtime benchmarks. So for instance, vector and text and byte string are all important enough packages that we really want to make sure that they don't regress in runtime, and record those in the same sort of format, and integrate those into our dashboard and monitoring.
Yeah, because we have sometimes found when we make a release and somebody says, "Oh, but text has got much slower on this benchmark." Yes. We think, "Oh, I wish I'd known that earlier." Or indeed, I wish I'd known that around the commit that caused it to happen. Yeah.
So again, this is an area where help if you have some time and DevOps experience, or even not, please be in touch. We're happy to get you up to speed and allow you to contribute.
So there we are. 3 minutes ago. Any questions or observations from anyone? Because I think that's all we had to say. But I do want to stress again. You can see how much is going on in this space, and it's all being done by volunteers. There's very few. There's a lot of coordination, a lot of volunteers putting a lot of time in, and we're so grateful to you. And it's and I think it's a shared endeavor that is really paying off. People are using Haskell for big mission critical applications, and they can only do that because you're putting in all this work. Thank you.
Yeah, let me also join thanking all the contributors and all the sponsors, but let's not forget also thanking Ben and Simon, who are not just like implementing lots of new features themselves, but also doing an incredible amount of work year after year, coordinating all this and making it possible. So thank you for the impressive overview.
That's great, thanks. I spend a lot of time in code review these days rather than writing code.
Yes, but even that, I mean, it's always like, yeah, I mean, somebody posts a rather complicated issue, and 20 minutes later there is a detailed analysis by you. I honestly don't know how you do it, but but it's great. Thank you. All right. I guess that's it for the session. I'm sorry that we've taken away most of your break. I think Etzko announced earlier that we're going to have a 5-minute break anyway before we start the next session. And yeah, that's it from my side for now. Thank you again.
Thanks, everybody.
Great. Thank you, everyone.
Good. Cheers.
Bye.
So yes, we're going to. Oh, did Nina already do it?
Yes, we are going to take a break for like 5 minutes, and our next session will start in 5 minutes. So thank you everyone for joining this session.
Hello, everyone. Good. Welcome again for the next session. I'm Dan Lyon. I have a very fond connection with the Haskell Implementers Workshop. I remember at the end of the 90s, one of the first Haskell Implementers Workshops with I think Simon Marlowe organized it in Egmond in the Netherlands, and there were about like 15 people. Everybody knew each other, and Haskell was still very small. And look at it now; it's just amazing how much it's grown and the interest and the ecosystem. So that's really good to see. So today, the first talk is by Chris Smith, a software engineer at Facebook, volunteer math and computer science teacher, the author of the Code World platform, a so-called amateur mathematician, but published. So I don't know about the amateur part, and Haskell enthusiast. And he's going to talk to us about testing Haskell with mocks. Take it away, Chris.
Hi. So I think it's great to be with all of you. Yes, I am Chris Smith. I'm with Facebook for another 4 days, though, so I wasn't going to say that. But nevertheless, it's good to be here. So I'm going to talk to you about testing Haskell with mocks, and there are basically two halves to this talk. It's sort of the opposite of the last talk in that I'm about as far away from GHC in my topic as anyone's going to get. So the first time I'm just going to talk about some developer tooling I've been working on, which is a library for mock testing in Haskell. And then the second half of my talk will be sort of an experience report. And maybe if you're looking at this from a implementation of GHC and compilers perspective, there will be some interesting insights there in terms of like what I ran into in implementing this library, what are the important GHC features and type system features, things like that made this possible, things like that. So to get started, the part one of my talk is sort of an introduction to mock testing in general and the HMock library. So in general, Haskell has a pretty good story for high assurance programming, right? It's purely functional. It has property testing with quick check pretty solidly built into our culture. We can do a lot of unit testing of purely functional code with, and it's a really nice experience because there are no effects. There's, there are a lot fewer corner cases and state mutation, things like that to handle. We also, most programming languages have integration testing, and Haskell can have integration testing just like any other programming language. But there's a bit of a gap somewhere in the middle, and that is a very complex code that's high effects, but where you want to build cheaper tests than integration testing. The standard solution to that in a lot of programming languages is to test with mocks. In Haskell, there's not really been a great story for testing with mocks. There have been a few libraries leading up to this, which I'll talk about later. But I think HMock I built to fill in this gap. So I'm testing effectful, complex code, and I'd like to test it in a highly performant way that's faster than integration testing and simpler than integration testing, as well as more isolated, so that my failures fail the right tests instead of just failing everything. So Haskell does have a little bit of a picture for mock testing, but I think it's less involved than some other languages. So outside of Haskell, there are widely used big mock frameworks, which are very feature-filled. Gmock in C++, Mockito in Java, Jest for JavaScript, and so on. Haskell has a sequence of libraries that are sort of inspiration for what I've done that I'd like to acknowledge. First, Test Fixture and Monad Mock, both I think libraries by Alexis King, sort of built the framework for mock testing in Haskell. Mockezo sort of modified Monad Mock to be a little bit more extensible in the sense that you can combine components that are independently mockable into tests that work with all of them without a lot of overhead. HMock kind of extends that. There's also a few other notable libraries, polysemi mocks, which is sort of monad mock for polysemi, typable mock, which is a sort of different approach to mock testing, but involves a lot of runtime lookup of functions in production code. So not the direction that I was necessarily looking to go. But HMock sort of extends a lot of this picture, and I'd like to tell you a little bit about how HMock is different and what it does differently, but I think the best way to start there is to just show you what a test with HMock maybe looks like. So here's an example on the left of a type class, and this is not using HMOC at all. It's just a standard MTL style type class called Monad Chatbot, which is able to do things on maybe IRC rooms or something like that. Join a room, leave a room, send chat, and poll for chat from other users. The line at the bottom there is a piece of template Haskell splice that is part of HMOC, which just says, make this mockable. So I've taken the type Monad Chatbot and I've just used make mockable to say, write a whole bunch of boilerplate for me so that I can write tests against this interface, which do not rely on having an implementation of that interface. And then my test implementation sits over here on the right. And basically, this is what mock testing is all about. It is not the same as testing with fakes, where a fake would be, say I've got like a file system and I want to fake it with an in-memory map or something like that. In a mock test, what I'm doing is I have no implementation of my interface at all. Instead, I'm just going to tell the interface how to behave for the purposes of this test, and then run the test and expect the interface to behave that way. So there's a couple of primitives I'm using over on the right-hand side here. Expect any says, expect any number of calls to this method. You'll notice that poll chat here is capitalized, a capital P, rather than the poll chat from the type class. And that is actually a GADT that is written by Monad Mock that captures all of the possible operations into this GADT type. And so this is saying, expect that poll chat will be called using the parameter room pound Haskell. And then in this case, it will actually give 3 different behaviors. So the first time it's called, Alice will say hello. Second, Bob will say help. Third, Chelsea will say leave. Next, I'm actually going to expect the intended behavior, which is that help call should result in some help text being sent. So that expect says that this must be called exactly once. Different from expect any, in that expect any says could be called 0 or more times. Expect says exactly once. And so I'm going to expect that this gets called. The third line is actually really interesting here. It shows that that I can say expect that I'm going to that join room is going to be called with any parameters at all. So this join room with an underscore at the end of it is actually a matcher rather than an action. It's another GADT that's defined by HMOC and says instead of giving the specific arguments that I'm expecting, I can give predicates for these arguments. And so anything is a predicate that says anything can be passed in. And then instead of this vertical line dash greater than, which says maps to a result, I'm using this sort of monadic version, which is going to expect a Cleasley arrow. So it takes the parameters, the actual parameters at runtime, and then produces a result in the mock-t monad. So in this particular case, I'm using this to say anytime you join a room, then I expect you to leave that same room, which is a nice invariant to be able to express in my test expectations, which is rather dynamic, something that is a little bit different from what you could do in Monad Mock or one of these predecessor libraries. And then I just simply call the chatbot implementation, and when it uses the operations from Monad Chatbot, the expectations earlier will be fulfilled by the library. So that's basically how Monad Mock is working. A really good question is why I would create a new Haskell mock framework. And I think there are basically 2 answers to this. One is that there's a danger of over-assertion if you have to specify too much in a mock framework. So a lot of mock frameworks that have previously been written by Haskell work on this theory that you should list all of the methods that will be called from this interface in order with the exact parameters that will be passed in. This leads to what's called change detector tests, tests that fail anytime anything in your implementation changes. The result of that tends to be that test failures are ignored, or I've seen developers who have these sorts of tests go in and just say, oh, I'm just going to change the test to assert exactly what I observed happening in my test case without thinking about what the correct behavior is. So these change detector tests tend to create a lot of work for developers, which results in the wrong responses to test failures. Also, I wanted to limit overstubbing by allowing you to put a lot of logic in responses, which can actually encode realistic logic for your implementation in some cases. So if you have to specify the exact response every time a method is called, then your tests can assume too much and miss difficult cases. So we'll see how more powerful responses to mock calls can result in better test cases. One of the things that or one of the core ideas that solved one of these problems is that that I've built a very expressive language for expectations in mocks. So in this case, you can expect something to happen not just once in order, but any number of times in any order. You can expect any of a few different options to happen. You can expect something to happen multiple times. So there's a rather expressive and composable language for building up a set of expectations, or a sort of execution plan or script for what you intend to happen in your tests. This is a relatively complex language, or not really all that complex, but it compiles down to a simpler core language for expressive expectations, which is actually built on a paper that's cited at the bottom of this slide. So this is Svenningsson et al., notably including John Hughes of QuickCheck fame, working on this paper as well. And basically says there are a few different sort of ways that we can take two primitive expectations, the empty expectation that expects nothing, and then a simple single-step expectation. And then we can combine those two primitives using a few operations. So a sequencing operation, an interleaving operation, which allows the steps to be performed interleaved between two different options, a choice operation, which is written as A plus B over on the right-hand side. So this notation on the right-hand side is the notation from the paper cited at the bottom, although I have added one thing, which is an interleaved repetition. The A hash sign operator does not exist in that original paper. There are actually two kinds of repetition you can have. You can have each thing must happen consecutively followed by the next one, or you could have any number of these can happen and interleave with each other. So all of these are sort of expressed in the core language within HMOC, and that surface expectation language gets compiled down to this core language. The nice thing to note here is that each of these expectations on the bottom is very composable, in the sense that I can take a any of and interleave it with something, and then I can take that and use sequencing to say then something has to happen after all of that complicated piece at the beginning. And that allows me to actually express pretty succinctly a lot of really interesting invariants about how my program should behave. The other major change was, I mentioned a little bit earlier when I said that there is an action type which represents individual calls with explicit parameters, and there's also a matcher type which represents calls with predicates. So if I'm expecting a call, I don't necessarily have to say, here's exactly what will be passed into this function. I can say, here are some predicates. And there's an entire language in this library, which I'd like to split into a separate library, to be honest, of explainable predicates. So these are essentially functions from A to bool, which can explain themselves. So they have a show instance, they have an explain method, which can examine an individual argument and explain why or why not it matches. So all of these explanations are for better error messages in test cases. But you can take these predicates, of which there are a good 50 built in, and you can write more against the interface and use them to provide, to match calls according to lots of conditions. So that's essentially the HMOC library. There's a little bit of a few limitations and some future work that I would like. Polymorphic return values are very difficult for mock frameworks. HMOC allows them, but requires a typable constraint. Otherwise, you cannot mock a method with a polymorphic return value if it does not have a typable constraint. I don't see a good solution to that, but I've thought about it for a long time. If someone does, I'd love to talk to you. Another thing I'd really like to see is integrations with more of the rest of the Haskell ecosystem. I'd love to see HMOC work well with polysemi and fused effects and servant and Haskell. I think something like that could be extremely valuable. If I could say, I've defined my interface in servant, now I'd like to just make it mockable and then use something like HMOC. So I think each of these may require a different code generator to generate different code, but ultimately can use a lot of the same primitives within HMOC, the same expectation language, things like that. And I'd love to see that kind of work happen. I'd love to collaborate with someone on that kind of work. It's really sitting at the edge of what I understand how to do at the moment. So again, get in touch with me if you're interested. I also intend to split these explainable predicates into an independent library. I think they're very useful for unit testing libraries in general, and not just for mocking. Part 2 of my talk is sort of an experience report on the implementation of HMOC. So I'm going to talk about what the challenges are and what some of the key bits of GHC and some of the experiences that I've had that may inform other Haskell development. Mock systems are really interesting, and they seem to inherently stretch the bounds of programming languages. So, for example, Mockito involved actually generating Java bytecode at runtime in its implementation. The implementation of C++ GMock, it has a bewildering mix of C preprocessor, template metaprogramming, stretches features of C++ templates that most people don't know about in order to make things work correctly. On the HMock side of things, I relied heavily on template Haskell. There are about 1,000 lines of template Haskell code in the HMock implementation. I could have done the same thing, and it would have been maybe a little bit easier using a GHC source plugin, because I ended up implementing a bunch of things like type unification, type variable substitution, etc., which are probably implemented within GHC as well, and potentially could have reused those implementations. However, plugins are a little bit harder to use, as well as harder to keep compatible with a wide variety of GHC versions. So I ended up re-implementing a lot of things in template Haskell. A big part of the challenge is working with arbitrary user type classes. So I cannot assume anything about the type classes that I'm testing, because I don't want to make assumptions about production code in order to be able to build tests for it. So in general, I'd like to make HMock work with as many different user declared type classes as possible. And that leads to a lot of the challenges of how do I handle, rank n types in an API in HMock, things like that. So some key GHC features that were used, obviously template Haskell is used for the code generation for boilerplate code, which is really critical. GADTs are used for the matcher and action, as well as type families. Those are associated types so that there can be a different action and matcher type associated with any type class. So those are critical extensions that were used here. Data kinds were used to add some additional type safety, so I can actually tag the constructors of the action type with which particular method name was used, which allows you to write complete lambdas that are not that will not fail pattern matches in cases where I know already what constructor is used. Rank n types are used for polymorphic arguments. So anytime you have a polymorphic argument, it turns into the corresponding predicate turns into a rank n type. And then type error was really useful for getting better error messages on this. So these were all very useful things. The Haskell type system was indispensable to me in trying out new designs. I was very much able to just sort of have an idea, make a few changes, and then spend 2 hours chasing type error messages, finding out where those occurred. Haskell language server was also indispensable in this, in that it was able to surface those type error messages easily, and led me to a lot of productivity in doing that. So, like, props to Haskell, to GHC, and to Haskell language server for making development really possible for a project on this scale. The limitations on impredicative types were an issue. So Simon was saying earlier he was interested in people who feel the pain of impredicative types. Because rank n types are used for a lot of APIs, then the corresponding predicates for those fields turn out to need impredicative types. Right now, rank n types in an API are not mockable. And so I would like to look into using maybe GHC 9 in the future to solve that problem. Another thing that I found myself wishing for was optional type classes, cases where I can say, like, hey, if GHC knows that there's a show instance for A, then it should choose this implementation. Otherwise, it should choose that one. I've thought about maybe I should write a GHC proposal for this. Crucially, those implementations are equivalent up to the quality of error messages. So it's okay with me that, the behaviors are different, but they're different only in that one of them fails with a better error message than the other one. So things like this, I think this particular thing, in fact, would have solved a lot of problems for me. Let's see, template Haskell, about 33% of HMock's implementation is template Haskell for boilerplate generation. The template Haskell API is very limited, and so I ended up re-implementing a lot of things, as I mentioned earlier, type unification, variable substitution, and so on. Also, testing is very difficult with template Haskell. It is hard to test your failure cases because they lead to build failures. And it's also hard to measure test coverage with HPC. My solution was I was actually able to mock the quasi-monad using HMock itself. And so HMock's test suite uses itself to mock the quasi-monad and run template Haskell code at runtime rather than at build time. And this ended up finding lots of bugs. And then the last comment I have is GHC compatibility. I'm targeting GHC versions 8.4 through 9.0. By far, the hardest GHC to keep working is 9.0. So I'm developing with 8.10. So I don't consider that one of the candidates because everything that I try builds in 8.10 first. It typically then builds reliably back as far as 8.4, but 9.0 is constantly breaking. And the cause of this is simplified subsumption. The fix is, in my mind, to make random changes to the code until it builds. I know that there's probably a more disciplined way of looking at that. But at this point, I've not figured out how to get my head around what does and doesn't work in the presence of simplified subsumption in GHC9. That's too bad. On the other hand, I do want impredicative types, so it's a trade-off. And thank you. I am now open for questions. Thank you for your time and attention.
Thank you so much, Chris. So we have time for some questions. I don't immediately see a question. I had actually a question. I love the experience you shared about impredicative types. So if you go back a few slides, you showed the predicates with the higher rank type in it, like here.
Yes.
The type you show here is like for all A to bool. So for any A, give me back a Boolean, right? So for such predicate, there are not many implementations, right? Is it a simplification here or?
Oh. Yeah, I wrote this particular example very quickly, and you're right. There are only 2 implementations of this particular rank n type.
Right. And in a total language, it would only be 1. So okay, that's interesting. So, but actually, that goes back to one of the first slides. You showed the interesting matcher. I think it's the first slide, even right here, right? The expect any.
Yes.
So there, the join room like gets anything, and then I saw you expected to leave the room, right? But that leave room could happen much later. So maybe can you explain how that works here, or is it the idea that you just join and leave?
Different expect calls are by default interleaved with each other. There is no ordering expectation. If I expect something and then on the next line I expect something else, then those 2 expectations can be fulfilled in either order. If I would like to expect things to happen in sequence, then there is a combinator called in sequence. And so I can just say expect, and then the argument to expect would be in sequence, and then have a list of things that would occur in that sequence. But that's something that I would have to explicitly say. And that's really important to me. I think if you default to having these ordering constraints between expectations, then you end up defaulting to over-assertion. And over-assertion is maybe the enemy of mock testing largely. So it was important to me to make as few assumptions as possible about the execution plan unless you explicitly state them. So these 3 expect statements do not have any ordering, or these 4 expect statements, if you include the leave room, do not have any ordering constraints between them.
Right. That's very powerful, right?
Yes.
So I had one, since I don't see any, is there anyone? Then I add one more question, actually, because I think it feels like you're specifying really rich state machines, right? Do you know about the relations with session typing here?
I have not thought about any relationship with session typing. No. That's an interesting question. Right now, the state machines have only one state. So essentially, well, I suppose that they have one state, except that there are error messages if you have a call that's not expected. So there's just one state type that says, there's a list of expectations, and they can be, or not just a list of expectations, a rich structure of expectations using. I even showed the GADT.
Yeah, that's amazing, right? That's really rich. So I'm not sure that could be expressed anyways. Yeah. Simon, do you want to ask that question? So Simon asked, I'd love to see if impredicative type satisfies the need you have, Chris.
Yes, I would love to see as well, but I have not tried because my range of GHC version compatibility doesn't yet allow me to try it out. So I should try that at some point in the future and find out whether Quick Look would allow me to write predicates of this form. I don't have anything else to add except yes, I would also love to find out.
Right. Christian asked, do you think if your testing experience will be easier if you were to switch to source plugins?
Oh, I have absolutely no idea how to do things like get test coverage information about a GHC source plugin.
Yeah. More in response to you used template Haskell, and that was already annoying. But I think source plugins will be even worse.
Yes, yeah. The two things that I want are to be able to test failure cases and to be able to test to get test coverage information, because both of those two things led to the discovery of non-trivial bugs in the implementation of HMOC. Inspecting test coverage as well as testing failure cases. And so those were really valuable. I was able to mock the quasi interface, but you're right. I definitely, the GHC API is not type classified in a way that could be mocked in this sense. I would love to be able to mock things that are not type classified, but or not MTL style type classes. And there are some thoughts on that. But right now, HMOC only works for MTL style type classes.
So I think we need to move on for time. Yep. So let's thank the speaker one more time. Great presentation. Thank you. So the next presentation will be about adventures in GHC compile times by Jeffrey Young and Richard Eisenberg from Tweak.
Yeah, hello. Can you hear me?
Yes.
All right, great. Let me share Keynote and play. I have a question. Can you see my mouse?
Can you move it?
I am moving it.
It's not moving for me.
Okay, then that's good to know. All right, if everything's ready, then I'll begin.
Yes, please take it away.
Okay. Hello, everyone, and thank you. I'm excited to be here. I'm currently an intern at Tweak with the sole goal from Richard Eisenberg to try to improve GHC compile times. So this talk's going to be a little bit about the saga to do that, or at least the way I've gone about it. And yeah, we'll see what happens. All right, so if you're given this goal by Richard Eisenberg, it's going to be hard to know where to begin, because if you look at the issue list on GHC, there's at least 170 open issues just for compiler performance, and GHC itself is a well-designed but rather complicated project. There's over 600 modules just in the compiler alone. One way to know where to begin is simply just to ask GHC. So this is a Tiki profile. It's a way to do low-level profiling. It's specified in the GHC user manual, and there's good information on the GitLab wiki. And what we're looking at here is on the right, we have our names of functions in STG. On the left, in the second column, I have allocations in bytes, and on the first column, I have entries. And I've just removed the head of this Tiki profile and then sorted it by allocations. And if you look at this, what you'll notice is that the insert call to data.intmap internal is absolutely hammered. It's one of the most entered functions when I compiled this or when I generated this Tiki profile and compiled this module. And the functions that you see above it are actually from the pretty printers, but that's a whole nother story. All this is to say that if we have small changes in the way that we are using these int maps, it's likely that we might produce large general effects in the compiler performance. There's more reasons to believe this is the case. So there's a lot of comments on the issue list, if you've spent time reading it in the last month, like I have, from Sebastian Graf, pointing out that there's interactions with the insert function and a certain test in the test case. And he finally narrows it down to the unique type interacting with the intmap insert function. in these issues on the comments on the issue list. So that's really the goal of, or the topic of this talk is, why are int maps sensitive to the unique type in GHC? So, well, what is the unique type? Well, uniques in GHC are just a new type wrapper over integers, but they're slightly more complicated than that. They're actually integers, 64-bit integers on a 64-bit machine, where we reserve the top 8 bits for a character class. The character class in a unique is used throughout the compiler to segregate the different uniques for different things. So if you generate a unique for a type constructor, you get a different class. If you generate a unique for a type variable, you get a different class. And the only difference is going to be in those top 8 bits. Okay, so this is what that's going to look like semi-graphically. So your top 8 bits is your character mask, your bottom 56 bits is your unique payload. That's the actual unique stuff in the unique. Okay, all that is to say that there's just a decent amount of variation in the top 8 bits of uniques in GHC. Well, why is that a problem, right? On the face of it, that doesn't seem like it's going to be that problematic. But enter int maps. So int maps are big endian Patricia tries. What that means is they're binary trees. All data is held at the leaves of the tree, and then the path of the leaves are based on the bit string of the key. Lastly, and this is going to be important, they're compressed tries. All right, so this is going to be more easy to understand with an example. So imagine you're building a tree, one of these big endian Patricia tries from containers. And I'm just going to create one where the keys are 1, 2, 3, and 4, and all the elements are 0, and I'm not going to show any of the elements. You start with the root node. We'll check the most significant bit. I'm inserting here. We'll check the most significant bit of the bit string of 1. If we see a 0, we'll go left. If we see a 1 in the most significant bit, we go right. That's how you get the binary behavior. When we insert just based on an empty tree, we just create a leaf node, no problem. When we insert 2, when we insert 2, we get to the first node that we created after inserting 1, and then we'll split the tree based on only the bits that change. So what you see, and this is why it's a compressed try, is that in the second node where you have 0, 0, those 0, 0s are shared between the bit strings of 1 and 2, right? 0, 0, 0, 1 and 0, 0, 1, 0. So rather than having to compare each bit individually and creating more comparisons down the length of the tree, you just compress and store that prefix that's shared between them and only split that prefix when you have to. So you get less comparisons on average. So then again, if we insert 3, we still have the 0, 0s in the prefix that are shared between 1, 2, and 3 in their bit strings. And you see we've split the 1, 0 and 1, 1 because we no longer have a shared prefix. And then we don't split the 0, 0 until we insert a 4, right? Because now we have 0, 0 or 0, 0, 1, 1 and 0, 1, 0, 0. So we only have a prefix that's shared that's 1 bit long. But so that's where the performance of these int maps really come from. That's where the algorithmic complexity of big O of min of NW comes from, because in the worst case, you'll be comparing every single bit in the bit string, right? And this is also where the performance of sequential keys comes from in int maps. So if you insert a lot of sequential keys, you're maximizing all the operations on that prefix. You have less comparisons than you otherwise would, and you have nice performance. But remember that we store the top character mask and the top 8 bits of the unique type in GHC, and then we put those into int maps, right? So what we're doing is we're artificially limiting that prefix and then therefore maximizing comparisons in the int map. That seems like a problem. Well, is it a problem? So the first thing to try is swap the character mask to little endian. So this is our old function to make a unique. What you see here is we basically OR the character mask with the bits after we shift the character mask 56 bits to the left. The new version of this simply shifts the unique payload 8 bits to the left and then ORs the character mask. So what that should do is maximize the prefix of the bit string, and then we should have less comparisons on average and so on and so forth. That's what this is, again, my little representation. So now the unique payloads in the top 56 bits and our character mask is in the bottom 8 bits. And this is a result of continuous integration compiler performance tests. And you see, well, it doesn't actually do a whole lot. We have 2 tests that have marginally improved by about 1%. Everything else is in noise, which I think is evidence that the uniques actually aren't interacting poorly with int maps. Okay, well, another thing we could do is we can mix the uniques. Well, what does that mean? This code comes from Sebastian Graf, and he links to this gist. What we mean by mix is we're going to scramble the bits in the bit string of the unique. So we're just going to randomize them, but we're going to do it in a rather clever way so that we can encode them so that they'll be randomized. And then when we need them, we can decode them and get our payload back out and our character mask. And so all this is a tiny hashing function. K forward and K backward are the keys to encode and decode. And then the only change that we make to our make unique function is we inline a call to encode to scramble the uniques. And if you do this, well, you get some performance benefits. So we see around 2% for a few tests and a few more goods, which are just on the edge of past the tolerance for the continuous integration. But again, it's not the big win we were looking for, right? So then I think, so the next question then to ask is, well, how many comparisons are actually being made in practice? The Tiki profile is wonderful because it gives us this nice low level information, but it doesn't give us, it sums over it. It gives us the total number. It doesn't tell us, well, what's the distribution? So that's what we're going to do. I'm going to add a counter to count comparisons in insert and lookup in the int map internal containers module. Then I'm going to build a custom GHC with that insert and lookup or that containers. And then I'm going to generate data on size and comparison count when compiling various Haskell projects. And if you do this, you'll have to let your computer run for a while because it ends up being a lot of data. So I'm going to show you a lot of data now. Basically, the rest of the talk is data. And I need to orient you so you understand how to read some of these plots first. So this is the first test case, and it's kind of what you should consider as the baseline. So this is the int map benchmark suite. So I did my containers hack, and now I compiled the benchmark suites and ran it. What you see is on the left side is our insert function. On the right side is our lookup function. Notice also on the bottom plots, the y-axis is log base 10. That's always going to be log base 10. And the takeaway here is that on average, the benchmarks for int map do 5 comparisons for inserts. For lookups, there are always 13 comparisons. The reason there are always 13 comparisons is because the benchmark suite in int map creates a tree that's 4,096 elements long, which ends up being 13 comparisons. That's also why if you look on the bottom right plot, the size of the int map is always 4096. Oh yeah, I also forgot. The top plots are the number of comparisons on the x-axis. The bottom plots are the size of the distribution of size of int maps during the analysis. So we get a distribution of comparisons and we get a distribution of size. These plots are a little more complicated. So these are empirical cumulative density function plots. And if you don't know how to read them, they can be kind of hard to read, but I'll walk through it here. So the reason I'm plotting these is because these kinds of plots are, they give nice information of, well, how much of my distribution is greater than some value. So if you look on this slide, we see that 5 is the mean in the top left plot of inserts. So on average, we do 5 comparisons. Well, I want to know how much of this distribution is above 5. You're going to say 50% because it's the mean. So if we look at the similar plot or another representation of the same data, that's in the middle to the left. And you see that you have this orange or red curve. You look at 5, on the x-axis of comparisons, draw that up, and you'll see on the y-axis, we're at 50%. So when you have a normal distribution in ECDF plot, you see this S-curve. Now I've also added black lines here that are important. So the x-axis on the top plot is the expected value that we would get for comparisons if we just had a self-balancing binary tree. So I take the size of the tree, I log base to it, and then take the ceiling of that. What that means then, and subtract that number from comparisons. What that means then is that if you see negative numbers on the top plot, the most of the distribution is on the negative side. That's good. That means we've done less comparisons than we normally would had we had a binary tree, a self-balancing binary tree. If you see positive numbers, that's bad. That means we've ended up doing more comparisons than we normally would with a self-balancing binary tree. And then for lookups on the right-hand side, it's not really good data because you just see everything's going to be at 13 and 1 because of the way the benchmarks work. The middle plots, the black line on 7, for the middle plots, the reason I marked this was because hashed array map tries, which are popular in the closure community, guarantee 7 comparisons. So if you look at the black line in the middle plots, follow that up to the ECDF curve, then you can calculate what % of time would we just be better off using hashed array map tries. Okay, that was a lot of information. Let's start looking at some real data. So this is a module spectral simple main that we use in the NoFib benchmark suite that GHC has. It's just a normal kind of sandy check, but this is our first real data. So what you see is we have our on the top left for inserts, we're centered around 6 comparisons, but then we also have a spike at 13 and 14 for lookups. Similarly, lookups, most of our maps are either around less than 500 size or 500 elements, or they're at, for some reason, peaked at 3,600 around. This is what the ECDF plots look for this, and this is an example of what bad looks like. So you see at the top, most of the time, we're actually okay, where most of our distribution is as good as a balanced binary tree. But if you follow this, you see about 10% of the time, we're worse than a balanced binary tree. Same thing with lookups. About 15% of the time, we see positive numbers on the x-axis, so we're worse than a balanced binary tree. For comparisons, we're centered around, so if we compared this with hashed array map tries, it's about 20% of the time a hashed array map try when compiling this module would perform better. Similarly with lookups. So you follow the black line from 7 up to the blue line, and you go to the left, and it's about 20% of the time. Okay, but that's just a single module. What if we did this analysis with all of the performance tests in GHC? If you do that, then you get a power distribution where it's always centered around 0. What that means is that most of the time we're inserting and looking up into an empty map, which again is not very surprising because we're constantly compiling these small little files. But these are just, one-off comparisons. Most of the time when I'm compiling something or using GHC, I'm compiling packages. Oh, and then this is the ECDF. So you see the ECDF for the performance test, 100% of the distribution doesn't get to positive numbers on the top plots. That's the key takeaway here. Okay, so what if we compile packages like Pandoc? So if you compile Pandoc, and there was so much data here, I had to take a 55% sample because, well, R was starting to die. You'll find that the overwhelming majority of the time, we are inserting and looking up into maps that are relatively small. Remember that the size of these maps is in the bottom plots, and the y-axis there is log base 10. So changes there are really quite significant. And if you end up looking at this in more detail, and I'll make the data public, most of these maps end up being around 1,000 elements. Okay, so that's Pandoc. For the ECDF functions, we see that, again, about 20% of the time, looking at these middle plots, hashed array map tries would perform better because the 20% of the distribution is over 7 comparisons, and that's the maximum you would get with hashed array map tries. But using just a balancing binary tree, we're actually pretty okay. So at the top, if you look at the top plots, about 5% of the time on our inserts are worse, and about 15% of the time our lookups are worse when we're compiling Pandoc. Well, what about ASON? Oh, and I'll have to switch. I'm going to skip ASON for time because I want to get to the big one. What about Cobble? So Cobble took a much longer to run and is much, much worse. So I've overlaid quantiles here, and you can see that. So let me let's look at the top left plot. 95% of the time, so the 95% quantile when compiling COBOL, you have 9 comparisons for the insert. 99.9%, you have 18 comparisons. And so if we look at the size, 95% of this distribution is around 1,200 elements, but the 99.9% is 10,000. So what we have is when compiling COBOL, most of these int maps are less than 2,000 elements, around 1187, right? But it's just this long tail that's extremely long. So the question I want to ask then, or the conclusions of this rather long amount of data, is, are these really the right data structure to be using? You know, if most of the time our data structures aren't getting longer or larger than 2,000 elements, then should we be even bothering using something like the Big Endian Patricia trie? I think we definitely need to try the hashed array map tries or Bagwell tries. So Bagwell tries would even perform even better, but I don't think there's an implementation in Haskell. And then also the takeaway from this kind of data analysis is most of these operations are being dominated by empty trees. Why? I mean, you know, the non-empty list has been in base for a while, and I almost wonder if there's some mapping function somewhere that's just inserting and then appending a bunch of empty trees. Okay, so that's all a lot to say that I don't have the answers yet, but they're on their way. And I'm way over time. Apologies. If you would like, here's the references. You can follow me on Twitter. You can follow me on GitHub or GitLab. I'll make the data available, and I'm also on the GHC Dev and Haskell IRC if you want to talk about this. And that's what I have. Thank you.
Thank you so much. Wow, that was an awesome talk. I especially liked it because I remember writing the initial int map implementation when I read Andy Gill's and Chris Okasaki's paper.
Mm-hmm.
It is already, I don't know, 20 years ago, right? So it's very surprising to see these results. I think there was an interesting, Simon remarked that about the small, why you see so many small ones there. Small maps dominate. That makes sense, not because programs are small, but because free var and occurrence analysis builds up sets from the leaves, right? I believe that too, right? So I think optimizing for small ones would be really good. Can I? One initial question I had was you started out the talk by saying like, why is unique so impacting int maps? But then you kind of showed it wasn't little endian or big endian. But do you have? I don't think you actually answered the question, right?
Yeah, I think the answer to the question is that it's not actually impacting bitmaps or int maps. So up here, right? So the idea was that these prefixes, we end up with, if the uniques were interacting poorly with the int maps, we would end up in a degenerate case like this, where we don't have large prefixes in our internal nodes, right? And so that was the motivation for the entire comparisons plots here. But you know, the result of the analysis is really that in most of the time it's fine. You know, it's like if we look at something that's realistic, like Pandoc, you know, 5% of the time it's completely okay. So I think the takeaway isn't so much that the uniques are actually creating it, or the uniques are interacting poorly with int maps, and therefore on some modules we get these slowdowns or high allocations. I really think that the takeaway is that we could use something that has better higher bounds or has better performance if we know that the size of the container is less than 2,000 elements. Right. I think these plots are too big to ignore, where you see, you know, orders of magnitude difference in tree sizes from 0 to 500 elements. And maybe, you know, if I'm not quite sure how to change the compiler to optimize for that, but it seems like something that should be optimized. Did I answer your question? Or the question of the talk?
Yes.
Yeah.
I think what you're eventually suggesting is saying like maybe we should switch halfway. Like once the data structure becomes bigger than 1,000, we should maybe use another form, right?
Yeah, I agree. Yeah, I think that's the next step forward.
So I think Sebastian Graf had an idea. You want to talk about that, Sebastian?
Yeah, I can talk a bit about it. So, yeah, well, I think you just answered my question basically. So, an idea would be to turn the unique FM, which is the map implementation that maps uniques and uses an int map as the underlying map implementation. We could turn the unique FM into a hash array map trie or into a backwall trie. Not sure what that is, but at least I thought it was related to hash array map tries.
It is. It's an improvement over it.
Okay, cool.
Yeah.
Yeah, so at some fixed metric, like maybe 1,000 elements, or based on tree depth, which maybe measures more accurately whether or not the tree has or is degenerate.
Mm-hmm.
Well,
yeah. So
just an idea.
No, that's a good idea. I actually have a branch up already that implements unique FM with the hash maps, which are hashed array map tries. But unfortunately, like all experiments worth doing, it went to the work in progress graveyard, which is GHC panic and the liveness analysis of register allocation. Yes. Yeah, and I still have to. I was racing to try to get something yesterday, and I just gave up around last night. So curiously, though, I can still build the stage 1 compiler, so I can still check allocations on the stage 1 compiler compared to master, and I'll probably do that today because my day's just starting.
Cool.
Yeah, to see if there's a difference.
Yeah, sounds great. I think you are really into this, and it's great that somebody is going to tackle this, because I think the myths that are building up around, or that we seem to create around int maps and uniques and so on, they just keep getting more annoying. And yeah, it's good that somebody takes the time to clear it all up.
Mm-hmm. Yeah.
So
yeah,
thanks.
I was enticed by Richard's low-hanging fruit, and then it turned out to be anything but low-hanging fruit.
Yeah.
Right. So I think let's thank the speaker.
And I will stop sharing.
So the next talk is a lightning talk about pinned warnings by Aaron Allen, which is a pre-recorded talk, I think.
It's pre-recorded, and I'm not sure that Alan is actually here, so we'll just play the video, and maybe he will join, and if not, then we'll have no opportunity to answer questions, but at least we can play the presentation.
My name is Aaron Allen. I'm a Haskell developer.
Did you want to introduce him, Dan, or?
No, it's fine. Let's just start. Aaron Allen with about pinned warnings, a lightning talk.
Okay, here we go.
Today I want to talk about a GHC plugin that I wrote. And while GHC plugins are usually intended to alter the behavior of GHC in some way or add some extended functionality, this plugin is actually intended to be more of a developer tool, specifically dealing with warnings in a GHCI session. So when I'm developing, I like to use GHCI, but I've encountered some friction around warnings. So let me show you a bit of what I'm talking about here. All right, so I've got the Cabal code base here loaded into GHCI. And for demonstration purposes, I'm going to export this text term from this module, which it shouldn't export, but let's reload this and see what happens. All right, so I'm getting some warnings here about redundant imports. Okay, so we got a number of warnings and they're spread out across my buffer here. I have to scroll around to find everything. It's a bit of a hassle. If I were to then go and fix these warnings, this is not very helpful user experience. So to fix this, I have a plugin enabled where there's this show warnings command, where if I evaluate this, then I get all of the warnings, all the active warnings for this GHCI session, all displayed together. So it's now much easier for me to go and deal with the warnings. Additionally, if I have some redundant imports here, like I'm going to add this char term, I'm going to import data.list, text as well. So let's reload this again. Okay, and again, I got some warnings, but they're all the way at the top here, so I might have missed them. But I can show the warnings, there they are. And for redundant imports, there's another command called fix warnings, which if I evaluate this, then we see that this file was edited. So I can refresh this buffer, and then the redundant imports are gone, and this extraneous term was also removed from the pretty print import. So that is a feature that saves me a lot of time when I'm doing a refactor where I'm touching a bunch of different modules, and imports can easily become redundant. And then you might spend a lot of time going through and removing import declarations, and might not even see the warnings because they got lost in the buffer somehow. So that's quite useful. I will say it's a bit of an experimental feature. I discovered actually making this presentation that this does not play well with the C preprocessor, so I'll need to look into that. Okay, so let's take a look at the implementation of this plugin. So this is the main module where the plugin is defined. Here it is. So it's got a few different components. I've got a typechecker plugin, parse result action, dyn flag, modifier, and the main sort of mechanism that this is using are these empty type class definitions here. So we've got type classes that don't have any parameters, just have a single method with type unit, totally useless type class, right? Except that with this plugin, specifically the type class or typechecker plugin, I can check for specific wanted constraints within the compilation context. So here I'm checking if the class for the wanted matches with the show warnings class. So if I were to evaluate this expression in GHCI, it would emit a wanted constraint for show warnings, and I would match on that here, do some implementation details, and then there's this add warnings to context, which takes the warnings that have been stored or pinned for the session and emits them back into GHC so that they're displayed to the user. So how do the warnings get there in the first place? So the warnings are tracked within this global state variable. So a bit of unsafe perform IO here, but it's for a good cause. And they get there using this dyn flags plugin. So this allows you to modify the dynamic flags for a session. So what I'm doing here is using this log action function, which is sort of a handler that GHCI sends messages through. So I can hook into this and pattern match on the warning messages, make sure they have source code locations, and then I put them in this map that goes into the global variable. And that's essentially how the plugin works. So I've been using this at work quite a bit, and I find it to be quite useful. So I hope you check it out, and feel free to open bug reports, and pull requests are welcome. And that's it. Thanks very much.
Let's thank the speaker. I don't think he's actually around right now, but it was a fun presentation, and I for sure run into this a lot, so it looks really good. If anyone has any remarks, please let us know in the chat or Q&A. Right. So Gergo remarks that if you use IO unit instead of unit, you don't see the unit printed by GHCI, which would otherwise use a show around it, right? All right, let's move on then to the next or the final lightning talk of this session. It's called GSOL, Confluence Checker for Haskell Rewrite Rules, by two students, I believe, at the Gunma University, Faustin and Makoto.
I think we're waiting for Austin to join. We do have a video for that.
Faustin, are you here?
Oh, yes. Yes, can you hear
great.
me? Yes, so the talk is supposed to be via a video recording.
Yeah, don't worry.
Do you have it?
Great.
Yes, and a little correction, like Makoto Hamane is associate professor, not a student.
Oh, sorry about it. Oh my God, I'm so embarrassed now. All right.
All right.
Thank you for correcting me.
Okay, so we'll play the video first, and then we can chat after.
Yes, please. Science laboratory at Gunma University, and we are working on GSOL, a tool that uses the second order laboratory, SOL, to check the confluence of Haskell rewrite rules. SOL can verify the confluence of higher order rewrite systems, and GSC has the feature of user-defined rewrite rules. To motivate GSOL, let's consider this sample program with two rewrite rules, F0 and F1. The rules have the same left-hand side, fx, but F0 rewrites it to the literal 0 and F1 to the literal 1. We also have the expression F99, from which the variable e gets its value, and F99 matches both rules. But from the specification of GSC, we don't know which rule is going to be applied. Depending on the rule that is applied, F99 is going to be rewritten to either 0 or 1. 0 and 1 are different literals, and they are already in normal form. This makes the two rules in this program non-confluent. But GSC does not notice this non-confluence. So we are developing GSOL to help with automatically check the confluence of the user-defined rewrite rules in a Haskell program. But why is confluence important? Confluence is the property of a rewrite relation that says that all divergent computation paths are joinable. And confluence guarantees uniqueness of normal forms, which is particularly important in functional programming. GSOL uses Newman's lemma to conclude confluence by checking local confluence and termination. And local confluence is a weaker variant of confluence, which requires that only all one-step divergences be joinable. And termination is the property of a rewrite relation with no infinite rewrite steps. We implemented GSOL as a GSC core plugin, so it works on GSC core programs. And GSOL first collects the GSC core rules, then it converts the core rules to SOL computation rules, and calls SOL for the verification. Then SOL performs its checking functions and prints the results to standard output. So GSOL uses SOL for checking, and SOL is an implementation of a formal framework of second-order computation systems. It has its internal language of metaterms, and metaterms are made of variables, abstractions, function terms, and meta application. The metaterms have up to second-order types, and pairs of metaterms form computation rules in SOL. GSOL can be used from the command line. The command takes two parameters, the property to check and the path to the Haskell program file. The property is either CRI for checking local confluence and SN for termination. CRI is short for a critical pair, and SN is short for strong normalization. So the property is optional, and if it's missing, then GSOL will check both local confluence and termination. There is also a web interface, which is available at this address with some examples. We experimented on the Arrow library of GSC, and the library Arrow provides a way to programming with various computational effects in Haskell, and it is implemented with the type class of the same name, Arrow. And the library has defined several rewrite rules, which assume that the Arrow is the function constructor. And when we run GSOL on the library, it reported 8 critical pairs, such as this one, between the rules, generated by the rules compose first and first arrow. So from the output of GSOL, we read that the sub-expression first f from the left-hand side of the first rule is unifiable with the entire left-hand side of the second rule by this unifier. And the result of unification is this expression that can be rewritten with either rules. And the result of rewriting is these two expressions that are in normal forms, that are different and are in normal form. And so the rules in the library are not confluent. This is useful information to improve the design of the rules. So we are still developing GSOL, and as a future work, we want to improve the handling of types when translating from GSC core rules to SOL rules. For now, GSOL drops type constraints, and we know that this is fine for checking critical pairs, local confluence, but it makes termination checking weaker. To summarize, GSOL is a tool that checks the confluence of Haskell rewrite rules using the second order laboratory, SOL, and GSOL checks confluence by checking termination and local confluence. We have a web interface for GSOL available at this address, and there we can find the example for the Arrow library from the pull-down menu, and we can visualize the results by ensuring that the GSC rules format is selected and the option WCR. WCR is short for week or weekly church roster. It's also a synonym for local confluence. And so when you submit the program, GSOL checks and returns the results. So these are the 8 critical pairs, and the conclusion is on the last line. So some details of GSOL, are described in the draft paper available at this address. If you're interested in GSOL, please refer to the draft or contact us. Thank you.
Thank you so much. Wow, that's very interesting. There's many questions already. Maybe I'll start with Jesper Cox, who asked, can it also suggest what rules to add to make the system confluent, or even add them automatically?
Yes, so for now, GSOL doesn't try to add the rules to add the rules. But what? But the results give a suggestion. So when you have a critical pair made of two terms T1 and T2, so you could add the rule from T1 to T2, or from T2 to T1, and then we run GSOL again to see if that solves the local confluence problem.
Right, yeah, thanks. So I asked because I also implemented the confluence checker for rewrite rules in Agda last year. And there, I mean, so the problem with what you just described is maybe that you get the critical pair, but in the syntax or in the translated syntax, right? So is there a way to get back and get something that's readable or understandable for the user, that to know what exactly went wrong?
So I want to make sure that I understand the question correctly. So, is the output understandable by the user? Is that it?
Yes, that's the first thing, right?
Yes. So,
because if it just says no, then that's not maybe not enough to fix the problem.
Yes. So, a little bit of knowledge of GSC code would be useful to read the output that is produced by the tool. Yes.
Right. Yeah, then, maybe you can take it as a suggestion, maybe to have a translation back as well.
Okay, that's noted.
Yeah, but thanks for the answer, and thanks for the talk, also.
Thank you.
Another question was by Christian Bai. What was the observed rewrite for non-confluent arrow example? I hope it's deterministic.
Yeah, so there was the non-confluent two rules, and then you could go either go left or could go right. But which one did GHC actually pick? And yeah.
So I've shown a critical pair with two expressions. Sorry, I don't understand the question clearly.
So there was you had one example for arrow where it was non-confluent because it could either go one route or could go the other route. But
yes.
Which one does GC actually do? Because I hope it doesn't do a coin flip every time it encounters the example.
Oh yes, yeah. So that I couldn't check because the rules in arrow actually, it seems they don't fire.
Oh, they don't fire. Okay.
Yes. So we've only been able to check local confluence, but without being able to know which one GSC actually picks.
Okay. Yeah, I was kind of hoping that, maybe if you even if it's non-confluent, as a rule designer, you might still favor, like, I prefer the one option over the other, and then maybe changing the order or giving a different name or whatever. But okay.
Thank you for the question.
Right. I think this is part of why it's so pernicious, right? That even if you don't have confluence, it doesn't, like, your program doesn't go wrong as such, right? It's just a hint that maybe there's something wrong with the way you specified the rewrite, right? Yeah.
Yeah.
That's very tricky. So. Wow, there's two more questions. Hope you're ready. One by Richard Eisenberg. Is there a way of stating that two expressions should be considered equivalent, even if they're not syntactically identical? Maybe you can explain a bit about that, Richard?
Can you hear me okay? Yes, okay, good.
Yes.
So I guess I'm hoping that the rules in the arrow library, so they may not be confluent, but my hope is that no matter which rule you end up taking, you sort of end up with an equivalent expression. And so, you know, that they might not be syntactically the same. So is there a way of sort of saying that these two expressions, you know, something simple like, you know, if plus is the sort of the key operator, then, you know, 1 + 2 is going to be the same as 2 + 1. But there's not going to be a rewrite rule from one to the other. Is there a way of sort of stating that, oh, you're doing this up to some equivalence?
So the answer to that would be, for now, no. There's no way to make two expression as that's equivalent, although they are syntactically different. Yes.
Okay, thanks.
Can I add to that? Like, if you would add a rewrite rule that says 2 + 1 can rewrite to 1 + 2, you might get that confluence, right? Without you building it into the tool. Or I don't know.
Yes, but that rewrite rule seems dangerous. But if you just have a
Right.
rewrite rule for all AB, A + B = B + A,
Yes.
that doesn't.
Now you could go forever, right?
Yeah.
Yes, you could get non-termination there.
Yeah.
Maybe something to think about for your project. Okay, so does it answer your question? Wait, good. One more question by Jeremy Gibbons. Did you find the critical pair in the arrow rules, or was it already known?
So we didn't know until we run the tool on the library that there were critical pairs in the rules. Like, we didn't know.
So that's a good result then.
Yes.
I mean, it was a surprise to you, I suppose. Was it known in the community? Was it a surprise to everyone that the rules are not confluent?
So the rules that I've described in the library, no, like we couldn't find any information on the confluence or non-confluence of these rules. So it was new for us.
Okay, very good.
As well. Yes.
It's quite a surprising result, actually, right? For such a basic library, right? All right, let's thank the speaker one more. I think we answered all the questions, right? Let me actually look. Yes, let's thank the speaker one more time, and that concludes this session. And I think there's one more session to go after the longer break. Maybe Etsko can.
Right, so we're going to break for 35 minutes, and then we'll resume with our final session. This session ran a little bit over, but that's, you know, we had the time, so no problem. So we'll resume in like roughly 35 minutes. See you guys after the break. Thanks very much. Thank you, Dan.
Thank you so much.
Okay, it is time for the final session. Welcome to the final session of the Haskell Implementers Workshop. Let me just check if he joins. Right, so we have two talks in this session. The first one is from Ranjit Jalla, but I think he's not in the session, but it's a pre-recorded talk. So I guess he needs no introduction. He works at the University of California in San Diego, most well known for his work on Liquid Haskell, of course, which adds support for refinement types to Haskell. And today he's talking about Storm, which is a new web framework built on top of Liquid Haskell that uses refinement types to express security properties. So I will play the video and then, oh, I see. Okay. Nico will be taking answers after the presentation. That's fine. Let me just find the video. All right, here we go.
Refinement types to secure web applications. So we trust web applications with all manner of sensitive information about our lives, our professions, our finances, our health. And it's not clear that this trust is entirely warranted, as glitches in these applications are routinely exploited to exfiltrate sensitive data. Why do we have these glitches in the first place? Well, the trouble is that typically the people who design these applications do think about security, but the mechanisms they have for enforcing it require them to sort of sprinkle a whole bunch of checks inside their code. So the security is sort of intertwined with the business logic, which makes it really hard to determine whether the checks have been sort of implemented correctly, or even whether there is some high-level security policy in the first place that's even being implemented. So what we wanted to do in the Storm web framework is to separate the policies from the quote-unquote business logic, right? What we want is to have some standalone notion of a security policy that is easy to audit and trust, and then have some systematic way to automatically verify that that policy is actually properly enforced throughout your web application. So having motivated why we want to secure web applications, I'm going to give you a kind of high-level demonstration of how you build applications with Storm. And then in the last part of the talk, which is really the bulk of it, I'll give you an overview of how Storm enforces security via refinement type checking. So let's start with a high-level overview of how one would use Storm. So imagine I want to build a kind of a wish list application where everybody has their, users have their list of things they would like their friends to buy for them, for example, on their birthday. And some wishes might be public. I might want everybody to know, for example, that I love Godzilla vs. Kong because you know what? It's a great movie. And there are other things maybe I don't want everybody to know. For example, that I love karaoke. I might want to keep these things private. I might imagine a policy for this web application that says that only the user who owns a particular wish should be allowed to access the private wishes. The public wishes, anybody should be able to see. We are going to start with the database schema that is sort of very common and ubiquitous in web applications. So this database schema essentially declares the different tables that the database stores. So there's going to be a table for each user, and the table, each row is going to store the user's name and their email, both as strings. And then you might have a separate table that stores wishes. So for each wish, we're going to store the owner of that wish, so an ID, a pointer to whoever the user is who owned that wish, a description of that wish, perhaps its title is a string, and perhaps a level which might be public or private, which determines who should be able to see that particular wish. Now the policy we might have might say something like this, right? Remember, the policy was only the owner should be able to see a wish unless it's marked public. And this predicate is going to return true if either the level field of that wish, okay, this level, is the string public, or the owner of that wish is exactly the same as the viewer. Okay, so notice these are data dependent policies. The policy depends very much on the data that's stored in the database. And this is essential for sort of writing real world realistic security policies. What I'm going to do now is I'm going to take this predicate and I'm going to attach it to this wish, to this row of the wish table. And it's going to say that the titles or the descriptions should only be visible to the owner unless they're explicitly marked as public. Now let's look at an example application. Okay, so here's a snippet of the web server perhaps that returns the list of wishes that belong to some arbitrary user UID. So in the first part, what the server is going to do is it's going to create a query that looks for all the wishes that belong to UID, whose owner is UID. Then it's going to execute those wishes using this select operator that runs the database query. And then having obtained the wishes, it's going to pull out the description. Maybe we don't want to send all the information, just the descriptions. And then finally, we're going to respond, send back a JSON or text or HTML response with all the titles. Now Storm is going to reject this code and is going to complain that there's a leak over there. Why is there a leak? Well, if you look at the security policy, this returns all the wishes that are owned by UID, and those should only be viewable by UID. We have not checked whether or not they're public, right? And so now since these titles are only viewable by UID, and since the response is sent back to the current session user who might not be the same as UID, Storm is going to complain and say, sorry, this code does not respect the security policy. How might we fix it? Well, what we want to do is to restrict the query to take only the public wishes when the session user is not equal to UID. Okay, if the session user is the same as UID, then it's fine to give the person back all of their own wishes. So here's how we might do that. I'm going to get the viewer. I'm going to sort of query Storm to say, hey, who is the viewer right now? Who is the session user? And then I'm going to compare viewer to UID. So if viewer is the same as UID, then I do nothing. Otherwise, I add this extra conjunct to my query that says level equals public. Okay, and now I'm going to update my query to owner equals UID and this extra conjunct query. Okay, and effectively this is going to restrict the results to only the public users, public wishes when the session user is not equal to UID. And now Storm says, okay, well then in that case, this code satisfies your security policy as declared at the outset. So having given you this high-level demonstration of how to secure apps with Storm, let's now dive in and see how Storm actually enforces security. At a high level, what we want to do is let's look at the anatomy of the web server. Let's see what its elements are. Okay, so if this is the entire code of the web server, as Haskellers, what you will have noticed, of course, is that this whole thing is a giant do block where each server is comprised of a whole bunch of smaller atomic actions, which you can think of as computations glued together as with bind and return and so on. Let's drill into an individual action. What you'll see is that this action is a select. It's a database query that takes as input a particular query object. Okay, in this case, owner equals UID and this subquery, which subquery checks if the level should be public and so on. And finally, each of these query objects themselves are made up of smaller primitives, these fields like owner and level, which correspond to sort of database fields or columns, which are glued together with these combinators like equals and so on and so forth. So what we're going to do in Storm is to exploit this structure. So we're going to look at these central types, field, queries, action, servers, and the functions that allow you to go from fields to queries, from queries to actions, and then build up the whole server. And we're going to associate refinement types with all of these individual elements to build up a refinement typed API such that just by type checking your server code, you can be guaranteed that your security policy holds at compile time. So there's three elements that I'm going to describe. First, I'll give you a whirlwind overview of refinement types. Then I'll describe how we do this information flow tracking or this policy tracking inside these action computations in the server. And finally, I'll explain how we actually connect that with the policies and the database. So let's jump in and look at refinement type checking. So refinement type is nothing but a plain Haskell type like int or bool or string or so on, decorated with a logical predicate. So for example, this particular refinement type nat is just an alias for the set of integers x such that they are non-negative. Okay. You can take these types and you can compose them with arrows and type constructors and so on to get interesting contracts. For example, this function type describes a contract which says that the function must be given inputs that are non-negative and returns as outputs values that are greater than this input x, which is the thing that we named in the input precondition. So this is what is called a dependent type. Now let's see how we go about checking such types. So imagine I wrote a function called double that takes x and returns 2 times x, and I want to check that it has this particular type, non-negative to values that are greater than the input. The way this works, roughly speaking, is that we generate a logical formula which we then ship off to an SMT solver, a decision procedure that will tell us whether or not the formula holds, and if so, the program type checks. So in this case, the formula looks something like, when x is greater than 0, any value that's equal to 2 times x must also be greater than x. And the SMT solver says yes, and so this code is correct. Now let's see how we use these refinement types to sort of track how information flows, how these policies, how security sort of can be checked inside these server computations. The central idea is this notion of authorizees and observers. Okay, so let me again explain with an example. So recall our show wishes server or controller. The set of authorizees of a computation is the set of users who are authorized by the security policy to access the data that that computation touches. Okay, so for example, let's look at this computation. The set of authorizees is the singleton set comprising UID. Why? Because the policy said that only the user should be allowed to access the title unless the wishes are marked public. Here, these wishes are all the wishes, not just the ones marked public. And so the authorizees of this computation is just the singleton set U equals UID. Notice how we're going to represent these sets as logical predicates, as refinements, essentially. U equals UID. Dually, the observers of a computation are the set of users who are provided access to data by that computation. So for example, if we look at this computation respond titles, the set of observers is the session user. Again, just a singleton set because that's who this response goes out to. And so the observers can be the set of the session user. To enforce the policy, what we want to make sure is whenever we sequence 2 computations, the set of observers of the second computation must be contained in the set of authorizees of the first. Why? Because if this containment does not hold, we're essentially leaking information to some observer who is not in the set that was authorized to view the results of the first of the prequel. And so this observer might see some sensitive data that they were not allowed to access by the prequel. So in this case, this policy enforcement fails. Why? Because the observers are the session user, U equals session user, and the authorizee is U equals the user ID. And again, this inclusion does not hold. In our case, this inclusion becomes a logical implication, and we ask the SMT solver, hey, if u is equal to session user, does that imply u equals user ID? The SMT solver says, no, these might be different people, and so this code is rejected. However, when we fix our code, the equation changes. Now the set of authorizees, since we have added this conjunct level equals public, and the set of observers remains the same. Okay, so the set of authorizees is now the set of all the users. Why? Because we put in this conjunct level equals public. The set of observers remains the same. It's still just the session user. And now when we ask the SMT solver, hey, if u equals session user, does that imply the set of authorizees? The answer is trivially true, because the authorizees is everybody. So what we are going to do in the Storm framework is to encode this notion of authorizees and observers inside as effects inside this action monad. And so we're going to track the set of authorizees and observers as we build up these computations, and we're going to enforce these checks across the entire server. Let's see how we do that. So first of all, you will have noticed, since it's a do block, each of these yellow snippets is just a monadic computation yielding a t value. So I'm going to call that an action of t. But now I'm going to take this plain old action, and I'm going to refine it. I'm going to index it with these security effects, okay? One refinement for the authorizees, shown in green, and a separate refinement for the observers, shown in blue. So let's look at some concrete examples in the API, just to build up an intuition. Let's look at the respond function. So this takes a piece of text and returns just an action returning unit, but the authorizees are going to be the set of all users. Why? Because respond doesn't touch the database. So it doesn't depend on any sensitive data. All users can have access to that particular data. However, the data is provided to the session user, and so the observers is u equals session user. Let's look at another example. The return function, this plain old monadic return, takes an A as an input, returns an action of A as output, but the authorizees is again the set of all users, as we don't touch any sensitive data, and the observers is the empty set, because we don't send any data to anybody either. The interesting work happens inside the bind operator. Okay, so this is the classic bind signature, action of A to action B, and returns an action of B. All of these are going to be indexed by the authorizees and observers of the first action, the authorizees and observers of the second action, and the authorizees and the observers of the output, the sequenced action. But we're going to add these extra constraints to these refinements via the notion of refinement bounds, which are essentially going to check that the authorizees of the first action contain the observers of the second action. Okay, so the policy is enforced at each sequencing. Second, we are going to make sure that when we sequence the actions, the authorizees of the resulting of the output action is the conjunction, the intersection of the authorizees of each of the two actions being sequenced, because now we're depending on both their data. And finally, we're going to make sure that the set of output observers is the union, because of course we have sent outputs either to O1 or to O2. Okay, so that's how we take these, we sort of track authorizees and observers as effects and build up our server computations and make sure that the observers are contained inside the authorizees at each step. Now we come to the last piece of the puzzle. How do we track the policies which were declared as part of the database schema across the query construction and execution API in order to determine the authorizees for all the primitive actions that involve the database? We're going to follow a three-step approach. First, what we're going to do is we're going to inject the policy predicates as they were specified in the database schema, and we're going to attach them with the field values that the ORM gives us to represent the individual fields of the database, the individual columns of the database. Next, as we build a query using equals and and other such query combinators, we are going to aggregate the policies of all the subparts of the subqueries to compute the policies, that is to say, who is authorized to view the results of each query. Finally, when we execute the query by invoking a database select or project or join operation, we're going to use the sort of aggregate policies to determine who the authorizees are for the corresponding action. Okay, so let's see how we inject the policies into the database fields. First of all, recall that the way that we specify the database schema was we specify individual tables like user and wish, and for each table we specify for each row what the different columns or fields are for that row. So the name, for example, the user has a name which is a string and an email which is a string. The wish has an owner, title, and level, which are respectively user ID, string, and string. An ORM like persistent, Haskell's persistence, which is widely used, generates field values for each of these elements from the database schema. So name, email, owner, title, and level are all first-class fields. And the type of each field is a field row val, where row denotes the table that it's a field of. So for example, owner is a field of the wish table and has the type user ID. Its value has the type user ID. Similarly, title is also a field of wish and has the type string. What we are going to do in Storm is to refine this field data type with the policies, the authorizees, who is allowed to see that particular field, and crucially, also a type level representation of the particular value that that field represents. Let's look at a concrete example. So the title field, which was just a field of the wish table of type string, is now going to be indexed with two predicates. First, the policy for that particular title, which was, if you recall, for any row and for any user, a user is allowed to view that particular row if either the owner of that row is the user owns the row, or the level of that row is public. Okay, and so that's what these green bits, they're taken directly from the database schema policy specification. The blue bits are type level representations of the value of that particular field. For example, what this predicate says is, for any row, the value v of the field is equal to the title of that row, R. Okay, similarly for owner, the value v is equal to the owner of the row. For any level, the value v is equal to the level of the corresponding row. Next, what we're going to do is propagate these particular policies and representation invariants across as we build up queries. So in persistent, the way we represent a query is, again, there has a special type called query of R, where R is the table that query is for. And so what we're going to do is we are now going to refine the types of equals and so on and so forth to essentially further refine the type of query with who is allowed to access its results. So specifically, we're going to index query with two predicates, one called Paul, much like the Paul for the field, which denotes the authorizees, who is allowed to see the results of this query. And we're going to get this from the sub-queries of that particular query. And second, an invariant that describes all the rows that are returned by that particular query. For example, does this query return rows that are public or private or whatnot? And our API for equals and less than and or and so on and so forth carefully track the policies and invariants of the subqueries to build up the policies and invariants for the superqueries. The last piece is the extract function. So how do we actually extricate the policies from the queries to determine the authorizees of the particular database action? For example, let's look at the select operator that takes a query and returns an action, where the action yields the list of rows that correspond to that match that particular database query. As before, we're now going to have refinements, right? So the query was refined with a policy and an invariant that denoted which kinds of records are returned by the query. And the action is going to be indexed by some authorizees, and it doesn't actually directly produce any values to the output, doesn't respond to users, and so these observers are just the empty set. But we are going to add a constraint, one of those refinement bound constraints, that's going to make sure that a particular relationship holds between the invariant, the auth predicate, and the policy. Specifically, we are going to require that all the rows that satisfies the invariant are authorized as long as they satisfy the particular policy corresponding to the query. Okay, so the important bit here is that all the rows need not be viewable, just those rows that actually satisfy the invariant and therefore may be returned by the query. So that's it. This is our API that essentially tracks the database, the policies as they are specified in the database schema, and brings them all the way into the database action by tracking how the policies are aggregated across query combinators and query execution. And finally, when we glue that together with the effect system that we described earlier for bind and return, we get a type for the server. And when we put the whole thing together, we get an end-to-end guarantee that the servers always adhere to the declaratively specified policies. This concludes this whirlwind overview of the Storm Web Framework. If you want to learn more, I suggest you check out this particular URL, stormframework.github.io.
Okay, that was somewhat abrupt ending there, but let's thank the speaker anyway, even though he's not actually here. I really enjoyed that talk. I love refinement types. I think it's really exciting. So Nico is here to answer any questions that people might have from the audience. I don't think any questions were asked yet. So are there any questions? I have some questions myself, actually. Nico, in one of the slides that he showed was that the type of return basically imposed no constraints. Did I remember that correctly?
Can you hear me?
Yeah.
No, that's not the case. Actually, it's very important that it has restrictions. Right. So it has some bounds that relates the input and outputs of the two actions you are sequencing. Specifically, the set of observers of the second action should be a a subset of the authorities of the first action.
For bind, right?
Yeah.
But
For return, yeah, it does not, because return itself doesn't have any effects.
So, but then my concern is what happens if I do a query, I get something that is potentially sensitive, I return it as a pure value, and then I run another query at some point, and I might leak information, right?
Yeah, that's true. So the action monad doesn't only protects you from the effects happening inside the monad, but if you run it and do something else like outside it, it won't protect you. So yeah, you can run the monad, return something, and outside the monad, like do something with the value.
Right.
And yeah, that will be leaking information, but that's why it will protect you from effects happening inside the monad.
But then it seems to me return should be more restrictive. Like I should not be able to return something that is sensitive.
Actually, yeah, that's a fair point. But in practice, what happens is that your actions are like your top level controllers, and there's like some trusted code that executes the monad. But it's in reality very tiny, small. So it's like easy to audit.
So you're saying the action monad is basically my top level monad, like all my server handlers, everything would run in action. Is that?
Yeah, and yeah, on the top level you have like a very tiny code that like runs it and then
I see.
Basically execute the monad.
I see. Okay. I see that Philip Butler raises his hand, so I'll invite him to the stage now. Philip, please.
Hi.
Floor is yours.
Right, I was just trying to type it in, but I didn't quite get it all typed in. So you've described a system that works well for actually following the policies, but quite often with systems like this, there are just a few places where you need to get around the policies. This is sometimes called declassification. So for instance, you might have a policy that the password is secret, and the password is secret, except when you're actually checking if somebody's typed in the password. So have you thought at all about where you might need to not follow the policies and how you get around that? I'm not very familiar with this, but my understanding is this is fairly standard in this area.
Yeah, for sure. Yeah, so there are two, I think, topics related to that. One is that there's a bit of untrusted code that you have to write to actually run Storm, and particularly with the authentication method. Actually happens outside the action monad, so you have to trust that. So in that sense, that code could be leaking information if you don't do it right. And second, yeah, it may be the case that you need to declassify inside the monad itself. In all the examples with coded, we never need to do it, but it will be pretty straightforward to add to the system because it's basically refinement type, so you just can assume that a function do the declassification and be like straightforward to do. You can just add like a function that like declassify, and it will work.
Okay, so it should be fairly straightforward to add a declassify operator.
Yeah.
Okay, great. Yeah, it looks like
we
really.
We experienced that the policies are expressive enough so that in many cases you don't actually need to declassify, where in other systems you actually need. For example, something like an example where other systems need to declassify is when sending emails, because the label system that they use doesn't know anything about emails. But we can easily encode that in a Storm, because basically when you're sending an email, you are sending that information to the user that has that email. So we provide an IPA that actually lets you send email without declassifying any information, because you know who will be the recipient of that information.
Right. Okay, but it sounds really like quite an exciting system. I'm looking forward to be able to the people who put together websites that I use being able to use this.
If I can ask actually a follow-up question sort of to Philip's question, what if you have, what if you want to have like, maybe I I'm not allowed to see a row from somebody who is, not me, but maybe I should be able to count. Like, for example, right, some sort of derived information that should be allowed. That I should be allowed. For example, maybe I can see how many users there are, even if they are not me. I mean, would you? Or maybe I can count maybe how many wishes you have. Maybe in some policy I can't see your wishes, but I can see how many you have. Would that sort of thing be expressible?
Yeah, to make the example concrete, I'm going to focus on, for example, the wish example where you the description field is private. So you won't be allowed to see the field. But what you can do is actually the level field itself is not private, so you can access it. In particular, if you do that, it will allow you to count the number of private wishes without knowing the content. It's basically up to you if you decide to make the private field private or not. I mean, the level field private or not.
I see. Okay. I see there's one more question. I think we have time for one more question. There's a question from Chris. Let me invite him to the stage. Maybe he can ask it himself.
Yeah. Hey, can you hear me?
Yep.
Okay, I was just saying, it looks like in order if I had complicated authentication rules, it looks like every time I query for data, I would have to write queries that reproduce all of these authentication rules. And I wondered if the rules are represented in a format where you could maybe like construct a filtered query automatically, like say, just give me all the wishes that I can see.
Actually, the original work that was cited in the slides, where they presented the like the security monad with authorities and observers, it was meant for do automatic repairs of security vulnerabilities. So that one actually synthesizes like repairs for queries. I don't know if like that's what you're talking about.
I'm not sure. I'm not sure I understood. Sorry.
In the sense that you may write a program that leaks information, and what this like system provides you is a way to repair those programs so they won't leak anymore.
Oh yes. Except I guess I wasn't thinking of it as a repair so much as I might just not want to reproduce the same code to express the security policy in many different places throughout my code base.
Yeah, that's fair. I think that's something you could do. Although we've experienced that in reality, you do want to write the code because it's not just about. I mean, your business logic actually depends on doing like this. It's not just the data you're getting, also the business logic. For example, if you don't have access to data, you want your application to react gracefully to it, right? So you do want to like do that explicit check and took a different path. Is that not the case?
Right.
So what I'm saying is that in reality, you don't write. It's like completely mixed within the business logic. And it's not that you can separate them.
Okay, maybe if we can take this offline if there's more to discuss here. Let's thank the speaker one more time. Thanks very much, Nico. And I will let you go from the stage. Thanks again. Okay, so our final speaker for today is Lucas Kramer. Let me invite him.
Oh.
Okay, so Lucas Kramer is a PhD student at Minnesota, where he's doing research on attribute grammars, but he's not talking about that today, I think. Instead, I think he's talking about work he did at Google, where he worked on adding generics in the style of GHC generics to Bluespec. Lucas, please take it away.
All right, can you see my slides?
We can indeed.
All right, thanks everyone. Yeah, so I'm Lucas. So a bit of background. So Bluespec is a hardware synthesis language, a high-level hardware synthesis language, where you can, for basically designing circuits, essentially, for designing processors or whatever kinds of hardware you'd like to specify. And it's a language that's heavily based on Haskell in a lot of ways. It's actually some of the same people that worked on early versions of Haskell also worked on Bluespec originally. There's a now they have a system Verilog inspired syntax for it that it basically uses the same sort of Haskell inspired AST, and the Haskell syntax is still supported. And it's been around for quite a while. It was started about 20 years ago, but just recently open sourced in 2020. So there's more details on Bluespec if you are interested. There's a tutorial last year at ICFP by Nikhil that you can check out if you want. And my project at Google internship last year was implementing a generics feature, which was merged upstream in March. So it's now free to use for hardware designers that are interested. Also, just for the purposes of the slides, anything that's in blue is Bluespec code. Otherwise, it's Haskell. The two look quite similar, as you'll see. So a little more background on the Bluespec than some of the features that we're interested in. So Bluespec's a two-level language. So there's elaboration time when hardware is designed, basically in terms of modules, and these modules get composed together, and this can be done programmatically and sort of generating the how the hardware design is, the different parts are hooked up. And then there's also another level, the hardware when it's actually being simulated or running in a physical chip, doing the logic part of it. So Bluespec also describes hardware in terms of basically we have rules that fire as atomic actions and interface methods that describe the interfaces between modules and how they are connected to each other. And values have implicit conditions attached to them that control when the rules can fire. And Bluespec also has some primitive, some very basic dependent types features. We can have numeric types, which we call kind pound for like number symbol, that let us have things like, for example, a vector of n 8-bit integers as a type. And also, familiar, Bluespec has records, which are called structs in the language, and also algebraic data types, which are just like Haskell algebraic data types. We also want to be able to have hardware designers use these algebraic data types, and the type class system is really what enables this. We have multi-parameter type classes with functional dependencies, amongst other features that we're interested in. So type classes in Bluespec, there's a lot of different ways that we use type classes. One example is the bits type class. This basically is specifying for any type A that has a serialization into a bit value, where a bit is a primitive type that's parameterized by n, which is the number of bits required to represent that type. So the bits type class has the pack method that packs a value into a bit vector, and an unpack that takes a bit vector and turns it back into the value. And the n, so it's a multi-parameter type class. So A is the type that we're serializing, and n is the number of bits required to represent it. And the functional dependency specifies that A determines n. So we determine the number of bits based on the type that we're interested in. Also, there's type classes for pretty-praying things. There's two different syntaxes for Bluespec, as I mentioned. So there's two different versions of a show type class. We also sometimes want to initialize structures with default values. Or there's also some type classes that are used internally in the compiler, like prim deep seek cond, which is used for composing together, basically lifting the implicit conditions of a value, determining when it's ready for the compiler. And what all these type classes have in common is that they can have lots of boilerplate instances that we write for almost every type in our design. So the Bluespec compiler supports deriving type class instances just like Haskell. So some of the default type classes like fshow, eq, ord, and also bits all have derived implementations where you can just say deriving some list of type classes on your data type declaration. But adding new derived type classes means that we have to modify the compiler, which isn't optimal. So for example, we have the default value type class, which has a single method that's just a value of type A. And we have an instance for integers where the default value for integer is 0, or integer is a primitive type. But if we have some data type foo, we basically want the default value for any data type to be just the default values for the first constructor with applied to the default values of all the constructor arguments. So we want to generate this instance default value foo where we just have foo applied to default value, which requires this big ugly blob of Haskell code in the implementation of the Bluespec compiler just for this one very simple instance. And this isn't even the entire thing. This is only for data types. And the question is then, what if we want, or what do we do if we want to customize the derived behavior? For example, if we, instead of the default derived bits type class, what if we now want to have a byte-aligned version of bits? Or there's many other examples of this where we want to sort of slightly tweak how the driving happens. And we don't want to have to modify the internals of the compiler. So one option that we thought about was doing something along the lines of template Haskell, where we can basically programmatically generate code at compile time in the Bluespec specification. And we actually already have a compile time evaluator for purposes of static elaboration. So it would be conceivable to just build on that and use that for doing a template Bluespec. But there are a couple of significant issues with this. So one is that template Haskell is nice because the GHC is already in Haskell. We have ADTs representing the abstract syntax of Haskell. In Bluespec, if we want to have template Bluespec, we somehow need to expose Bluespec's AST in Bluespec rather than Haskell. Another issue is with quasi-quotation. If we want to actually sanely specify bits of Bluespec AST in our sources, we somehow need to port a parsing library into the Bluespec hardware language, which seems a little, it could be doable, but it's a bad power to weight ratio, as some would say, for a lot of work to do this effectively. Another option is doing something along the lines of GHC generics, where GHC generics is basically a generic approach to deriving type class instances, where we have this generic type class that specifies a representation type for any type A, where that's sort of in terms of basic sum and product types, and we have a way of converting from any value to its representation value and back in the other direction. So then we can define implementations for type classes on this representation and be able to automatically get an implementation for any type that can support this. And this does cover most of our desired use cases in Bluespec. Just for completeness, we also did think about scrapper boilerplate, doing something along those lines, which is an approach to doing generic folds and traversals. Most of you probably familiar with it. This is maybe a little less well suited to implementing like overloaded things like bits. Another more subtle issue is that Bluespec doesn't have the same kind of rank 2 quantification we'd need for a lot of these types in order to write. Like the type of G-fold L, for example, or so we thought. I'll get back to that in a minute. So based on this, we decided to implement something along the lines of GHC.generics in Bluespec. So now talking about a little bit of the design for generics. So we have the generic type class in Bluespec here. We don't have type families in Bluespec. So instead, we just use a multi-parameter type class with a functional dependency, which is basically equivalent. So we have the generic of A, and for any type A and R, there's an instance. If R is a generic representation of A, and the type A uniquely determines the representation type. And we also don't care about types, generics for types this kind star to star for now. So this just means we don't have a generic one type class like in Haskell, and we also don't have to have an extra type parameter floating around on all of our representation types, which is nice for a few reasons. So for example, here looking at the representation type for a struct. First of all, we're not following Haskell's naming convention. So I have this, if a struct foo on the left, the representation type is shown on the right with the metadata abbreviated because it's very large and messy. So we're not following Haskell's convention. So instead of K1 or rec0 for like the sort of bottom level concrete types and that are the members of the struct, we just have conc for concrete. Also, meta instead of M1 is what we use for tagging types, representation types with their metadata. Another really nice thing and really interesting is Bluespec has inductive tuples. So we have basically a primitive pair struct that a tuple type desugars to. So instead of a custom :*:* constructor for product types, we can just reuse tuples, and basically is in terms of these primitive pairs that we can write the instances in the same way. For data types where we have some types, we also reuse the either type, and because once again, we don't care about kind star to star, so we don't need this extra type parameter. So we might as well just reuse either. So we have something in terms of tuples and eithers for our representations. So now talking about our metadata schema slightly. So meta tags the generic representation with info about constructor names and field counts and positions. So we already have numeric types, so of kind pound, which are for doing things like the sizes of a vector or something. So we already have that. We added a string kind specifically for doing generic metadata, for doing the names of fields and the names of members and like the package name and data. Metadata, another interesting thing is that we are including in the metadata, or the metadata type for data, a tuple of all the type constructor arguments that were given to the type, which we needed for a couple things. It lets us do stuff like, for example, if we want to print the type as part of our generic representation, or part of a generic implemented type class, or do a type name mangling for generating C code, which is a cool thing we did. I'll mention later. Bluespec also doesn't have data kinds, so we have these separate metacons named and metacons and non-constructors instead of having a single one that is like promoted to the kind level like we do in Haskell. And also we don't have zero constructor data types, which is just a little bit annoying, so we have a bunch of dummy constructors that never get used for all these data types. Another thing Bluespec has that's quite important in hardware are these fixed size collection types. So we have vector and also list_n, which is a fixed size list, versus vector is basically more of a statically typed size array. So these are important things that we want to handle generically. So we need some sort of type representation for them. So my first try at this was doing some fancy instances that basically turn a vector into a chain of tuples, basically, or as a product type for all the elements, which didn't work out. This would have been nice. It would have allowed us to, if you have a generic implementation for anything that's for a product type, we can just have this generic implementation work for collections then. And this unfortunately gets kind of messy, and I eventually gave up for a few reasons. But the alternative that we came up with was using just vector itself as the generic representation for these fixed size collections for vector and list_n. So basically we have an explicit instance for a vector and list_n then that just have as their representation type the vector n of the concrete elements. And just using the existing from and to and for converting between list_n and vector. So so now an example. This is what you actually write for doing the generic implementation of something. So prim deep seek cond, which is basically lifting these implicit conditions on values, is basically the simplest one, the simplest thing we've implemented with generics. So basically it has for a type A and B, it basically will lift the implicit conditions of some of the first argument and include them in the implicit conditions of the second argument. So the representation type for this, the generic type class version has this basically overloaded for the representation types. So we are just ignoring metadata. An either type require an instance for both of the operands, and we just call recursively. Same thing for a tuple for a sum type. Unit basically is for empty tuples, just ID, and concrete types. Then we recurse back to the non-generic primdeepseekon type class there. So then the question is, how do we actually specify the instance for a type class in terms of the primdeepseekon generic implementation? So the Haskell approach for this, if this were Haskell, we basically would write something like this, where we have the default instance signature or the default class type signature extension, where it lets you write a more specific type signature for a default implementation that only applies if there's a the default implementation is only valid if the more specific type signature can be type checked. So here we would have a default signature where we have the generic instance and the primdeepseekon prime type class, and the default implementation calls from, and then we explicitly define instances for the foo and bar types for primdeepseekon. Unfortunately, this isn't an option in Bluespec. We don't have default instance signatures. And also the primdeepseekon type class is something that's used internally in the compiler, and we'd like to avoid having to write, somehow still specify that there's an instance that exists for every type. So the alternative that we take in Bluespec basically allows what we refer to as default instances, which is basically a combination of the flexible instances, overlapping instances, and undecidable instances extensions in Haskell. So we can just write basically a instance of primdeepseekon A for any type A, and this will apply if there's not a more specific instance for primdeepseekon. And this has the needed context, and we can use this for the generic implementation. And also an interesting anecdote, we found a bug actually with handling mutually recursive instances in Bluespec compiler, which we had not previously exercised seemingly prior to adding generics. Also, something to note on this way of doing things is that there's no good way of saying we don't want a generic instance for some type. For example, bits and EQ aren't as nice with generics because there's some types where we don't want an instance for those type classes, but writing a sort of default signature means that there's always an instance that exists. It's just that instance resolution might give some annoying error messages if it turns out the primdeepseekon prime or generic type class doesn't have an instance for that type, if it's for some primitive or something. Another interesting thing, so I did slightly lie earlier. Bluespec actually does support rank 2 types, as we discovered after not realizing that these were a thing in Bluespec for some time, but only in struct and interface fields. So, for example, we have this interface for fold FIFO. It's basically a first in, first out structure, a queue for hardware. And it has a fold method that you can fold over all the elements that are currently in the FIFO, besides just the general NQ and DQ and all these standard things. So the type B, which is basically the type of thing that we're folding into, is not in the type of the fold FIFO interface. So this is a rank 2 type with a sort of implicit for all there.
Just so you're aware, we're well into question time by now. So.
Oh, I was told I had 22 minutes for it. Sorry.
Yes.
Sorry about that. Okay, I'll try to wrap up here. So the issue that comes up here is generic. We somehow have to write the generic representation for this, and this is the instance you may write where basically now we have a conc field with the type B shows up here in the generic representation. Unfortunately, recall due to the functional dependency, the type A actually is determining the R representation, or it must fully determine it, which does not hold because B is now polymorphic in the representation. So yeah, we have to fix this because we use generics for these internal type classes. So our solution to this is we add another, basically we generate wrapper structs for anything that has a higher rank member in it. And we have this alternative conc poly thing that says that this is a higher rank 2 member. Yeah, and then we don't lift implicit conditions from these. Yeah, we also implemented generics driving in the Bluespec compiler. And finally, we use this for a bunch of really cool things. One being generating C code and doing the equivalent for doing a serialization and deserialization and this lets us communicate generically with a equivalent generic implemented encoding and decoding module and hardware between a host and device application. Yeah, sorry about going over.
You're fine.
Yeah,
thanks very much.
Thank you.
Let's thank the speaker. Thanks very much. I always enjoy seeing stuff about generics. We have time for maybe 1 or 2 questions. There's one marked as silent, so I guess we should not bring that up in here. Any other questions? I actually have a question myself. Actually, I have 2, but maybe ask one first. So I'm not a Bluespec expert, but my understanding is that it has like pure functions, but it uses to model sequential circuits, and then it has this thing called actions, which are like updates to registers, things like this.
Mm-hmm.
Is it possible to write like generic actions?
To do what?
I don't know. I mean, maybe write to like I don't know, some generic way of updating a register depending on I mean I don't know what you might want to use it for, but I could imagine that there are some things that you might want to do.
So yes, I have used generics for doing some things with like actions involved. Like for one thing was doing basically going from implementing a hardware module for doing this sort of credit counting message exchange thing, which going into more detail on this project, where basically we're doing this flow control and you just specify the message channels you're interested in by just writing a struct that's the interface for your message interface, and using generics from that to synthesize a module that has actions and rules and things inside of it for doing different updates. So yes, I think is the answer to your question.
Okay. Yeah, I'm not sure how it works with the type system, so I mean, yeah, fair enough. Any other questions? I guess there's no. Oh, I see. Okay, sorry. All right. He says silent question. Okay, I misunderstood what he meant. Okay, there's a question from Artem. Let me bring it up on the stage here. Silent meaning he doesn't have any audio. Have you thought about getting deriving via in? May ease some challenges with deriving instances.
I believe that was something that I considered, that we considered and did not have time to pursue. But that is a reasonable approach.
Mm-hmm. Yeah, I mean it's very powerful in Haskell, so.
Mm-hmm.
And while we're on the topic of more powerful stuff, I mean, did you consider you mentioned I mean, scrap your boilerplate stuff, but there's also different ways of, doing generic programming. For example, like sum of products. But I guess maybe Bluespec's type system is not powerful enough to express it. Is that maybe right?
I mean, that's in terms of sum of products. I don't. I mean, that's basically what our representations are.
Well, this is binary sums of binary products as opposed to n-ary sums of n-ary products. So you don't have to do this arbitrary nesting thing. Like in this case, it's like a data type is a sum of a sum of a sum rather than a sum of a product. You know what I mean?
Oh, I see. Yeah. So I mean, Bluespec's like higher rank, or sorry, like numeric types and like sort of the more dependent features of Bluespec are kind of limited. So I mean, I'm not sure. So I mean, this is sort of, I guess, along the lines of what we have with dealing with these fixed size collections. It's basically that is a product of n types, but there isn't anything for a more direct sum type, I guess. I have to look more into what that is in Haskell. That approach you're referring to.
Well, I might be a bit biased because I'm one of the authors on it. So.
Okay. I'd be interested to read about it.
Fair enough. Okay. All right. If there are no more questions, oh. Right. Okay. Yeah. I mean, Adam remarks that generic SOP doesn't need data kinds, for example, so that Bluespec's type system might not be powerful enough. Yeah.
Yeah. Bluespec does not have data kinds. We kind of worked around that already for doing metadata, but it's a little bit messy.
Right. Okay. Well, let's thank the speaker again. Thanks, Lucas. It was very interesting.
Thank you. Thank you, everyone.
I will remove you from the stage, and then I think Ning Ning has some closing words for us. But she will have to show herself. There we go.
Oh, yeah. I will get my set up. So I will share my screen. Okay, cool. So thanks everyone. This is the end of the HIW program. Thank you everyone for joining us today, and hope you enjoyed this year's HIW program, because I really did. At this point, I'd like to take a moment to thank the people who have helped me a lot to put this program together. So first, I'd like to thank the great program committee of HIW this year, Dominic, Dan, Andres, Julia, John, and Edward. They put lots of energy in reviewing submissions and participating in discussion. So thank them a lot for their great contributions. And I'd also like to thank EDSCO, who co-hosted the whole program with me on AirMeet. There were lots of management duties with virtual conferences, and we won't be able to run the workshop without his help. Dan Andres and EDSCO also served as our session chairs as well. So this year, we had 13 submissions, with 11 of them got accepted in the program. This number is roughly in line with previous years. Within these 11 accepted talks, we have 20 distinct authors coming from 8 different institutions, with 2 of the authors not indicating their institutions. And we have 2 lightning talks come from 3 authors. So thank you to all the authors who have contributed to this great program this year. And we always encourage more submissions and sharing from the broader community. And we are looking forward for more contributors next year. And hopefully next year we will be able to hold the workshop in person. And speaking of next year, I'm happy to announce that our next year's program chair will be Alexandra Serrano. So Alexandra has great exposure and contributions to the Haskell community, and I'm sure we will have another great program next year. So finally, while HIW has ended, the SFP May conference and many co-located events are still yet to come. Please have fun with the rest of the SFP program. And that's all for HIW, and I'm going to end this session now. Thank you everyone for joining HIW with us this year, and people who would like to stay longer for discussion, please feel free to hang out in the virtual lounge on AirMeet. And thanks everyone, and hope you had fun. And I will see you in the rest of SFP.
Before you hit end session, let's thank Ning Ning for all her hard work. Thanks, Ning Ning.